a cosmic collision that rocked the very foundations of the universe. It happened on the morning of August 17th, 2017. Marica Francesi, an Italian astronomer and associate professor at the Grand Institute of Science, spent the entire night at the hospital in the picturesque fortress town of Urbino in central Italy. She was tired, having been part of an international team of scientists working. She'd been working with lasers at the Interferometric Gravitational Wave Observatory, which is based in the US, and the Gravitational Wave Detector in Italy, near Pisa. She knew that just 3 days ago, the instruments had picked up a signal from the collision of two distant black holes. Such discoveries had been made before. Since the last upgrade, the detector has been down 5 times. They also recorded similar events. For the first time, astronomers observed the merger of black holes. Just a few days after it was turned on again, on September 14, 2015. Now we have the chance to see gravitational waves, which are ripples in space-time caused by really dense objects colliding in deep space. This divergent wave covers the Earth like waves from a stone thrown on a calm pond. The observation of gravitational waves has confirmed what Albert Einstein said nearly 100 years ago, that gravity can also create waves that propagate through the universe at the speed of light. On October 3, 2017, Keith Thorne, Rainer Weiss, and Barry Barish, the 3 scientists behind the LIGO project, won the Nobel Prize in Physics for making it impossible to register gravitational waves. Ronald Driver, another key figure in developing the technology, passed away 6 months before the 2017 Nobel Prize winners were announced. However, the franchisee was a bit disappointed. The merger of 2 black holes is certainly an interesting event. In fact, she was hoping the league would register something different. Franchisee was on the lookout for proof of a crash between 2 objects that were even more mysterious than black holes. These are small, ultra-dense, rapidly rotating cores of massive stars whose nuclear fuel has already burned out and collapsed under their own gravity. Unfortunately, the league was only a week away from shutting down for 2 years for its next scheduled upgrade. So far, though, only the merging black holes have been detected. 2 detectors that the league had simultaneously toppled just now. It had been waiting for this, and it was now registered. The signal was clear. 2 neutron stars had collided about 130 million light-years from Earth. Even though neutron stars aren't as dense as black holes, the collision was strong enough to release a lot of energy and set off gravitational ripples that traveled in all directions through space-time. And now the ripples have finally reached us here on Earth. If the league hadn't been modified 2 years ago, these disturbances would be incredibly weak from a journey that took 130 million years. If they hadn't been picked up by the league, they would have reached Earth and gone unnoticed. The scientists haven't learned anything new. If this observation is confirmed, the merger, now known as G170817, could be a sign from space. For instance, our sun gives off not just light, but also a steady flow of particles that are almost massless. These are called neutrinos. So far, multi-channel astronomy has only been able to confirm 3 events outside our Milky Way in 1987, using optical telescopes and involving neutrino observatories. In 2018, a supernova was discovered using an optical telescope and a neutrino detector. The source of cosmic neutrinos was identified from the club in Antarctica. It was actually the Quasar object, which is really bright and linked to a supermassive black hole at the center of a galaxy 4 billion light-years away. But the game changer was the detection and observation of a gravitational wave burst in 2017. This time, physicists picked up on ripples in space-time passing through Earth and got the word out to astronomers right away. We set off to find the source of these faint ripples. Their optical radius and all other telescopes designed to receive electromagnetic radiation of different wavelengths are used to record the entire spectrum of signals. In other words, the cosmic cataclysm's messengers are pretty important. This historic collision and the ongoing multi-channel astronomy have helped scientists gain insight into the structure and evolution of these wonderfully strange objects in our universe. Neutron stars. Take a look at the full moon one night. Now picture this. you're holding a pen with a diameter that's less than 1% of the moon's diameter. The moon's transverse size is about 3,476 kilometers, so the diameter of the drawn dot would be about 20 kilometers. That's a little less than the diameter of Chicago. If you picture this city in a ball floating in space, the average size of a neutron star is exactly that. A neutron star is what's left of a star that originally had a mass between 8 and 15 times that of the Sun. We don't yet know the upper limit on the mass of the ancestors of neutron stars. It could be as high as 60 solar masses in a million years. The nuclear fuel runs out, and the big star slowly dies. This process ends with a supernova explosion. On average, in a galaxy like our Milky Way, a star dies about once every 50 years. In a vast, empty universe, a neutron star might seem like an insignificant object, but its incredible density, about 100 trillion times that of water, makes it anything. But a dense object is made up of a lot of matter packed into a small space. A neutron star is the densest object we know of, made up of ordinary matter. If you add more matter to a massive neutron star, or if two neutron stars collide, the star will keep collapsing until it forms a black hole. The diameter of our Sun is about 4 million kilometers, but it weighs about the same as a tiny neutron star, which has a transverse dimension of only 20 kilometers. Just picture the cherry on top of the cake that weighs 1 billion tons. Given their incredible density, these mysterious zombie stars are also spinning rapidly in space, with a rate of at least 1 revolution per second. Some neutron stars have narrow jets of electromagnetic radiation near their magnetic poles. As neutron stars rotate, we can detect bursts of radio waves from one of the jets aimed at Earth. A rapidly rotating neutron star can be thought of as a continuously glowing, rotating lighthouse. Ships at sea, or in this case astronomers, can only see individual flashes. These neutron stars are called Army pulsars, and that's what they usually are. The flashes of many pulsars are so regular that they've even been used to verify atomic clocks that determine international atomic time. It's thought that there could be as many as 100 million pulsars in our galaxy, although so far astronomers have only managed to discover about 3,000. But we still know very little about them. It seems that the two neutron stars spotted by LIG were formed about 11 billion years ago. At that time, the universe was still young. Earth and the solar system didn't exist yet. Two stars, each about 10 times more massive than the Sun, joined together in a cluster. They died one after the other. From a cosmic perspective, they weren't too far apart, and their remaining cores had a mass of just over 1 solar mass. The Sun's masses started to spiral towards each other because of mutual gravitational attraction. This was the moment their fate was sealed. As they spun around their shared center of mass, they were reshaping the very fabric of space and time, much like a bowling ball leaves an imprint. The deformation of space-time caused by the neutron star resulted in the Rabi gravitational waves propagating through the universe despite the fabric of space-time being stretched like a sheet held by 4 corners. As the two neutron stars drew closer, the universe continued to evolve and expand, with new galaxies forming and new stars being born. About 130 million years ago, the neutron stars got so close to each other that they each had a tidal effect on the other's surface, similar to what the moon has on Earth's oceans. The tidal effects were destructive, stretching and compressing the stars. At some point, a cosmic catastrophe took place. Eventually, the neutron stars collided and exploded. Some of the matter that was ejected in the explosion stayed connected to what was left of the pair. The debris around the supernova remnant formed what we call a recycling disk. This led to the formation of a powerful jet of jets from the matter of the ion disk, which traveled through the universe at close to the speed of light. It was studied in the X-ray, optical, and radio bands. On top of that, the jet was the source of a short and incredibly strong burst of gamma rays, the most powerful electromagnetic event we know of. Some of the ejected mass managed to get past the gravitational pull of the supernova remnants, forming a very hot and rapidly expanding cloud that looked like a donut that kept getting bigger. This cloud was so rich in neutrons that it triggered a reaction to form elements heavier than iron, such as gold, silver, and platinum. It's thought that the cloud contained about 10,000 Earth masses in heavy elements. That's 236 million tons of pure gold, which is 236 times the weight of an average car, and there was a tail of 21 tons, which is equal to 40 Earth masses. The radioactive decay of all these heavy elements produces light and optical radiation due to radioactive decay. After the glow, which is called quantum. When two neutron stars merge, the density of the new body increases significantly. It's likely that a merged neutron star will become too massive to continue existing. It collapses in on itself and forms a black hole. It's important to note that the merger significantly amplifies the gravitational surge that was present before the collision. Gravitational waves are invisible messengers of the big, bad impact, and they, with the energy of 200 million suns, are scattered in all directions at the speed of light. At the same time, on Earth, the Cretaceous period was getting underway, with dinosaurs taking over the continents and oceans. It wasn't until August 2017 that the gravitational ripples reached our world and affected sensitive equipment. A mirror was also affected. Over the course of 130 million years, gravitational waves have been moving at the speed of light, about 300,000 kilometers per second, as Einstein predicted. As a result, they become significantly weaker. We've also received other signals from this cosmic event, including light and radio waves that are moving at the same speed. When we see something in space, we're actually seeing the past. Even light from the sun takes about 8 minutes and 20 seconds to reach us. If the sun suddenly disappeared, which it shouldn't do in our lifetime, it would take us 8 minutes to realize what happened. When the Vega detectors picked up the gravitational waves, they sent out automatic notifications. The notifications were picked up by a few so-called first responders, whose job was to look over all the possible candidates flagged by the program. It became clear that the data was pretty sensational, and the signal strength pointed to two objects whose masses fell within the interval corresponding to the masses of neutron stars. To put it another way, it was less than the mass of black holes. Theoretically, this meant that the collision should even be accompanied by electromagnetic radiation. As it turned out, just 2 minutes after the gravitational waves were registered, the Fermi Space Gamma Ray Telescope picked up a strong burst of gamma radiation. Do you remember the story of Isaac Newton, who was hit on the head by an apple and then suddenly came up with the idea of gravity? It's believed that this is how Newton had his epiphany. That's not quite right, though. He did, however, observe apples falling from a tree in the orchard on his Woodstock estate in Lincoln County. Maybe, more than 3 centuries later, that apple tree is still growing. Newton was also wondering why apples always fall to the ground in that same orchard. He came up with the theory of universal gravitation as a result. He published this work in 1687. Newton's theory says that gravity is the force that affects all material bodies in the universe. It depends on both mass and distance. Newton said that all particles of matter are attracted to each other with a force that depends on their mass and the distance between them. Newton's law of universal gravitation was the gold standard until Einstein came along. For Einstein, a Swiss patent office clerk who dabbled in physics in his spare time, gravity wasn't really a force at all. He said it was actually a warping of space and time, or space-time, made up of 4 related dimensions. 3 spatial: up, down, right, left, forward, backward, plus another dimension of time. The general theory of relativity, published in full in 1916, states that what we think of as gravity is actually a result of the curvature of space-time. Massive objects like stars and planets warp and twist the fabric of space-time, creating mountains and valleys, ridges and plateaus. This makes nearby objects zigzag through space-time, like they're rising and falling. It might seem like the sun is pulling the Earth towards it, which is why our planet orbits around it. It basically means that the Earth's motion is determined by the curvature of spacetime around the much more massive sun. Moreover, Einstein demonstrated mathematically that any non-ideally spherical accelerating mass and binding spacetime serves as the source of gravitational waves propagating through the universe at the speed of light. Even the tiniest bit of movement can create gravitational waves, but they're usually too small to be noticed. For time-space warping to be measurable, an enormous amount of energy is needed, like in catastrophic cosmic events involving objects as massive as black holes and neutron stars orbiting each other and then colliding at 1/3 the speed of light. Einstein said that these collisions excite gravitational waves of great energy, which then wash over planets, stars, and anything else they encounter in their path as they propagate. They carry information about what caused them, and maybe even about gravity itself. In his later writings, Einstein came back to the topic a few times over the years, but for decades, gravitational waves existed only in theory. In 1974, astronomers Russell Allen Haas and Joseph Cotton Taylor Jr. of the University of Massachusetts in the U.S. indirectly proved the existence of gravitational waves. They noticed that in a system of two gravitationally bound neutron stars, the orbital period, that is, the time it takes for the stars to make a revolution around a common center of mass, gradually decreases. As the system loses energy in the form of gravitational waves, the two bodies gradually converge and move toward an inevitable collision, according to Haas and Taylor. This type of system is now known as a body-chaos pulsar. In 1993, these scientists were awarded the Nobel Prize for their work. However, the results of Haas and Taylor didn't provide direct proof of gravitational waves. Experimental confirmation was needed, and scientists needed new, highly accurate equipment to get it. The result is two twin detectors working together, one in Washington State and the other in Livingston, Louisiana. Each detector uses the interference of two laser beams to make incredibly accurate distance measurements. The observatory is run by the scientific community, or a group of 1,000 scientists from universities in 16 different countries, with MIT and Caltech operating it. The idea of LEGO was first discussed in the 1980s. Rainer Weiss, Keith Thorne, and Barry Barish. But it was also important to get over some bureaucratic hurdles and secure the funding needed for a project of this scale. It took another 10 years before construction started. The League finally got started in 2002, and another 5 years later, in 2007, a third Vera detector joined them. It's located near Pisa, Italy, and is funded by the European Union. It's the result of human ingenuity, which has allowed us to gradually learn more about the most fascinating mysteries of the cosmos. The galleries are laid out in a grid pattern with small bridges crossing them, and they extend from David into the valley below the mountain range. A drone is flying above them. You'll see them as a giant Latin letter. This is the interferon meter, which is part of the European Interferon Gravitational Observatory. It's named for the cluster of galaxies at the top of Virgo. It's a cluster of about 1,500 galaxies. It's situated in the Virgo constellation, about 50 million light-years away from Earth. Construction kicked off in 1996. The detectors are run by a research team made up of scientists from France, Italy, the Netherlands, Poland, and Hungary. France and Italy are responsible for about half of the operating costs, but the 2GO and 3GO detectors are designed to register waves in the frequency range of 10 to 10,000 Hz and 10 kHz. The way they work is pretty similar too. This is a laser beam that has been split in two. The two halves of the beam are sent to the far end of each of their perpendicular shoulders at exactly the same time, where they hit a mirror. The mirrors are securely attached to a special weight. You can see the prototype at the entrance to the main building. It's a very sensitive mechanism that's designed to pick up on any disturbances that could rock the mirror. Their source could be something like an earthquake or even just a passing truck. It's a pretty straightforward system. It's made up of weights that are suspended one below the other, which help to balance out any disturbances. This is similar to an experiment we recommend children try. If you fill a bottle with water and suspend it, then add another bottle below it, another bottle below it, and so on, you'll see that not a drop of water will come out of the lowest bottle, even if the deflection from above is pretty strong. The system with more active elements is a little different from the one at the top. The laser beam hits the mirror and bounces back. This is repeated 400 times. Because the beam bounces back and forth so many times, it covers a distance of 1,200 kilometers instead of just 3. Once the two beams are back together, the scientists take a look at what they've got. If there were no gravitational waves, the rays would return to where they started at the same time. So, there's no interference. However, if the detector passes gravitational waves, there is a local, very small disturbance of space-time, which we can't feel. Gemini lie detectors and wind detectors can only pick up waves that are a lot stronger than they would normally be. The frequencies are gravitational when they're passing through. Rabi, one of the two galleries, either lengthens or shortens slightly. In this case, the difference in length is less than 1/10,000th of the diameter of an atomic particle, like a proton. When one arm gets shorter, the other one gets longer, and then they switch roles. The lengthening or shortening of an arm depends on how far it is from the equilibrium position. In other words, it depends on the distance from the equilibrium position to the crest of the wave. The change in the path length of the laser beam means that the reflected light is out of phase with the source light. Put simply, the time it takes for each beam to get back to the source is slightly different. Scientists then look closely at the amplitude and frequency of the phase shift, which helps them understand the properties. When the recorded signal is analyzed with the results from other detectors, gravitational waves are identified. Scientists can pinpoint the source of these waves, which are caused by a cosmic catastrophe that has disturbed the fabric of space-time. The more detectors we install in different locations around the world, the more accurate our results will be. Today, finding all the sources of gravitational waves requires combining data from detectors and two detectors. They'll be able to get a lot more accurate source locations soon, thanks to similar detectors in Japan and India. Japan's Kagra detector, the COMEX gravitational wave detector, started working in February 2012. The new generation of detectors, such as the antenna, telescope, and exporter, should be much more sensitive, and those designs are currently in the works. The plan is to make the underground detector a 10-kilometer-long telescope, and the detectors for the huge ground observatory a 40-kilometer-long. These detectors will be so sensitive and accurate that they'll be able to register gravitational waves coming from neutron stars that have begun to converge, which are still 1,000,000 years away from merging and forming a pulsar. It seems that chaos and the body were responsible for this one, and it was discovered after the launch of Ether. It's been about 10 years, but we haven't seen any results yet. Right from the start, scientists thought this was possible, so there were always plans to make the detectors much better. In 2010, both the League and the RGO were shut down after 5 years, and $620 million had been spent. It looks like the gravitational telescope has either been upgraded or is now up and running. The testing phase kicked off in February 2015, and the official observing cycle began on September 18, 2015. The new installations are 4 times more sensitive than the original. The first upgrade at MSU happened in 2011, and it increased the sensitivity by a factor of 10, and then it was put on hold again for another significant upgrade. It's now a quad detector, which started collecting data in August 2017. Before that, 2 detectors were used for observations. The modernization and previous years of effort paid off handsomely. Even before it was officially 90, the League had relaunched. On September 14, 2015, LIGA, which was still being debugged, made detector history. LIGA picked up a gravitational signal from the collision of 2 stellar mass black holes, or, to be more technical, a merging double black hole about 300 million light-years away from Earth. The announcement of this amazing discovery, which was preceded by lots of rumors on social media, was made a few months later on February 11, 2016. The words registration and gravitational wave were all over the press, as were Lee and Einstein. They were a hot topic at informal gatherings among scientists, and even family dinners. The following year, Weiss, Thorne, and Berry shared the Nobel Prize awarded to them for the discovery. Once we had discovered gravitational waves, we could observe their sources using other methods too. We could intercept various distant cosmic messengers to find out more about the same event. This approach would later be known as multi-channel astronomy. At the time, though, many astronomers thought it was unlikely that gravitational waves would ever be observed directly. The idea of astronomers working together to study gravitational waves seemed a bit unusual to them. It wasn't that scientists didn't believe in the existence of gravitational waves. Not many people doubted it. They have to exist. Einstein's equations are structured in a way that makes them inevitable, so they all agreed that a major cataclysm must disrupt space and time and serve as a source of gravitational radiation. If astronomers can detect a cosmic afterglow from the gamma-ray flare that matches up with the gravitational waves, it would be proof that gravitational disturbances travel at the speed of light. This would be proof that Einstein was right 100 years ago. They'll also be able to look into what caused the gravitational wave, its surroundings, and how such a huge amount of energy was released. Black holes don't emit much electromagnetic radiation. Once an extremely massive star collapses, only the gravitational field is left. Nothing can escape from it to emit light. Black holes aren't really the best subjects for optical telescopes. But what if they were neutron stars? In 2010, Columbia University astrophysicist Brian May figured that when these dense objects collide, it will be more than just space-time being distorted and gravitational waves being generated. He also believes it'll result in the formation of quantum particles. This flash is about 1 in 100 as bright as a supernova, so you should be able to see it with an optical telescope. Based on his calculations, a kilonova is formed in a hot cloud of radioactive matter ejected in the collision and from the radioactive decay of heavy elements. They're created through nuclear fusion. On top of that, the collision will also result in a brief flash of gamma radiation, which we'll call a short gamma burst. Then, we should be able to see the afterglow of the gamma ray burst in radio and X-rays, and eventually even in the optical range. This will help us to know exactly where and when to look. It's not easy to get scientists from different fields to work together. This one seemed particularly challenging. At the time, gravitational waves were still just theoretical, and optical observations were a science that had been around since ancient times. Astronomers weren't sure if it was even possible to see electromagnetic manifestations of gravitational waves. They figured it'd be tough to register gravitational waves when they're traveling through the Earth. The detector picks up the slight difference in the return time of the reflected laser beams. Then, computer programs automatically load this info into a special candidate database. In the gravitational wave events that happened in 2017, the system flagged one that could be the merger of two neutron stars. The chance of a false alarm was really slim. The combined mass of the two objects was only 7 solar masses, much lighter than a stellar mass black hole, but in line with what we know about the masses of double neutron stars. It looks like two neutron stars are merging. The program also indicated that there is a 100% chance this event will be observable in the electromagnetic spectrum. The system's calculations show that the merger happened pretty close to Earth, about 130 million light-years away. Fortunately, this was the case because at that point, neither would have been sensitive enough to record the event from a greater distance. Later on, the optical equivalent of this gravitational event was dubbed the SWAP supernova, with an army of 2017, or SS-17 for short. Given the size of the area where the signal came from, it would have been too big to focus on with optical observations. Even so, the coordinates from the League of Virginia could narrow the search area enough to identify at least the galaxy where the collision occurred. They just said it happened in a particular area of the sky, which is about 150 times the size of the full moon. To narrow the observation window, Alexander Berger and their colleagues first decided to add a powerful optical camera to the observations. Dean Dark Energy Camera. The Dark Energy Camera, which is mounted on the Victor Blanco telescope in Chile, is operated from Harvard. They quickly took a few pictures to get a general idea of what was in the area. It was a huge area, and it took them about an hour to find a galaxy 130 million light-years away. They spotted a bright source of a previously unseen galaxy there. It's called JC 4993, and it's in the constellation Hydra. This meant that the radioactive decay of heavy elements was already underway. They combined them during the light merger. The cloud of radioactive debris is a bright blue. It's like the tips of a gas burner's flame tongues, incredibly hot. Over the next few days, the cloud gradually disappeared, and telescopes around the world kept a close eye on it as the ejected material cooled. The cloud gradually changed from blue to a dark red. Astronomers were able to study the spectrum in detail and identify chemical fingerprints. It became clear that a lot of heavy elements, including gold, platinum, and silver, are formed in these kinds of collisions. So, we finally know how these elements are formed. The Chandra X-ray Observatory picked up the first clear signals of fusion in the X-ray range. After the X-ray range at the very edge of the electromagnetic spectrum, we have the gamma-ray range, which is the highest energy radiation we know of. When two neutron stars collide, most of their matter merges to form a single object. It's likely to collapse rapidly under its own gravity into a black hole. Some of the matter is ejected at high speed in the form of a jet. In other words, it's a narrow jet of gamma-ray particles traveling at close to the speed of light. It was this brief burst of gamma radiation that the Fermi Gamma-Ray Space Telescope picked up on. Less than 2 seconds after the gravitational waves were registered, the mirror also fell. On July 2, 1967, two American satellites, UA-3 and 4, recorded the first ever gamma flashes of this type. At first, scientists thought they were the result of nuclear weapons tests in the Soviet Union. It took about 10 years of observation to figure out that these gamma-ray flashes, which can last anywhere from a few milliseconds to several hours, are coming from deep space. The ultra-short flashes, which last less than 2 seconds, are called gamma-ray bursts. The bursts, spotted by the Fermi telescope, finally confirmed what theorists had long believed, that the merger of neutron stars may be the source of short gamma-ray bursts. These orbits are thought to be the most powerful explosions in the universe. At the other end of the electromagnetic spectrum is the region of very long waves. We're talking about radio waves here. Radio antennas are traditionally used to observe neutron stars and black holes, and dozens of these were used to analyze the effects of the merger, which was the first of its kind in multi-channel astronomy. By observing two extremely distant, extremely dense objects that collided with each other more than 130 million years ago, which marked the end of their existence in the universe, it has demonstrated its incredible capabilities. The paper about this neutron star merger had over 4,000 authors. That's about a third of all the astronomers in the world. It would take years to analyze all the data they collected. But we still have a lot to learn about how neutron stars are formed. Maybe by looking at these huge events from our own planet, we can learn more about how neutron stars are put together. Well, try to figure out what makes their unassuming jets eject particles and send radiation into space. Well, never be able to travel to pristine stars? But multi-channel astronomy, with the power of many different telescopes around the world, and the use of giant particle accelerators, will soon help us learn more about them. Maybe we'll gain insights into how the universe is expanding, what's happening with the supermassive black holes at the center of galaxies, and finally, once and for all, confirm if Einstein's general theory of relativity was right. When you add high-energy astronomy with its new X-ray telescopes, such as Germany's ROSA XM and Chandra, and gamma-ray detectors such as the Fermi Gamma-Ray Telescope and Integral, scientists have been able to study these mysterious objects in entirely new and mind-boggling ways. How did our world come to be? How did the elements come to be? All the elements that exist on Earth were created in space in one way or another. Mendeleev's periodic table has 118 elements, and 94 of them are found in nature. But right after the Big Bang, which happened 13 million years ago, there were no elements at all. At the beginning, there were only the basic building blocks, quarks, which are found in slabs. The neutrons and protons we're familiar with are built from them, and from them, in turn, atoms are formed. When the universe was first formed, it was extremely hot and dense, which meant that quarks couldn't bond for at least a few minutes. The quarks were in a kind of quark soup. As the universe expanded and cooled, it became possible for quarks to combine into protons, hydrogen nuclei, and neutrons. Then, Helium nuclei were formed from 2 protons and 2 neutrons. The universe kept expanding and cooling, but it took another 38,000 years for the electrons that had replaced all the electrons to become trapped in orbits around the nuclei, and the first very light atoms were formed. The main elements that formed were hydrogen and helium, with a small amount of lithium. Let's go back another one. 6 million years. The first stars and galaxies came about when clouds of interstellar gas were pulled together by gravity. That's when the heavier atoms, carbon, oxygen, and iron, were formed. Massive stars grew to be giants, and in their cores, thermonuclear fusion transformed helium into carbon and produced magnesium, nitrogen, oxygen, neon, and iron. The appearance of iron marks the end of fusion. But when stars die in a supernova explosion, they create even heavier elements: nickel, cobalt, copper, manganese, zinc, and vanadium. However, computer models show that the energy of the supernova explosion isn't enough to produce elements significantly heavier than iron. So where did all the silver, gold, platinum, mercury, molybdenum, uranium, and other such elements come from? Some scientists think these elements might have formed when neutron stars merged during what's called the fast neutron capture process. The letter P shows how quickly the decay process is happening. This is when a series of nuclear reactions involving fast neutron capture by heavy nuclei like iron creates elements heavier than iron. When neutron stars merge, they release a ton of neutrons that are super hot. The neutrons hit the surrounding atoms, which creates the heavier elements. When the merger of 2 neutron stars was first spotted, scientists were able to see blue, cold, and radioactive neutron stars. The heavy elements that were formed in the collision are decaying. Another thing we need to figure out is how these heavy elements got to Earth. It's possible that some of them were delivered by meteorites. For instance, nickel and cobalt are frequently present in iron meteorites. Iron, nickel, and cobalt are all formed at the same time during the fusion process in supernovas. Then again, they might have been present in the matter from which the solar system formed about 4-5 billion years ago. Over time, these elements were released from the Earth's crust. Let's dig a little deeper. Why was the planet blue? The color of a cosmic object depends on the wavelength of light it reflects. Depending on the circumstances, light can act as either a wave or a particle. The wavelength is basically the distance between 2 crests or 2 troughs. Waves. The wavelength depends on which part of the electromagnetic spectrum the radiation falls into. There's light wavelength and there's gamma radiation. Radio waves are the shortest, while light waves are the longest. The energy of each photon, which is the basic building block of light, is directly related to the wavelength. This means that the shorter the wavelength, the more energy is packed into that type of radiation. Gamma rays have a lot of energy, while radio waves have much less. Visible light falls somewhere in the middle. Let's take a closer look at the part of the spectrum that corresponds to visible light. The blue part of the spectrum has very short wavelengths. As we move to the other end, the red end, the wavelengths gradually get longer and longer. Bodies absorb light perfectly. These are what we call totally black bodies. As is the case with many solids and dense gases, the sun is a black body. You can also relate the spectrum of radiation to the temperature of a body. The wavelength at which more light is studied is directly related to temperature. So, the colder the object, the redder the light, and the hotter it is, the closer its color is to blue. This is contrary to the usual practice of labeling hot water taps red and cold water taps blue. Some stars are blue. That means they're really, really hot. They're about 7,000 degrees Celsius in temperature. Some are cooler and red. Their temperature is only around 4,000 degrees Celsius. At temperatures below 4,000 degrees Celsius, you can't see the light they give off, but it's stronger in the red than in the blue. The following ratio of temperatures for stars with colors ranging from 7,000 to 10,000 degrees is more widely accepted. White is between 6,000 and 7,000 degrees, yellow-white is between 5,000 and 6,000. Yellow is between 3,500 and 5,000, and orange is between 2,400 and 3,500. On Earth, we tend to associate heat with something red, reminiscent of a bonfire. It's also because it's difficult to heat a flame to a high enough temperature to make it blue. After two neutron stars merge, optical telescopes have picked up a blue glow caused by radioactive decay of heavy elements. Xenon. Previously, scientists thought that the clanova formed by the merger of neutron stars should be exclusively red. They figured that during the WASP process, the heaviest elements are at the bottom of the periodic table and have atomic masses over 140. These elements soak up blue light really well and don't let it leave the field cloud and gas that's ejected during a neutron star merger. But in 2014, Brian May and his colleague, astronomer Rodrigo Fernandez, suggested that clanova separates the blue and red components. Gear argued that not all of the matter in the field cloud gas formed by neutron star mergers has to be made up of elements with atomic masses over 140. If the processes of a given part of the ejected cloud only create elements with atomic masses less than 140, then the emission from that part will be blue. He also said that the elements in the ejected matter will come from different parts of the expedition disk. Some of them will have atomic masses greater than 140. Some will have a red glow, while others will have less, resulting in a blue glow, and both can be seen in the same event. It turns out that the intensity of the blue color depends on the composition of the emission and the number of neutrons and protons, which in turn depend on how long the neutron star lasts after the merger before collapsing into a black hole. The longer the neutron star lives, the more light elements it will create in the process, which makes the clan stronger. The color of the light gave us information about when the black hole was formed. The new ones that were observed during the merger, especially in the first few hours, were bright blue, and then a red glow appeared. Hertz says this shows the neutron star didn't last long. He figures the black hole probably formed as soon as a few hundred milliseconds after the merger. The interplanetary integration matrix isn't in the best shape. The copper wire has been stolen. Malcolm Long, a cheerful 77-year-old English astrophysicist with gray hair, shakes his head disapprovingly. Von Gehr is more than just an astrophysicist. He used to be Royal Astronomer of Scotland and director of the Stone Laboratory at Cambridge University. We're standing in a field in front of a thorny hedge that's pretty high. Behind it was once an interplanetary breeding matrix station, which was basically a vineyard-like wasteland under an icon with hundreds of cedar poles about 5 meters high each. They used about 200 kilometers of copper wire between the poles. It was this radio telescope that first picked up the pulsar signal on August 6, 1960, confirming the existence of neutron stars. Up until that point, they'd only existed in theory. Longy showed me the place right from an afternoon in January. We also stopped by the medical lab where he worked for a quick visit. This is where Ernest Rutherford started studying radioactive transformations of atoms in the late 19th century. This led him to create the planetary model of the atom in 1911, which suggests that atoms are made up of a tiny nucleus with electrons orbiting around it. James Chadwick also discovered the neutron here in 1932. Next to the hedge, on the other side of the idol complex, there's a real astronomical graveyard. There are 4 fixed black radio telescopes on rails. Their bowls are reflective and look like withered flowers. They're stretching out their petals toward the sun. There's a closed control room nearby, another abandoned structure. The wooden poles sticking out of the ground are all that's left of the interplanetary integration matrix that made scientific history, as with many other sources of copper, including church roofs. The price of this raw material has seen a temporary spike, which has unfortunately affected this product. The copper wire that once connected the poles was stolen and resold by some unscrupulous traders for scrap metal. Let's go back half a century, though. Back then, things were really thriving in these fields. There was a lot of hard work involved, with dedicated masters and scientists playing a part. The 1960s were a great decade for astronomers. In 1963, Martin Schmidt of the California Institute of Technology solved the mystery of quasi-stellar sources, or quasars. He showed that these are distant, super-bright, active galaxies associated with supermassive black holes at their center. 2 years later, Arno Penzias and Robert Wilson, American radio astronomers at Bell Laboratories in Hill Township, New Jersey, made an accidental discovery, the relic radiation of the Big Bang's residual glow. And here's where history was made. In rural Cambridge County, Josie Linda, a young highwaywoman from Northern Ireland, noticed a strange signal in 1967. She dubbed it a main on green and white rolls of millimeter paper, a kilometer-long crawl out of a small recording device. This message turned out to be from a distant pulsar, sending a weak signal to people, but she didn't know that at the time. At the time, no one saw the importance of starting a story about this. We have to go back another 50 years. The turn of the 19th and 20th centuries was an amazing time for physicists. In 1897, Joseph John Thomson made a major discovery. He found the electron. Rutherford, who had moved to McGill University in Montreal in 1898, was starting to grasp the sequence of transformations of elements in the process of radioactive decay. When he got back to Manchester, he looked into how high-energy alpha particles behaved on thin gold foil. In 1911, Rutherford put forward a planetary model of the atom. Rutherford believed that the atom is mostly empty space with a tiny nucleus of positively charged particles in the center. The nucleus is surrounded by a cloud of negatively charged electrons that spin around it. However, there were still some things that needed to be figured out. If we assume that the number of electrons is equal to the number of protons, the mass of the nucleus is larger than we expected. Then scientists thought there might be electrons in the nucleus too, which would balance out the excess positive charge. In 1920, Rutherford suggested that the nucleus was probably not made up of electrons and protons, but of protons and neutral particles, which he called neutrons. For the next 10 years, Rutherford says, Gear Rutherford and a man who had moved to Cambridge from Manchester with Rutherford kept trying, but couldn't detect this elusive neutron. At last, in 1932, they managed to catch it. The neutron. He was later awarded the Nobel Prize in Physics for this discovery. Once the neutron was discovered, the model of the atom finally took on a more complete form and was accepted by everyone. While most scientists were keen to keep studying the atom and its inner workings, there was one man who took a different approach. Fritz Zwicky, a Bulgarian-born Swiss physicist, started working at the California Institute of Technology in Pasadena in 1925. Everyone knew this unstable and self-confident man. During a lecture, he could, for example, suddenly fall to the floor and start doing push-ups on one arm. He also liked to start arguments for no reason. As you might imagine, many colleagues found him annoying. But by 1934, just 2 years after the neutron was discovered, Flower, his co-author and astronomer Walter Baade, had already published a short article linking the death of a massive star with a supernova flash and a remaining neutron star. As it turned out, this assumption was correct. Tsvetkov later discovered a total of 120 supernovae on his own. This was just speculation. Tsvetka's idea was based on the fact that neutrons don't have an electric charge that repels them from each other, which means you can get a very compact star out of them, Lange says. This paper is just a glimpse into the mind of the idea. As it turns out, there's no physics in it. As it turns out, Iris was right. It's a shame when a massive star runs out of nuclear fuel and dies. The collapse of the star's core leads to a spectacular finale with a supernova explosion, leaving behind a very compact and incredibly dense formation. It's a neutron star. These days, Sveta isn't seen as a fool anymore. He's regarded as a genius. He's also known for his work on dark matter from galaxy clusters, not just for his ideas on supernovae. Let's go back to 1934. Not many people were interested in the Flower hypothesis. At the time, astronomers were more focused on the issue of white dwarfs. As we now know, these are what's left of less massive stars, and they don't usually go supernova. But just 3 years after Tsvetky's paper, another scientist, Soviet physicist Lev Landau, published a paper on what he called the neutron core of a star. Robert Oppenheimer was one of the scientists who noticed Landau's paper. In 1939, Oppenheimer came up with a way to estimate how big a star could be before it collapsed into a black hole. Oppenheimer and his student George Volkoff figured out that this maximum mass should be about 70% of the mass of the Sun. It turned out that this result was wrong because they hadn't taken into account the strong nuclear interactions between neutrons. Later on, theoretical estimates moved this limit to somewhere between 1.5 and 3 solar masses. Oppenheimer had done everything. He also came up with the first estimates of the surface temperature of these objects. But the neutron star was so small that no one thought it was possible to detect them. Longy ponders for a moment. X-ray telescopes didn't exist back then, and it was generally thought that these stars couldn't be detected. This probably explains why the astronomical community wasn't interested in pursuing this further. Although it was known that neutron stars could theoretically exist, they were still regarded as something rather exotic. That was the situation until the end of World War II. At that time, Oppenheimer was working on something a bit more practical, the creation of the atomic bomb. Neutron stars sat in the back of his desk drawer until 1967, when they burst back onto the scene with a bang. Lang says the 1960s were a turning point for modern astrophysics. As a matter of fact, that's when modern astronomy got its start. In fact, up until the 1940s, astronomers mainly studied the universe by looking at light in the visible or near-visible range. The electromagnetic spectrum is made up of all frequencies of electromagnetic radiation that can be recorded, from lowest to highest, or longest to shortest wavelengths. This includes radio, infrared, visible light, ultraviolet radiation, X-rays, and gamma rays. With the advent of radio astronomy, scientists suddenly had access to highly sensitive instrumentation that was previously unavailable. This made it possible to discover whole new measures, pinpoint the location of the source from the recorded radio waves, and then try to detect the source of these waves in visible light. It's true that there was some confusion when, in the 1950s, radio telescopes began registering radio waves from sources that didn't correspond to any visible objects in the sky. These sources were compact. And yet, the brightness of the radio band was a complete mystery. Then, in 1962, John Bolton, who was the director of the Parker Observatory in Australia at the time, and astronomer Cyril Azart, used the moon covering technique to observe one particularly bright object. They made use of the fact that the moon's trajectory is well known and were able to pinpoint its location. When the moon moved in front of the source, the emission stopped. Then, when the moon passed the source and the radio waves could travel through, the radiation came back on. The following year, Martin Schmidt of the Naval Observatory in California took a look at this source with the Hale telescope and saw the jets coming from it in visible light. After looking at the spectrum, the scientists noticed a significant redshift. This meant that the object was moving away from Earth at a speed equal to 1/6 the speed of light, which is about 50,000 kilometers per second. They also figured out that the object was about 3 billion light years away from Earth. It seemed to be much farther away than many other galaxies, but it was much brighter. Schmidt observed the first quasi-stellar radio source that resembled a star. We now refer to it as a quasar. The following year, 1964, the idea was put forward that quasars are actually supermassive black holes. It's thought that they're at the center of most large galaxies, and that they're one type of so-called active nucleus of galaxies. It's been a really turbulent period. Many of us were fortunate to start work at a time when things were really taking off. Alan Meyer says it was a great time. He was a young graduate student who joined the Cambridge Radio Astronomy Group in 1963. He went straight into the search for new quasars at the suggestion of Martin Raef, a well-known radio astronomer. Today, Cavendish's lab is on the outskirts of Cambridge. But at the time of the discovery of the neutron, it was right in the center of the city. Wenger's room was conveniently located near the astrophysics professor's office in the old lab. Anthony Hewitt, the same professor, was interested in quasars, and, most importantly, in how they were being affected by solar radiation. At first glance, random fluctuations in intensity and the radio waves they send down are similar to the twinkling of stars, which we're all familiar with. It looks like the brightness of stars is changing, but it's actually just the turbulence in the Earth's atmosphere that's making it seem that way. Turbulence in the air causes inhomogeneity, which in turn leads to focusing of light. This is because, under the action of wind, the brightness of each star appears to fluctuate rapidly. In other words, the stars twinkle when waves pass through the resolved gas in the space between the stars. They run into similar issues. The interstellar medium is a bit of a mixed bag, with some areas being denser and others more dispersed. As they approach the Earth, radio waves also encounter the solar wind, which is made up of bursts of plasma from the sun. This makes it look like the radio source is flickering, which is different from the flickering quasars of the compact radio sources in our galaxy. Another type of active galactic nuclei with large angular diameters don't flicker. Studying how a radio source inflates can help scientists learn more about the inhomogeneity of the interstellar medium. Hughes figured that if we used big radio telescopes that could spot flickering sources in the sky, we could narrow it down to a quasar. His colleague Martin Ryan found several thousand radio galaxies, many of which could turn out to be quasars. It was impossible to see which ones because the telescope was operating at too high a frequency for us to see from the integration. Houston had the idea of building a radio telescope with a really sensitive radio antenna system that could detect very low frequencies from the UK Department of Scientific and Industrial Research. He got a grant for $17,000. It might not sound like much, but it was enough to drive 1,000 poles into the ground in an open field in rural Cambridge. Construction started in 1965 when Hughes designed the Interplanetary Station lecture matrices. He wasn't planning to drive the poles himself. 6 graduate students were given the task. One of them was Lynn Bell Vaughan. Gear says that among the master's students in the Department of Physics at Cambridge, it was pretty uncommon to meet women. In 1965, W. Cavendish, a 22-year-old girl who'd recently relocated from Northern Ireland, showed up in this lab. Langa said she was officially enrolled as a grad student at another college. Lynn Bell had a bachelor's degree in jazz physics from the University of Glasgow, and she had a 3-year grant that allowed her to work on her thesis at Cambridge. Like other undergraduates, she spent most of her time in the lab loft or in the field. Joyce Glenn Bell's dissertation involved building an information matrix and testing its performance. She wanted to see if the matrix could be used to study radio source fluctuations, investigate the role of the solar wind, and search for a quasar with Anthony Hughes' ventilation matrix and its wooden poles. It's definitely not what most people picture when they think of a radio telescope. Even so, at the outset, most of the radio astronomers' results were obtained with these straightforward arrays and poles and miles of copper wire to make the array work with such a large collecting surface. It's important to make sure it's phased. That means making sure the signals from the different parts of the matrix come in at the right delay so they can be put together to get a single incoming signal. Hewitt was the first to suggest this way of looking into how radio sources are selected. When Bell started using this matrix, there were only about 20 quasars known. By the end of her work, she'd discovered about 200 more. The Hewitt matrix covered about 210 square meters 5 acres. It's about the size of 2 soccer fields. Longo says this was enough to record fluctuations in the intensity of radio sources on a time scale of about 1/10 of a second. On top of the kilometers of copper wire, they also had to get about 5 kilometers of cable and 124 kilometers of reflector wire. The poles were set up in 16 rows at the right distance to create the required phase delay. Together, the matrix could register a wave about 7 meters long, which meant it could operate at the very low frequency of 81.5 megahertz. The matrix worked like a regular TV antenna, but you have to multiply its length by the number of fields it has, which is 2048. A matrix is different from a steerable reflector because it can scan the entire visible sky. When a radio is received, its signal causes the electrons in the wire connecting the poles to oscillate. The oscillations are sent to a connecting cable that's hooked up to a receiver in the lab, where the oscillations of the electric current are recorded. Today, we're sending a series of numbers through the cable to a computer. Back in the 60s, though, computers were analog, so Bell had to look over miles of scrawled red ink. The scrawls on a narrow strip of millimeter-thick paper running continuously from her recorder. If you go to the old control room, which is near where the matrix used to be, you can see several of these paper rolls on display. Bell was the only one looking at these because, as she puts it, the topic wasn't considered important enough to bring in other grad students to work on it as well. Bell says it was tedious and time-consuming, and she adds, "I didn't have time to keep up with everything. I was a bit behind in detecting inflation, so Bell had to keep a close eye on changes in the intensity of the fluctuations. She had to make sure that the squiggles on the recorder tape really meant radio waves from a distant source, and not interference from a tractor working nearby or a car arriving. They might look like radio waves too, but the squiggles associated with space sources looked like a specific interference pattern. They had two small protrusions on the sides and a large protrusion in the middle, and they were nicknamed Chads. Hughes thought it would be a good idea if Bell could make a map of the sky, marking where the flickering sources were. For each source she spots, she has to put an X on the map. If the source was in the same spot every week, she'd know it was a real quasar. Bell updated the map every week, analyzing hundreds of meters of paper each day with data from the telescope. On August 6, 1967, the recorder tape was about 120 meters long. Bell noticed her scribbles and was surprised. She named the half-centimeter-sized scribble for the vulture and marked it with a question mark, moving on to the next section of tape. She realized, though, that although her main was somewhere far away, it looked like a source of strong insulation in a patch of sky noticeably distant from the sun. But it was obviously not interplanetary flickers. Interestingly, whenever Bell saw this signal, it seemed to come from the same place in the night sky, as the initiation is a phenomenon associated with the sun. It was usually seen during the day, and Bell had deliberately chosen this area of the sky to investigate. She was not a fan of going to bed late. Interestingly, Zagreb never produced all three elements of Chad's interference pattern. Sometimes the flash lasted 1 minute, sometimes 2 minutes, but never 3 minutes. Hughes, Bell's supervisor, didn't keep a close eye on her work, hoping she could manage on her own. But if there were any issues, he was there to lend a hand. Bell figured out that this strange signal was coming from the same place in the sky over and over. She got in touch with the Hughes show. Hughes was curious. He decided to keep watching and speed up the recorder tape to get a closer look at the image. Hughes figured that if he stretched the signal to occupy more than 6 millimeters, he could study its structure on a daily basis. Bell had some trouble with the accelerated recorder for part of the day. She couldn't get it to run non-stop. The paper was running out pretty quickly. What was even more frustrating was that this signal was proving to be unpredictable. For an entire month, during the exact hours she'd been monitoring, the source had been elusive and didn't show itself. It seemed like it had vanished for good. Bell had pretty much given up hope of seeing him when, finally, on November 26th, this source showed up again. He's here. It's not an obsession. The next day, Bell noticed that the pulsation period is only 133 seconds, which is much shorter than what you'd expect from a star. Is there a chance this source is artificial? Now Hughes and Bell had their work cut out for them. Before we announce the discovery, we need to make sure there's no interference from other sources of radio emission. If they made a mistake, it would definitely hurt their reputation. We spent a lot of time trying to get to the bottom of this object. We also tried to find something that would show it was man-made and could explain this signal, Bell said. This scribble on the recorder tape seemed like some kind of foreign interference. It was strangely connected to the sidereal time system that astronomers use to locate objects in the sky. It's connected to how the Earth rotates relative to the stars, which makes sidereal days a little shorter than usual. It's 11:56 p.m. The new pulsing signal was recorded at the same time as the sidereal day. Bell recalls, "I remember we were trying to figure out if there could be a satellite appearing every 2356, but with a stable orbit for it to fly in. I couldn't find one. Once it was established that the signal had been registering consistently for months according to the stellar cycle, 4 minutes earlier each day and 28 minutes earlier each week, it became evident that it wasn't interference from a random person driving an old car down the road. It doesn't line up with people's work schedules, Bell says. They even wrote to all the observatories in England, wondering if they had run any programs capable of causing such interference since August. They all said no. Since this chat wasn't perfectly symmetrical, they figured the strange signal was traveling through the telescope at the same speed and coming from the same place as the signals from the quasars they were looking for. Then Hughes and Bell asked their colleagues Paul Scott and Robin Collins to see if they could register the same signal with their equipment. At first, they didn't see the signal because of a mistake in calculating how long it took the source to move through their equipment's field of view. But they eventually saw it, proving that the signal they detected wasn't caused by a hardware error. Hughes and Bell kept this strange pattern to themselves for several weeks. They only knew a few people in the team, and they were pretty close. Even Longy, whose office was right next to Hughes, who often went to the same meetings with him, had no idea about the discovery. There were whispers that something out of the ordinary had been found, but no one had any idea what it was about, Longy recalls. He says that the secrecy was partly down to the participants being wary of the theorists. They were worried that the theorists would use the data without asking before they'd had a chance to analyze it themselves. But mostly they kept everything under wraps because they wanted to make sure they got it right and to eliminate all possible sources of interference and outside interference. They took 2 measurements of the distance to the source. The researchers made use of a phenomenon called dispersion. When a radio signal travels through space, it keeps bumping into free electrons, and the signal that reaches us is made up of waves of different frequencies. Even though all the waves start at the same time, they're affected differently by the collision. The higher frequency waves travel almost instantly, while the lower frequency waves take a bit longer to reach the telescopes. Bell says that even then, astronomers were able to estimate the number of electrons over time, the lag between registrations and bursts. We found that the distance to the source was about 65 seconds. It's about 200 light-years away. Based on the latest data, the first pulsar is several times farther away. Based on this, she and her colleagues figured the source was inside the Milky Way, but outside the solar system, in the direction of the constellation Foxy. It was obvious that the signal was coming from outer space. Could it be that aliens sent it? What if there are other civilizations out there, sending us a signal from far away? The whole crew gave it a lot of thought. Of course, they could see that this was a possibility. Even so, if these are aliens living on a planet orbiting a star, we should be able to see changes in their pulsation due to the movement of their planet in its orbit. But they haven't noticed any changes. It was already December, and the group was still trying to decide how to publish the paper and whether it should mention aliens. Bell wasn't exactly thrilled that aliens could contact Earth and take her thesis away from her. After all, the defense was only 6 months away. Why should she? She reasoned, somewhat irritably. It would be pretty ridiculous if little green men were using some kind of device to send signals to a planet that's not that big. Hughes and Wright were also worried about the risk of a mass panic. If we're going to announce to the world that we've received a message from aliens, shouldn't we contact the Department of Defense first and run it by them? Or maybe the signal was a potential threat from a hostile nation? After all, there was a Cold War going on at the time. Did it have any implications for national security? These questions were taken very seriously at the time, but there was still no agreement on what this strange source was. On December 21st, just before heading out for Christmas, Bell stopped by the lab one last time. It was just getting started, and she wanted to settle up and look over the graphs on the tapes from the recorders, which were still moving at a rate of about 5 meters per day. Just before the lab closed at 10 p.m., she noticed a piece of hairpin-shaped object similar to the first one by the main. But now the source was in a very different place, right next to a supernova remnant in the constellation Leo and a really bright radio source. On the other side of the sky, in the constellation of Hydra, the signals from A were so striking that it was difficult to observe them. I'm sure you're curious. B went to the radio telescope to oversee the observation at a time when this part of the sky would be visible. Best, she got to the field at 2 p.m. It was a frosty, starry night. The telescope's receiver wasn't working too well because of the cold. Bell remembers trying to fix the receiver by breathing on it. She managed to get it to work for about 5 minutes. But even that was long enough to detect another one, which lasted 119 seconds. There was a series of bursts, but unfortunately, the pulsing source was very similar to the first one, but located in a completely different part of the sky. Bell felt a huge weight off her shoulders. At this point, she was certain that it wasn't a signal. It looks like we've got more aliens on our hands. It was unlikely that two of their tribes would be sending signals from different parts of the galaxy almost simultaneously. You might come across something unusual once, like an anomaly, but when you find it twice, you realize it's not an anomaly, but something completely new. We're still not sure what it is. One thing is for sure, though. We're looking at a new type of astronomical object. John Bell got a special award of $3 million for her key role in discovering pulsars and her inspiring leadership in the scientific community. Bell served as president of the Royal Astronomical Society from 2002 to 2004. Decades later, Bell is still a popular speaker at many international conferences around the world. As soon as Bell and Hill's paper was published on February 24, 1968, researchers around the world were eager to find out what was causing these mysterious pulsations. Neutron stars weren't a priority at the time, but they suspected white dwarfs. But scientists knew that the period of one of the sources, 0.25 seconds, was too short for white dwarfs. It's not possible to make white dwarfs spin that fast. Even so, white dwarf oscillations couldn't be ruled out. So in their paper, Observing a Rapidly Pulsating Source Radius, Joseph and his team suggested as a working hypothesis that the pulsations they saw could be the result of oscillations of either a white dwarf or a neutron star. The term pulsar was coined a few weeks later. Anthony Michael, the science correspondent for the Daily Telegraph, asked Hugh what he thought about naming these new stars, and they kept going, saying that they were pulsating. Maybe Pulsar would be a good fit? Hughes replied, "Yes, that's a good fit." Michael remembered this, and on March 5, 1968, he wrote in his paper that the name Pulsar, which means a pulsating star, was likely to be assigned to this new celestial object. But naming them doesn't solve the underlying issue. So, what exactly are these new pulsating stars? Neutron stars might have been good candidates, but at the time, no one thought they'd ever be discovered. Not only did the theory say that these stars should be tiny, about the size of an average-sized city, but they also shouldn't emit heat. That made them really hard to detect, at least in the optical or radio range. It wasn't that nobody was looking for pulsating radio wave sources. In 1955, Austrian astrophysicist Thomas Gold gave a talk at a meeting of the Royal Astronomical Society in London called On the Origin of Cosmic Radio Noise. In it, he discussed the possibility of the existence of such objects, but no one paid attention. And it wasn't long before Bell discovered this first scribble of hers, and it turned out to be a never-ending journey. It's coming out of the Lente recorder. Frank Kopsinia, an astrophysicist at Queen's University, submitted a paper to the journal Mir describing a model of a rotating and pulsating neutron star. This paper was published in November 1967, just as the Cambridge group was keeping their discoveries under wraps. He didn't think there'd be a narrow, directed stream of radiation coming out of a rapidly rotating neutron star with a magnetic field. He also suggested that this radiation could come from matter left behind after a supernova explosion around the neutron star. Zweig was the first to talk about something like this back in 1933. Bell's discovery, which came out a few months after the honors article, was a real game-changer. He also came up with an explanation for the new discovery that was separate from honors. It was based on his idea about what makes pulsating radio waves happen. He thought the strange pulsations were caused by the rotation of a neutron star. Gold says the regular pulsations are caused by the plasma matter in the magnetosphere, which he coined the term neutron star for, accelerating to a speed comparable to the speed of light. This is down to two things: the high rotational velocity and the strong magnetic field of the neutron star. However, as in 1953, the scientific community didn't approve of Gold's theoretical constructs. His report wasn't even accepted at the first scientific conference on pulsars, held in May 1968 in New York. The organizing committee decided to put a stop to the spread of all kinds of ridiculous theories by taking this approach. Gold quotes their response in his memoirs. "Your idea is so flawed that if we accept your report, there won't be any other equally outlandish ideas that we'll have to accept." The conference was held on May 21st and 22nd in the same week. Gold submitted his article, which was published on May 25th. It seems the editor had a better understanding of the situation than the conference organizers. As it turns out, astronomers had already discovered 2 new pulsars in the constellation Sales and the Prominent Nebula within 2 months. This was a great example of how a neutron star and a supernova explosion are connected. On top of that, nebulae can be seen when studying Crab pulsars. It became clear that the time between their pulsations was increasing, even if it was only a tiny amount each time. This suggests that the pulsar is slowing down. This also means that it is rotating. Before this discovery, it wasn't clear whether neutron stars were rotating or oscillating. If something, like a star like a white dwarf, is oscillating over time, the oscillations get faster and faster. Clearly, these new changing objects aren't white dwarfs. They're probably rotating neutron stars. It seems that the pulsar in the Crab Nebula is still the most well-known pulsar. It's bright and sparkling in its magnificent home. After Bell's discovery, astronomers around the world rushed to get their telescopes out, eager to make their mark in this exciting new field of radio astronomy. They were trying to find a new pulsar in the sky. For several decades, the radio telescope at Parkes Observatory in New South Wales, Australia, was one of the best tools for discovering pulsars. The telescope is also famous for picking up the signal from the live TV broadcast of the Apollo 11 moon landing on July 20th, 1969. Over half of the known pulsars were discovered with the help of Parkes and the radio telescope at the George Bank Observatory in northwest England. Parkes also made a big splash by discovering the first extragalactic pulsar, WASP-05b29, in a large cloud dwarf galaxy satellite of our Milky Way. A few years later, 4 more of these pulsars were found, 1 in the small cloud, 2 in the large cloud, and another one nearby. Once Parkes was kitted out with a cutting-edge multi-beam receiver, it could survey a much larger area of the sky. In 2001, astronomers made another 13 discoveries. Another big win for Parkes' multi-beam survey was the discovery of a double pulsar, J0737, 3030 plus 39, and its fractions have now been retired. This is the only system with 2 pulsars orbiting around a common center of mass. It's only a matter of time before they collide. Science magazine named the discovery of this pulsar as one of the top 10 scientific breakthroughs of 2004. But this isn't a dream, folks, James Court thought, looking at the screen in front of him as he was measuring pulsars that had taken 1,000 years to reach us. I'm going to show you something called a scenograph. A quick look at the screen showed a splash, just a quick splash, just a quick splash. There was a signal sort of like dodging up and down, a zigzag and a figurative line on the heart rate monitor screen. He saw a space beacon flashing in the distance. It was a rapidly spinning neutron star, immersed in a resolved medium. I got the gas and dust going. This is what's called the Misha stellar medium, which fills the space between all stars and neutrons. While we already have some understanding of the interstellar medium that surrounds stars, it is still a relatively new field of study. That was back in 1972. That's when Court first got to experience the rainforests of Puerto Rico. He took his gaze away from the stage manager and looked into the big one. Right in front of him, just a few dozen meters away, was the giant reflector dish for the observatory's telescope, the receiver. You can actually see events occurring in the interstellar medium. And, at a subconscious level, there's a kind of feeling. Then somehow it made me think of her. I just know it happened to me, he says, sitting in his office at Cornell University. This pulsar astronomer was so intrigued by the effects of the interstellar medium on signals and the pulsar's descent that he's been studying it ever since. Pulsars are super accurate clocks, even on a 10-year timescale. They're so reliable that they're being considered as a beacon for space travel. For instance, the extremely fast-spinning pulsars make hundreds of revolutions every second due to their high rotational speed and large mass. This makes them difficult to see, which means their periodic flashes are extremely accurate. Even after 1 billion years, they slow down by just a few milliseconds, so the sequence of pulses they send out stays the same forever. Pulsars are so unreliable that even the slightest change in their behavior can indicate a change in their environment. The interstellar medium in the vicinity of a neutron star. A lot of people think the stellar environment is a perfect vacuum. But it's not quite as simple as that. It's made up of moving charged electrons and protons at a rate of about 1 for every cubic centimeter. What's more, the interstellar medium is magnetic, and its pervasive magnetic field of varying strengths can be found everywhere in space. The magnetic field of the interstellar medium is on average a few microgauss, which is about 1/millionth the strength of the magnetic field at the Earth's surface. The magnetic field of a tomograph is around 10,000 times weaker than that of the Earth's surface. On the other end of the spectrum is the magnetic field of an average neutron star. It's about 10 to the 12th power of 1 trillion voices in strength. This field is so big that the atoms in it are stretched along magnetic lines of force, taking on the shape of cylinders. Pulsars give off radiation across a huge range of frequencies in the electromagnetic spectrum. High-frequency waves have very short wavelengths, so they're less likely to be scattered by plasma particles and can easily pass through the interstellar medium. Waves of lower frequency lag behind when they collide with electrons, so they reach the telescope later. This is what we call dispersion. The time it takes for waves of different frequencies to register differs depending on the number of electrons between the observer and the pulsar. The delay for several frequency waves can be about 1 second. If we're looking at a pulsar that's 1,000 light-years away, it'll take us 1,000 years to register its pulsations. So, a delay of 1 second might seem pretty insignificant. But when a scientist studies a pulsar, they have to take this effect into account to be able to account for all the emission frequencies coherently. By measuring dispersion, astronomers can work out how many electrons are in the interstellar medium between us and the pulsar, which helps them figure out how far away it is. The further away a pulsar is, the more electrons the radiation has to get through. This also means that the dispersion, or the difference in how long it takes for different frequencies to register, will be greater. It's not just a matter of counting electrons floating around in space. If we can grasp the properties of the interstellar medium, we can gain insights into how stars and galaxies are formed and evolve. If they observe a certain pulsar and see that the dispersion of its emission has changed in a year, it means that the electron content has changed in that region because there are regions of vented turbulence. Radio flicker also gives astronomers a chance to study how clumps of matter move between us and pulsars. Korth says that radio flicker can be measured. So then we have to ask ourselves, what kind of turbulence in the interstellar medium could be responsible for this effect? And we can even solve the inverse problem. In August 2012, the interstellar medium made the news for a brief moment. It happened when the Voyager 1 space probe, launched back in 1970, left the solar system and headed into the cold, silent space between the stars. On November 5, 2018, its twin probe, Voyager 2, joined it. The device, which John Sarkeesian still sees from time to time with the help of Parkes in case of an alien encounter, both probes contain a gold-plated record of audio and video information about our world. Voyager can't measure the properties of the interstellar medium on its own. The plasma detector is damaged, but a second spacecraft 5 years later came to the rescue. As it turns out, interstellar plasma is denser, colder, and moves slower than plasma inside the gel sphere region of space surrounding the Sun. The supernova had a neutron star at its center, and the scientists gave it the somewhat silly nickname, Cow. The supernova naming convention says the name has to include the year it was discovered, and a certain sequence of letters that have already been agreed upon. So the Cow is now officially called ETHI 2018. What is it? But the nickname stuck. On June 17, 2018, Ho, like hundreds of other astronomers, got a message from Stephen Smart, an astrophysicist at Queen's University in Belfast, and his colleagues. They were sharing their measurements of a strange transit. This is what astronomers call an event where a cosmic body releases a sudden burst of energy when it undergoes an unexpected change, like a supernova. The Atlas Automatic Observing System picked it up the day before. The Asteroid Earth Impact Emergency Warning System is based in Hawaii and is designed to detect small, near-Earth objects weeks or days before they collide with Earth. This transit was extremely bright, several dozen times brighter than the normal energy release of a star explosion. However, Ho noticed something else that seemed strange, so she went to her supervisor's office right away. What's interesting is that this supernova reached its maximum brightness in just a few hours, which is unusual. Typically, the increase in brightness can take several weeks. Telescopes and other instruments around the world turned to study this phenomenon in more detail. The others are the two twin Keck telescopes in Hawaii and the Liverpool telescope at the Roque Dallas Observatory on the island of Palma, which is part of Spain's Canary Islands. That's where the first confirmation was made. It seems that the outburst was caused by something happening in our galaxy, which is about 200 million light-years away. Scientists were able to witness the death of a star in real time for the first time by detecting this explosion. Of course, if you don't take into account the 200 million year delay it took for the light to reach our planet. If the measurements are done right, astronomers can see the explosion of a massive star, as well as the collapse of its core and the formation of a neutron star at that point. That's why Ho decided to move on from using conventional optical and radio telescopes and chose diamond as a better option for observing this supernova. To understand where Ho started from, we have to go back 88 years. So we're on a steamship coming from the Indian port of Bombay to England. The journey on the steamer took about 2 weeks. It was 1930, and Yang Chen was heading to Cambridge to become a graduate student in the physics department. To make the time go by more quickly, he kept himself busy by doing some math. The Indian prodigy and Sir Chandra Wang's nephew from the novel is the first Asian to win the Nobel Prize in Physics in the same year, 1930. Roman Yang got his bachelor's in physics at 19. Half a century later, in 1983, Chandrasekhar himself would win the Nobel Prize for the work he had been doing at Steamboat. Just before he left for England, Chandra became really interested in white dwarfs, which are very dim remnants of stars. At the time, it was thought that when the hydrogen fuel that supports thermonuclear combustion runs out, all stars, including our own sun, turn into white dwarfs. As it turns out, not all stars die this way. Only those that gradually shed their outer layers over time do so. What's left is a dense core of carbon, oxygen, and nitrogen. It's thought that after about 100 billion years, the white dwarf will cool down completely and stop emitting light and heat. It'll turn into a black dwarf without a functioning black dwarf. By the time of Chandra and Icarus, astronomers had only discovered 3 white dwarfs. Among them was Sirius, a dim and dead counterpart to the bright star Sirius. It was already known that white dwarfs are incredibly dense, more than 1,000,000 times denser than the Sun. Quantum mechanics, which was just emerging at the beginning of the 20th century, could explain how such incredible densities could be achieved. As a star dies, the gravitational pressure inside it squeezes the atoms in its core so tightly that it rips electrons off them. This means that the forming white dwarf is made up of positively charged ions floating in a sea of electrons. As the gravitational compression continues, quantum mechanics comes into play. One of its laws is the forbidden principle. Pauli said that no 2 Fermi ions, like 2 protons or 2 electrons, can be in the same state at the same time. It's similar to the game of hot seats. Two people can't sit in the same chair at the same time. This means that inside the white dwarf, some of the electrons must move from the ground state, which is the lowest energy state, to a higher energy state. This process creates what's called forced electron pressure. It's this pressure that keeps the gravitational force in balance and prevents the white dwarf from collapsing. Chandra Icarus knew all this, in part because he had carefully studied the internal structure of stars, written in 1926 by Arthur Stanley Ellington, one of the best astrophysicists of the time. The term white dwarfs was actually first used by the Dutch-American astronomer Willem Clayton. But it was his book that really put them on the map. However, Ellington incorrectly attributed the enormous density of these dying stars, thinking that it was due to thermally induced thermal pressure inside white dwarfs. Later that year, the right quantum mechanical explanation was put forward by English physicist Ralph Howard Fowler in a paper on dense matter published in the monthly notices of the Royal Astronomical Society. Chandra Icarus also took a close look at this article. He was heading to England to work with Fuller and decided to continue his calculations on his own. The trip was a long one, and the young scientist had plenty of time to look over Fuller's equation. Chandra made another adjustment to account for relativistic effects, which is necessary when an object is moving at a speed close to the speed of light. He realized that the electrons inside the white dwarf were moving at incredible speeds, which led to some surprising results. It turns out that for a star to become a white dwarf, the mass of its core at the time of its demise has to be less than 4 solar masses. The Chandra-Icarus calculation showed that if this limit is exceeded, a white dwarf can't exist because the extra mass of incredibly dense matter inside the star can't resist gravitational compression. Put another way, no star that ends up being 4 times more massive than the Sun by the end of its life will end up being one of these discovered stars. These are faint, super-dense celestial objects. This was later calculated. The upper limit for the mass of a dying star is now known as the Chandra-Icarus limit. But then it raises the question of what happens to all the more massive stars at that time. That was something that scientists didn't know at the time. When Chandrasekhar published his work in 1935, the neutron hadn't been discovered yet. It wasn't until the following year that it was proven to exist. The young Indian scientist couldn't have known what would happen to more massive stars as they died. He didn't know that neutron stars could form, so he figured that maybe, in the absence of gravitational pressure, a massive star just shrinks and becomes nothing, fading into nothingness. It's now thought that the result of the collapse of very massive stars is black holes. But at the time, black holes were only theoretical and remained mathematical objects for several more decades. The Chandra sector ended up being the first to discover both neutron stars and M1 black holes. Who was there to challenge Chandrasekhar's idea? In 1930, after publishing the initial findings, the young scientist sent 2 more articles to the Royal Astronomical Society. These articles further explained his earlier calculations and conclusions. In January 1935, Chandra and Kara were asked to give a paper on the subject at a meeting of the Royal Astronomical Society of Deutschland. Ellington listened to Chandra's presentation from Icarus and then took the floor himself, going over all the details of his work. Chandra's Icarus formula is based on combining relativistic mechanics with non-relativistic quantum theory. Such a union seems wrong to me, and the result is illegal, Ellington told a shocked Chandrasekhar. Ellington was convinced that every star eventually turns into a white dwarf. He found the idea of collapse into nothingness under gravity hard to accept. This nothingness later became known as a black hole. Eisenstein said he believed there had to be a general law of nature that would stop a star from behaving in such an absurd way. Chandra-Icarus was so taken aback that he spent the next 4 10-year periods no longer studying white dwarfs. At the time, he was influenced by Ellington's authority. Most scientists agreed with him. Even so, Chandra Branch and Princeton managed to stay on good terms, despite the controversy. 3 years before Chandra-Icarus spoke to physicists, he encouraged them to stop criticizing Ellington and try to understand his calculations and hypothesis. Meanwhile, on the other side of the Atlantic, another scientific debate was underway. In early 1932, Fritz Zwicky of the California Institute of Technology found out that James Chadwick had discovered the neutron. The news had a huge impact. Most of the world's major newspapers covered the story, as the discovery completely changed the model of the atom. The New York Times headline read, "Rutherford discovers the neutron embryo of matter, February 20th, 1923. The article started with a discussion of the ethical implications. Dr. James Chambers, who was working at the Cavendish Laboratory in Cambridge at the time, made an important discovery. He found a new particle, which he called the neutron. We're pleased to announce a discovery that came to light today. Our scientists say this is the most important thing to happen in experimental physics, since Lord Rutherford showed us what an atom looks like in 1911. For Zwicky, this discovery was the icing on the cake. Astronomers were already familiar with the phenomenon of new stars suddenly beginning to shine unusually brightly. They'd already observed a much rarer type of new, brighter, and strangely looking nebulae blossom, which they called supernovae. Fritz Zwicky and his colleague Walter Beards had already thought that supernovae might be the result of really powerful explosions of stars. Now that he had a neutron in his arsenal, he was able to tie up loose ends. What if, he thought in 1933, at the end of a star's life, the star's core collapses under the force of gravity, and the star's interior is revealed to consist only of neutrons. As protons capture electrons and turn into neutrons, this makes the neutron star significantly smaller and reduces the original mass of the nucleus. Based on Einstein's famous mass-energy equivalence equation E equals n, Zwicky square suggested that the mass lost in the collapse of the nucleus is converted into energy, leading to an explosion. And then it explodes as a supernova. In one of two papers on the subject, Zwicky and Bada wrote with all the usual caveats. We still believe that supernovae represent the transformation of an ordinary star into a neutron star composed mainly of neutrons. Such a star may have a very small radius and be extremely dense. In December 1933, 2 years before Chandra Kar presented a study of white dwarfs, Zwicky and Baldy reported their findings at the American Physical Society meeting at Stanford. As it turns out, the physics conclusions were right on the money. But since the papers didn't have much in the way of supporting calculations, at the time they seemed like just a bunch of guesses. When Zwicky and I published a paper on supernovae and neutron stars in January 1934, it didn't get much attention. For years, other scientists rejected the idea of neutron stars, considering it purely speculative. But everyone quickly agreed with Zwicky that a supernova is a catastrophic event that ends the life of a massive star. This was a more significant discovery than the slow, steady death of less massive stars, which are known to turn into white dwarfs. It's also worth noting that supernovae have been known to scientists for a long time. They've been observed and described for centuries. In 185 AD, Chinese astronomers were surprised to notice a new star in the sky that was brighter than all its neighbors. It disappeared after 8 months. They made careful notes of what they saw and gave it a romantic name. Star. Guests, please. Today it's thought that this was probably the outburst of supernova N185 towards Alpha Centauri, somewhere near the border between the Circulus and Centauri constellations. Over the next few decades, astronomers in the Arab world, China, Egypt, Japan, Italy, and Switzerland also observed similar visitors at various times. These unusual stars were in the same place as all the other fixed stars, and they couldn't be confused with any other celestial event. They were like a comet moving across the sky. In 1054, the guest star was visible for 23 days during the day and 653 days at night. It was so bright that at its brightest, it was thought to be 4 times as bright as Venus, which is easily seen with the naked eye. Eventually, it was given the modern name supernova H1054 in the constellation Taurus. It's famous because its remnant is a bright light crab, a prominent nebula that looks like a large cosmic cloud. However, the ancient astronomers had no idea why these stars appeared and disappeared. This went on until the Danish astronomer Tycho Brahe discovered a new star in the constellation of the Spear on November 11, 1572. This star was as bright as Jupiter. He was certain that no star had ever been seen in this part of the sky before. At least Brahe demonstrated that the sky is not static. A few decades later, in 1604, Johannes Kepler discovered another new star and came to the same conclusion. It was becoming clear that the sky wasn't a solid sphere or a piece of velvet with sparkling sequins. But it wasn't until 300 years later that Blossoms and Bads realized that the light of the guest star came from an explosion of incredible power, which alerted them to the death of a massive star. However, the theory of blooms in the part relating to neutral stars wasn't accepted as fact until 1930. In 1937, Soviet physicist Lev Landau wrote a paper suggesting that all stars, including our Sun, have a neutron core. In the nucleus, matter is in a state where all the nuclei and electrons have combined to become neutrons. In this state, matter can withstand much stronger gravitational compression, which prevents the nucleus from collapsing. At first, not many people paid attention to Landau's work because it was written in Russian and published only in the journal Reports of the USSR Academy of Sciences. On top of that, Landau was also facing arrest. The well-known Soviet physicist Pyotr Kapitsa helped spread the word about Landau's work by sharing this article with Niels Bohr, a scientist from Copenhagen who won the 1972 Nobel Prize for his research on the structure of atoms. The paper made such an impression on Bohr that he sent it to a journal where it was published. February 19, 1938. His confession didn't help avoid arrest. In April 1938, Landau was accused of anti-Soviet activities, arrested, and sent to Butyrka, a notorious prison for political prisoners. Landau spent a year in Butyrka, but was released thanks to a letter from Niels Bohr to Stalin and Kapitsa's intervention. I studied under Landau. Landau's paper was published just a few months before the German-American nuclear physicist Hans Bethe first correctly described the thermonuclear reaction, which is how energy is generated in stars. He went on to win the Nobel Prize for this work. It's ironic that Landau's idea about neutron star cores was flawed, but it got scientists talking again about whether neutron stars exist. One of the people who read Landau's paper was American physicist Robert Oppenheimer. He decided to look into whether massive stars' nuclei could survive after they died. He worked with his master's student George Volkoff, who was an immigrant from Russia and had graduated from the University of Vancouver. He started working out the upper limit for how much mass a neutron star can have before it can't resist being compressed by gravity. Oppenheimer was actually trying to solve the same problem that Chandra Icarus had solved for white dwarfs to determine the upper limit on the mass of a neutron star during 1938 and 1939. Oppenheimer, Volkoff, and American physicist Richard Chase Tolkien published 3 key papers on neutron stars. They explained how they form, what their maximum mass could be, and what happens if this limit is exceeded. Based on their calculations, they determined that the upper mass limit for a neutron star is 7 solar masses. They explained that a neutron star is born when a massive star collapses at the end of its life. As long as the short-range repulsion between neutrons balances its mass, it'll stay stable. But if the mass of the neutron star gets too big, for example, if the matter left over from a supernova explosion falls back onto the neutron core, the neutron star keeps collapsing and eventually becomes a black hole. Oppenheimer and his colleagues thought it was impossible to detect both neutron stars and black holes because they were too small. X-ray astronomy hadn't been developed yet. The upper limit on the mass of a neutron star is still called the Oppenheimer-Volkoff limit. However, their calculation of the mass value was significantly underestimated because they didn't take into account the strong nuclear interactions holding protons and neutrons in the nucleus of the atom. By 1990, when the equipment was better and more accurate, it turned out that this limit fell between 1, 5, and 3 solar masses. And finally, after a lot of hard work, the team observed the first merger of neutron stars. The Volkoff limit for neutron star thickness was revised to a value of about 217 solar masses, The most massive neutron star discovered to date is called J0740 plus 6620. As of September 2002, the heaviest neutron star, PSR J0952 plus 6030, has a mass of 305 solar masses. It's a rapidly rotating pulsar in a double system with a white dwarf. This star has a mass of 214 solar masses. Oppenheimer and his graduate student were working on this at a tense time before World War II when the war broke out. Many physicists had more urgent matters to attend to. Oppenheimer got involved and helped run the Manhattan Project, which aimed to build an atomic bomb faster than the Nazis. Neutron stars were overlooked for more than 20 years until Saline discovered the first pulsar in 1967. After this breakthrough, physicists quickly realized that detecting neutron stars could still be within reach. The accidental discovery caused quite a stir in the astronomical community. But Fritz, who first suggested that neutron stars might exist and that they could be linked to the death of a massive star, wasn't at all interested in the subject. Radio astronaut Ronald has this to say about that time. He's now a staff member at Aero Radars in Australia, but at the time he was working with Iris at the California Institute of Technology. I met Chris at CERN Aero's main office, which is about 20 minutes from downtown Sydney. Vicky's office was on the lower level of the same building as mine. Vicky remembers it this way. I got on well with him and we often had a chat. From what I know, he never took part in discussions about neutron star coupling to Skoltech pulsars. There was a lot of talk about it at the time, but for some reason he didn't get involved in those conversations. By then, Flowers had moved on to other projects. He was one of those rare physicists who took on problems from different areas of physics during his career. Wiki also made a big impact on the theory of neutron stars. He also suggested that the universe might be missing a lot of matter. In 1968, just as Bell and Anthony Hughes published their paper on N1 pulsars, scientists started discussing how rapidly rotating neutron stars could be the source of these mysterious pulsations. Vicky was more focused on finishing a catalog of galaxies and galaxy clusters based on observations made at the Holloway Marine Observatory. This catalog, published by the California Institute of Technology, is made up of 6 volumes and includes carefully verified data on 418 galaxies and 134 galaxy clusters. X says Vicky wasn't interested in neutron stars at the time because they weren't just theoretical anymore. There's an opportunity here. Now, scientists were modeling these newly discovered objects by candlelight, as X put it. It was more about how to generate great ideas based on intuition, using gestures to guide the process. So when it came to detailed analysis, he no longer saw neutron stars as something he was interested in. Despite this, the discovery of neutron stars never really piqued the Swiss eccentric's interest. The new topic was quickly picked up by other astronomers. Astronomers turned their telescopes toward pulsars, trying to keep an eye on neutron stars and the associated nebulae. According to the theory, these nebulae were the remnants of massive stars. One of the telescopes used for this purpose is the one belonging to the Allen Radio Observatory. It's about an hour's drive from Australia's capital, Canberra, and about 4 hours from Parkes. It's a cross-shaped radio telescope with a small, unusual design. It has 2 perpendicular arms, each a mile long. This type of antenna is called a cross. The telescope's shoulders are shaped like cylinders that have been untied and folded in half. Drum. This is the cross-sectional shape of the antenna. It's used to focus the signal. You can rotate one of the cylindrical parabolas about its long axis by moving the antenna up or down. The telescope was fully operational in 1967, just as the first pulsar, NM1, made its spectacular debut. Not much. It was designed to observe radio emission sources, so you could tell it was looking for pulsars because its cylinder diameter is relatively small, in comparison to the larger single ones. The reflector allows this telescope to scan a wider area of the sky more quickly, which helps it to find pulsars more easily. It started collecting pulsars right away, and in such numbers that in the first 2 decades of astronomy, More than half of all pulsars and supernova remnants were detected by this observatory. On Friday, October 4th, 1968, the radio telescope confirmed that Wiki was right once again. As it turned out, the number of pulses from this neutron star was about 11 per second, compared to the periodicity of 6 other pulsars that were already known at the time. 2 were spotted by the Longo telescope, while Bell's remaining 4 were about 1 second apart. About 10 years later, in 1970, astronomers using an Anglo-Australian telescope at Siding Spring Observatory also observed a pulsar for the first time in the optical range. On the very same day the paper on the pulsation of the shaft arrived, 2 astronomers, David Stern and Edward Stein, were working in the U.S. at the Green Bank Radio Telescope, about 2 hours from Charlotte, when they spotted a crab in a nebula. The crab's unusual pulses are visible in the nebula that remains from another supernova explosion in the constellation Taurus. As I said earlier, Chinese astronomers observed this bright supernova in 1054. In 1850, astronomer William Parsons spent many nights at his 36-inch telescope and drew the nebula that was left behind. His drawing looked like a crab, so the nebula became known as the Crab Nebula. Here's a view of the situation. Just a month after Stephen and Riefenstahl's discovery, which was made with the Green Bank telescope, Cornell University graduate students Richard Lovelace made another discovery. He found that the radio signal coming from the Crab Nebula came at regular intervals of every 33 milliseconds. He was working on the radio telescope at the SIB Observatory in Bolshoi. The reflector is set into a natural sinkhole. Later on, this radio telescope gained notoriety thanks to the TV series Contact. The Zari telescope in New Mexico was still being used to film the movie, as well as 17 Bond films, including GoldenEye. The Green Bank and SIBA telescopes backed up what astronomer Frank Honor had said a few months earlier in a paper he wrote about the Crab Nebula. He said there had to be a pulsar inside it. So now there were 2 pulsars shining brightly among the supernova remnants. Everything came together. So all of Fritz Wicky's intuitive predictions from 1933 were confirmed. Neutron stars, superdense, tiny, rapidly rotating, and strongly magnetic, became a tangible reality. It's pretty rare for a supernova to occur in a galaxy like our own Milky Way. It happens about twice every 100 years, on average. Our galaxy, which has about 300 billion stars, is already behind schedule. The youngest supernova we know of exploded at the center of the Milky Way around 1870, but it was never visible. It was obscured by cosmic dust. Now, astronomers can see the remnant of that supernova as a bright source of radio and X-ray radiation from the visible universe of at least 2 trillion galaxies. That means that every second, somewhere in the vast expanse of space, 10 stars go supernova. It's hard to predict where and when a supernova might appear, so it's challenging to track them. Astronomers are using robotic telescopes to survey the entire sky, monitoring all flares across different wavelength ranges. Computer algorithms check the data and flag any promising supernova candidates. Then, astronomers try to get on powerful telescopes right away to study the electromagnetic spectrum of the flare and other astrophysical details. We're looking for footprints. Matteo, a concierge astrophysicist at Princeton University, calls this kind of analysis stellar forensics. We know the star died, and now we want to find out exactly why and how it happened. If we can observe the last hours of a star's life, we'll get some really valuable insights into supernovae. In particular, can we tell if a dying star is about to explode, and if so, how far in advance? On February 23, 1987, astronomers got a rare chance to see a new one in action from above at Las Campañas Observatory in Chile. The night shift had just started work. Back then, the way we worked here was pretty old-fashioned. Scientists were right there with the telescope, not hundreds of miles away in a comfortable office with high-speed internet. Ian, Shelton, and Oscar, who was on duty, took a quick look. Out of the blue, Shelton spotted a flash of light in the dwarf galaxy, the Large Magellanic Cloud. On a cosmic scale, this is not far from our own Milky Way, about 168,000 light-years away from Earth. The flash was so bright that it could be seen with the naked eye. Shelton quickly made a note of what he'd seen. He later found out that another astronomer from New Zealand had also spotted the flash. The scientists checked the catalog and found that there used to be a massive star at the site of the flare that had suddenly vanished. The blue giant Sandu Leak is at 69 degrees 202. Normally, it's located on the outskirts of the Terran Nebula, in the Big Grave New Cloud. It exploded as a Type II supernova with a collapsed core that later became known as NGC 1087. It's the closest supernova predecessor star to Earth that could be observed for over 400 years. At 3 a.m., astronomers in Chile and New Zealand noticed the flash in the optical range. 3 neutrino detectors, 2 in Japan and 1 in Ohio on the shores of Lake Erie, recorded about 24 neutrinos at the Baksan Neutron Observatory in Russia. This is a lot more than any of these 3 observatories have ever picked up before. Before this, the idea that neutrinos could cause supernovas was just a theory. Now, though, it's been proven. However, it's much harder to prove that neutrinos are what provide the energy for a supernova explosion. Scientists have tried doing 3-dimensional computer simulations of the neutrino mechanism near the peaking core of a star, but these are very expensive and time-consuming. A single computational experiment can take several months, and observations don't really help us understand how a supernova explosion works. The thing is, says Stephen Smart of Queen's University in Belfast, what can you actually see? That's when we can see the shock wave passing through the surface of the precursor star. The glow we see is determined by the radius of the star and the amount of material around it. These characteristics don't help us understand the explosion mechanism. To answer this question, we need to measure the kinetic energy of the material that's been ejected, understand how it's moving, and compare that to the energy of the shock wave and the exploding star. That's what Smart says. But that's also a tough theoretical challenge. And it's basically impossible to examine the center of the explosion directly. For over 35 years, scientists have been studying the evolution of CN19 Way. They've been able to observe the transition from a non-bulge stage to a supernova remnant in real time. The big mystery is the missing neutron star, which should be about 20 times the mass of the precursor star. The theory is that it should be at the center of the supernova remnant. The observations were clear. A compact object had formed in the place of the original star's core. But so far, astronomers haven't found anything. One possible reason is that there's just too much debris in the way to see the core. It's hidden behind a lot of dust and gas. Or maybe the magnetic field of the neutron star, if it exists, is either too strong or too weak to be viable. The formation of a regular pulsar. Then again, maybe too much ejected matter fell on the young neutron star. It gained so much mass that it reached a point of no return, which caused it to collapse further into a black hole. Despite observing the supernova almost immediately after it happened, and knowing which star was its predecessor, scientists couldn't detect any signals that the blue giant was about to die. It seems that at least some stars will give us a heads up before they die. Astronomers discovered such a star in 2013. Normally, a new interesting object is found, so a robotic telescope scans the night sky. Astronomers on duty then take the incoming data and select for further study those objects that seem most interesting and suitable candidates for supernovae. This is how experts try to spot a cosmic event as quickly as possible and start observing it. When dawn made its appearance with a spectacular fireworks display, the red giant star met its end. The sky in Northern California was surveyed using the Duty Survey Robot Telescope Palomar Transit Factor, and just after 3 a.m. the supernova flare reached Earth, and it was noticed by observers in Israel. The star was in a nearby galaxy that, it turns out, had been overlooked. The night before, as it happened, one of the group had already booked time at the Keck Telescope in Hawaii for other observations that night. Officer Yerlan of the Weizmann Institute in Israel brought up Jerry, an astrophysicist from the California Institute of Technology who had experience with Burnley. He immediately asked the telescope operator in Hawaii to point the telescope at the flare and got in line to work on the Swift orbiting telescope to get data in the X-ray and ultraviolet bands. Perry was able to get a sequence of 4 spectra using the left bugle spectrum. The idea is that the telescope collects light and directs it into a spectroscope, where it passes through a narrow slit. This lets us collect as much light as possible from the object we're looking at, while leaving nearby sources of light out of the picture. These are the earliest spectra ever obtained right after the supernova explosion, he says. Up until now, astronomers thought it was impossible to predict whether a star would explode in the next 10,000 years. Ron's group has found that we might be able to spot signs that a giant star is about to die in the next few years, maybe even a few months before a supernova explosion. This could mean that the star is erupting matter more and more quickly. This is similar to the tremors caused by rapidly rising magma, which are the warning signs of an eruption in some volcanoes. By analyzing the spectrum of the supernova, which is called N2013FS, Erlin and his colleagues found a dense gas shell of what is called near-stellar material around the dying star. So, was this gas there hundreds of years before the explosion? Or is it an early precursor to the explosion, in the supernova core collapse model? It's thought that before the final explosion, it's not possible to tell whether the inner collapse of a star's core is already taking place at a high intensity, the outer layer of the star. The star's intermediate layers stay eerily quiet until the end, when the matter in its core collapses at its center in a matter of seconds. This causes the intermediate layers to explode and rush towards the center of the star. But even before Nero, other scientists were saying that perhaps dying stars lose their outer layers of gas before the supernova explosion occurs. In one study, scientists looked at images from a robotic survey of 16 supernovae. They discovered that small flares actually occurred before the supernova in 5 of the cases they looked at. Nero's paper shows that in the final moments of the life of the supernova precursor star his group was studying, gas erupted several times, resulting in a much greater loss of mass than at any time in previous years. Just 5 days after the explosion, the gas disappeared as the shock wave from the supernova explosion moved through the area. Not everyone is on board with these findings. Other astronomers believe that since there is a lot of gas around red giants throughout their lives, the material may have been there for a very long time, right near the star. Norbert Lang, an astronomer at the University of Bonn in Germany, suggests that the cloud near this star may have existed for 1 million years. For instance, consider Giza's red giant in Orion, which is relatively close to Earth at around 600 light-years. It's clear that it's surrounded by gas, probably there for 1,000 years or more. To figure out who's right, we need to measure how fast the gas is being carried away from the explosion of the existing star. If it's moving quickly, it's probably a gas explosion. It might be. In the case of N2013G, we've only been able to determine an upper speed limit, but Joran thinks there are clear signs that the gas was moving much faster. The stellar wind speeds are typical of a red giant. So is it likely that the outer shell is aware that the star is about to explode? Stars are so big and dense that it takes 1,000 years for information about the core to reach the surface. However, the information doesn't have to be carried by photons trying to get through the thickness of the star. Information can be carried by shock waves, and they have enough energy to form big gas bubbles on the surface. In 2017, Jim Fuller, an astrophysicist from the California Institute of Technology, published a paper where he suggested that information about what is happening inside a star can be carried to the surface by sound waves. He likened this process to that of a boiling kettle. If the boiling is intense, you can even hear it because the process excites sound waves in the air. We can assume that just before the supernova explosion, the core of the star boils, which causes sound waves of great energy and can lead to powerful ejections from the surface. Just before the explosion, Joran and Fuller believe that warning signals can be noticed before the supernova explosion. Anna Ho looked at not just the cow, but also CN 2018 and Pi. Type 1 supernovae were detected by the Sound Transit Basel C observing system. Ho's team started taking observations just a few days after the explosion, as soon as radiation from it reached Earth. They got 9 spectra, which were the earliest spectra for a supernova of that type. Ho and her colleagues observed supernovae that resulted from the collapse of a massive star's core, which had lost its outer hydrogen shell before the explosion. This was in contrast to Nero's group, However, host analysis like NERO's data showed that the star was giving signs of an imminent explosion. This was the first reliable observation of outbursts for Type 1 supernovae. This suggests that such warning signals could be a common phenomenon for different types of massive stars, not just those that explode as Type 2 supernova. The data Ho and Ron gathered gives us some insight into what the progenitor star was made of right before it died. But it doesn't tell us much about how the supernova actually happened. The majority of the energy released during collapse is contributed by the neutrino core. But we had to see if we could transfer enough of that gas energy to the substance of the star and its outer envelope to get the supernova explosion going and take a look inside. About 200 days after the explosion, astronomers are studying the resulting nebula. They're also keeping an eye on the supernova remnant that formed 10 years later, when the ejected gas cloud moved from the explosion site into outer space, where it's relatively easy to observe. The explosion essentially turns the original star inside out. It's in these remnants of stars that scientists find the heavy elements that make planets, other stars, and eventually life. By looking at spectra at later stages of supernova evolution, astronomers can figure out the mass and relative amounts of each chemical element that was formed and ejected during the explosion. They can also figure out the total mass of the star that exploded and what it was made of. Data on the precursor signals are really valuable, but it's now crucial to use such analysis techniques more often. When we're looking at a lot of other supernovae, to do this, we need to look at spectra from the early stages of evolution, before the cloud of gas ejected in the explosion covers the disk around the star. If we don't get the data on how the star died, we'll lose all the information we need about what happened. That's where the supernovae from 2018 hours come in. As an unofficial measure, using a cow could be helpful. Supernovae are usually observed in the earlier frequency range, moving away from where the star exploded. The material carries energy in the form of waves that are very short and very long, but as time goes on, the waves get longer and longer. This is why astronomers rarely use millimeter telescopes to study cosmic explosions. After all, to see its distinctive features in the range of millimeter wavelengths, you have to do it very quickly. That means that when we look at the explosion, we're seeing traces that have shifted to the region of radio and centimeter wavelengths, according to Echo. What made the cow so strange and unusual was that its spectra in the optical range didn't resemble supernovae at all, Echo says. If we want to know for sure if it was a star explosion, we need to look at other evidence. The CW team got to study the gas and dust in the area of the explosion. It turned out that the environment there has characteristics that are similar to the effects of such an explosion. In particular, there's a lot of gas and dust in the area. That's the kind of density you'd expect near a dying star when it's losing matter rapidly. But that's what experts think happens to massive stars. It's likely that the explosion happened before the star died. In fact, it probably erupted and shed stars before that. The material was preserved for months. The emission of ultra-short wavelengths also indicates that this is not a single release of energy. It seems that the explosion was actually a continuous process of energy production, similar to the operation of a central engine correcting matter at a rapid pace. This could be likened to a neutron star or a newly formed black hole. It wasn't just the CW team members who thought they'd seen the birth of a neutron star. Another group led by Raphael and Guti, an astrophysicist at Northwestern University in the US, came to the same conclusion. Margulis' team looked at the X-ray emission of the cow using the Star Nuclear Spectroscopy Telescope, NASA's Space Observatory System, and the European Space Agency's Integral Instruments. They also looked at radio wave spectra captured by telescopes from the U.S. National Radio Astronomy Observatory in New Mexico. From this, they figured that the transit is getting warmer from the inside, so it must be getting energy from inside. However, to confirm whether there really is a neutron star inside the cow, astronomers will have to wait years for the remnants of the gas and dust around its center to dissipate into interstellar space. We can observe stars and explosions on their own, and we can also see neutron stars separately. But it's really difficult to connect these different stages of evolution together, Hall says. So if we can see a neutron star left over from the cow, it means this is one of the few cases where we can actually see the explosion that produced the neutron star. It would be really interesting if we actually saw the birth of a neutron star. If this is confirmed, we can learn more about how neutron stars form by doing further observation. Right now we can study neutron stars because we can see them in our own galaxy. We believe that stars of a certain mass explode. But what was the star that then became a neutron star? How did it evolve? What happened to it during its existence? What was the end of the road for it? Did it lose mass? And if so, did it happen gradually or rapidly? Given what we know about the explosion, we have no idea what happened next. So if there's a neutron star inside a cow, it's like a zombie. Stars can tell us a lot about other stars that are still alive. In the past 50 years, astronomers have detected about 3,000 radio pulsars in our galaxy and observed several dozen supernova remnants. But we still can't say for sure whether a star is dying or if we're seeing the birth of a supernova. For instance, we know that all stars are in motion, revolving around the centers of their respective galaxies. As a rule of thumb, this motion happens at a speed between 6 and 100 kilometers per second. But we don't know why a newborn neutron star is often ejected from the site of a supernova explosion at speeds of up to 500 kilometers per second, moving in the opposite direction to its original motion. What's more, the speed of this projectile is much faster than the speed of the original star. Scientists refer to it as a pulsar kick. Hans Thomas Young, an astronomer at the Institute for Astrophysics of the Max Planck Society in Germany, thinks that Kiki is probably down to the fact that the supernova explosion wasn't perfectly spherical and symmetrical. Such an asymmetric explosion is similar to the way smoke rises calmly from a cigarette with swirls and currents suddenly appearing. In March 2015, the Fermi Gamma Ray Space Telescope helped astronomers track down a pulsar called J00226, which is about 6,500 light-years away. This pulsar was ejected by the explosion of the star that spawned it and is currently moving through space at about 4 million kilometers per hour. It's moving at almost twice the speed of other pulsars, and it's leaving a trail of light 13 light-years long. If a spaceship were to travel to the moon at that speed, it would get there in just 6 minutes. The other thing we need to think about is whether it would have been able to brake in time. If we can get to grips with the asymmetry of the supernova explosion, it'll not only help us determine the direction and power of the Kiko, but also shed light on a much bigger mystery. What is the actual mechanism that provides energy for the supernova explosion? The most popular theory is that it's the neutrino mechanism. The collapse of the nucleus produces a huge number of neutrinos, which then burst out of it in an asymmetric stream. Computer modeling of these explosions should help us understand not only neutron stars, but also the many observations indicating a strong asymmetry in the distribution of gas ejected in a supernova explosion, Yang says. Three-dimensional computer models of supernovae, like the one that accurately reproduces the shape of the 400-year-old supernova remnant, A, align with the observed pulsar peaks. This is a big win for both cosmological theorists and astronomers. Based on current models of supernovae, the neutron star at Kiki gains speeds of a few hundred to 1,000 kilometers per second, and possibly more, according to Janka. This is in line with what we've seen with young neutron stars. These models also explain where iron and radioactive titanium are distributed around the supernova. This was recently verified by the NJ-100 satellite, which observes X-rays in space. It also observes neutron stars. The neutron star is due to the asymmetry of the supernova explosion. It seems that the rotation of pulsars is mainly determined by the rotation of the progenitor star. This is because angular momentum is conserved during the core collapse, which leads to the formation of a neutron star. So, if these assumptions are right, different processes are responsible for how fast it rotates and how fast it moves through space. To figure out how fast a pulsar is moving through space, you need to know how far away it is, which isn't always easy to determine. If we know the distance to a pulsar, we can only measure its speed in relation to the plane of our sky. But we can't measure the radial component of the velocity toward or away from us. To make these measurements, They compare what they see of a pulsar moving in space or measure how wide its beams are. However, some pulsars, such as the pulsar in the visible nebula and pulsar, don't leave their home nebula. Yanko says that not all neutron stars have velocities high enough for Kiko. I think it probably depends on the energy of the explosion, and thus the initial mass of the parent star. The theory suggests that the greater the mass of the progenitor star, the more powerful the explosion, and therefore the more powerful the Kiko. The velocity of a significant number of neutron stars is less than 200 kilometers per second. The theory of stellar evolution also suggests there might be different groups of slow neutron stars moving at just a few tens of kilometers per second. This could be why there are so many neutron stars in globular clusters, which are large, spherical groups of connected stars. If a star wants to leave the cluster, it has to be moving at less than 30 to 50 kilometers per second. This means that the speed of neutron stars in clusters must be low from the moment they're born. There's another reason why some stars leave the nebula left behind after a supernova explosion, while others don't. It's believed that this is linked to the age of the supernova remnant. Janka says that initially, the gas that makes up the remnant expands into near-stellar space at a rate of a few thousand kilometers per second, which is 10 times the average speed of a neutron star. It takes about 10,000 years for the supernova explosion to eject the surrounding gas and dust. The remaining gas slows down, but doesn't stop. Neutron stars that keep moving at the same speed will eventually leave their gaseous remnants, maybe 1,000 years after the supernova explosion. When this happens depends on how fast the neutron star is moving and how dense the interstellar medium is that the gas from the supernova explosion is interacting with, Janko said. Stars die in different ways depending on their mass. Some stars die quietly, while others explode. Stars with a mass of less than about 8 times that of our Sun live for about 1 billion years. These stars then shed their outer layers to form planetary nebulae, while their cores shrink and become white dwarfs, a compact remnant of a star that's stuck in space forever. But red and blue supergiants, which are more massive stars with masses ranging from 8 to 100 solar masses, have a different fate in store. When a star dies, it's mainly made of iron, and the nuclei of these stars reach a certain limit of about 4 solar masses at the moment of death. It's possible that the number is actually somewhere between 1, 3, and 2 solar masses. They have enough nuclear fuel to keep the combustion process going for about 1 million years, with matter being expelled into interstellar space. As the nucleus collapses, it slows down the release of heat from the nuclear reaction, which is what turns lighter elements into heavier ones. This creates all the known elements from carbon and oxygen to iron, which burn up in the star one after the other. These elements are trapped inside the star for a while they're also formed with almost no mass neutrino particle. As the star nears the end of its life, the rate of nuclear fusion and heavy element production accelerates significantly. This is due to the temperature and pressure reaching a dangerous level. A star like this can burn hydrogen for millions of years, and it takes about 1 million years to burn through all the helium. After that, the star starts burning carbon in a nuclear reaction, which lasts for about 1 million years. Next, the remaining oxygen is burned in a process that lasts only a few weeks. The same thing will happen to the heavier elements. After oxygen, neon burns, then magnesium, and finally the very last stage. Right before the core of the star turns into iron, silicon burns out, which probably only takes a day. That's when the star really starts to have problems. Iron is different from the other elements in that it doesn't release energy when it's transformed by nuclear processes. By this point, though, the star's energy production has stopped, and the core starts to shrink because gravitational energy is now the only source of energy. Once the core, which is now made up of iron, reaches about 4 solar masses, it suddenly loses its ability to resist the crushing force of gravity. In a matter of seconds, the outer layers of the core collapse and rush inward at about 70,000 kilometers per second. That's about 20% of the speed of light. As a result of the collapse, electrons and protons merge to form neutrons, which in turn produce a stream of neutrinos that push outward from the collapsed star. The matter falling on the center of the iron core is thrown out at incredible speeds, given the density of the core, which is now 40 grams per cubic centimeter. Could this be how a neutron star or a black hole is born? If the star is really big, at this point a shock wave forms around the nucleus. This is because the neutrinos are diverging in all directions and heating up the nucleus. They follow a straight path and will reach the Earth before the supernova light. Since the actual explosion hasn't happened yet, it can take several hours for the shock wave to travel from the core to the surface of the star. The temperature of the outer layers of the star rises significantly. This allows the formation of heavier elements from the iron group, such as radioactive nickel-56 and elements of intermediate mass between silicon and the iron group, such as radioactive titanium-44. It's thought that heavier elements like gold, platinum, silver, and uranium are created when neutron stars merge. When the shock wave reaches the outer or intermediate layers of the star, a massive explosion occurs, accompanied by the ejection of matter at over 50 million kilometers per hour. It's this final explosion that marks the end of the star with a spectacular supernova display that can outshine an entire galaxy. These supernovae are known as collapse core supernovae. There are a few different ways that collapse can happen, but the most common are Type 1b, Type 1u, and Type 2 supernovae. In all three cases, the precursor star starts out with 2 layers of outer hydrogen and helium. Stars that have lost both layers during their lifetime explode as Type 1u supernovae. If the first layer hasn't burned out, it's a Type 1b supernova. If both layers are still there when the star collapses, scientists call it a Type 2 supernova. Even after 10 years of observation, study, and modeling, we still don't know exactly how a neutron star is born in such core collapse scenarios. Recently, scientists have been puzzled by a different type of supernova that doesn't fit the usual core collapse model. We're talking about superbright supernovae here. These surprisingly powerful, rare transits are about 50 times brighter than their taker relatives. There's no clear explanation of their nature, nor any idea of why they're so bright. There are lots of different ideas out there. One hypothesis is that these supernovae get their energy from strong magnetic, rapidly rotating neutron stars. These are formed in the usual collapse and transfer the energy of the ejected stellar material to the remnants of stars, heating them up so much that they begin to glow. The Large Survey Telescope will soon be able to detect 1 million new supernovae. It'll be really helpful to look at the findings to understand how and why giant stars actually explode. The astronomers are excited about this promising data. It seems there are likely to be undiscovered slow-spinning pulsars. If we find them, we'll have a better understanding of the population of pulsars and neutron stars in the galaxy. It'll also help astronomers figure out how quickly neutron stars formed as the universe evolved. The discovery of the pulsar was based on. There's another strange thing, too. The thing is, even though it spins pretty slowly, we've also measured how quickly it's slowing down, and it's got a pretty strong magnetic field compared to other pulsars. After Orlov discovered this pulsar, other telescopes picked up its signals at frequencies between 300 and 400 megahertz. What makes LOFT special is that it can register very low frequencies of radio waves from 10 to 240 Hz, which overlap with the bandwidth of 87, 5 to 108 megahertz. Before they reach computers, the signals in the air are processed in real time by supercomputers at the Netherlands Institute of Radio, University of Groningen. The data this observatory collects is pretty unique compared to other radio telescopes. Normally, radio signals gathered from a particular location are sent to receivers, where they combine signals from 1,000 antennas spread across different countries. They use a method called interferometry to do this. In other words, all the antennas work together as one big virtual telescope, with an equivalent collecting surface of about 300,000 square meters. That's precisely how the antenna and the Bolivian reflector pair system operate. There aren't any moving parts, though. At any given moment, each antenna has a view of the entire sky. To direct the airwaves to a specific area in the sky, A supercomputer calculates the difference in the time it takes the radio signal from that area to reach the different antennas. Once that's done, the signals are synchronized to correct for the time difference, and the information is presented as a map of the sky. The very low frequencies that the ether is capable of registering have long been out of reach for single reflector observatories. This is because the lower the frequency of a radio wave, the longer the wavelength. A frequency of 10 megahertz is the same as a wavelength of 30 meters. That's why it's a good idea to make the collecting surface as large as possible. This allows us to get a high-resolution view. Radio interferometry in the air has made it much easier to spot radiation sources across the whole range of radio frequencies. So far, this radio telescope has already discovered about 100 new pulsars. The pulsar that CHEO detected wasn't always as slow as it is now. The pulsar that formed after the supernova explosion was young and energetic at first and rotated much faster. The reality is that the collapse of the core of its parent star, in which protons and electrons fuse to form neutrons, only stops when the pressure of the neutrons, which are incredibly compressed into a tiny volume, balances the gravity of the core. A newborn neutron star gets its spin from the original star spinning like crazy, just like all the other stars. Our sun is no exception to this rule. It takes about 30 days for it to make one full rotation around its axis. But when a massive star rapidly shrinks at the end of its life, during a gravitational collapse, the rotation rate increases significantly. It's like the sudden increase in speed a figure skater gets when they push their arms out wide against their body. Simply put, the star transfers its angular momentum by compressing the core, which gives it a significant increase in rotational velocity. The radiation that these rotating remnants of star cores send out into outer space is what allows us to detect them. We don't yet know exactly what causes this radiation, but scientists are looking at a few different possibilities. It's thought that all neutron stars have the same internal structure. It seems there are 3 different sources of the radiation we're seeing. Sometimes, a neutron star's radiation may only come from its rotation. In other cases, it's the matter from the companion star that's responsible. Finally, some neutron stars are so strong in terms of magnetism that their swirling magnetic fields can cause growth. Risks outside the star's surface. A star shock happens, and it's accompanied by a powerful, short, and bright flare. Each of these mechanisms is pretty remarkable in its own way. As we keep observing neutron stars, we're getting a better understanding of how they work. When Jocelyn Bell discovered the 4 G-class pulsars, they seemed like little green men scattered across the sky, spinning in cosmic solitude. Radio pulsars use their own rotational energy to emit radiation. Since then, more than 2,700 radio pulsars have been discovered, mostly in our own Milky Way galaxy. As of September 2022, we've identified more than 3,300 pulsars. The emission from these pulsars is too faint for our radio telescopes to detect them. The ones that are much farther away are super slow pulsars. It's also one of these radio pulsars. The radiation from a rotating pulsar comes from particles that are accelerated along the line between its magnetic poles. When a stream of particles crosses the telescope's beam of view, we register a burst of radio. Pulsars can be either single stars or parts of double stars. That's a system of 2 stars that are bound together by gravity and orbit around a common center of mass. As the pulsar loses energy, its emissions become weaker and slower. The slowest pulsar is no exception. They usually emit in the radio band. While some pulsars can produce X-rays and gamma rays, it's uncommon to find one that's particularly large. These are called faint X-ray single neutron stars, which are stars that emit only in the X-ray range. This is unusual for single pulsars, which usually emit in other wavelengths. Just 7 have been found so far. They've been nicknamed the Magnificent Seven. What they really are is still a mystery. It's possible that we're unable to see the radio waves from these sources because they're not directed at us. Or maybe they're just really narrow, so there's not much chance of them crossing the telescope's field of view. Just picture someone waving a laser pointer right next to you. There's only a small chance that the narrow beam will shine directly into your eyes. Even before the discovery of the first pulsar, the Italian astronomer Franco had already suggested that rapidly rotating neutron stars could emit radio waves. However, this will involve a number of different physical processes. The parent star gives its offspring not only rotation, but also magnetic flux, which is a component of the magnetic field perpendicular to a given surface. So, a neutron star gets a magnetic field, but a pulsar, like a bounded bar which is shown in a physics lesson at school, has two magnetic poles. The magnetic lines of a pulsar behave quite differently. The magnetic lines of the pulsars leave the south pole and head to the north pole, where they exit again, forming continuous, infinite closed loops. As a neutron star spins, its magnetic field lines also rotate along with it. They're attached to the surface in a similar way to grooves on a spinning gramophone or records, and like a child on a merry-go-round. The further away the stars are, the faster they spin. But the rotation rate can't keep increasing forever. At a certain point, it reaches a speed greater than that of light. At this point, the rotation of the field lines and the star come to an end. Otherwise, the field lines will move faster than the speed of light, which is impossible. This is the virtual boundary where co-rotation is no longer possible. It's what we call the light cylinder. Any magnetic force line that isn't getting destroyed. The light cylinder is still open. The radiation spreads out inside the cone that's bounded by the last closed lines of force. It ends at the light cylinder. The light cylinder has each rotating magnet, including the Earth. But the Earth's magnetic field is pretty weak. It can range from 0.25 to 0.65 at the surface. Gauss and the ends of the cylinder are so far away that they don't have any impact. However, the magnetic field of a neutron star is so strong that it makes a difference. These open lines of force can actually accelerate particles, just like a motor. Near the two magnetic poles, they pull an enormous number of particles from the surface of the neutron star. These particles, mostly high-energy electrons, are carried along the open lines of force inside narrow cones of different beams, not necessarily directed along the pulsar's axis of rotation. As they interact with the magnetic force lines, the particles are accelerated and emit radio waves that travel through space in the same direction as the moving particles. If one of the streams of particles traveling through space is pointing toward Earth, we can spot a pulsar. As we said earlier, a pulsar is like a lighthouse at sea. It emits light continuously, but it rotates on its axis, so we see repeated flashes of light over time. As more and more particles are swept away from the neutron star's surface, the pulsar slows down. At some point, the pulsar, which has lost its energy, begins to spin too slowly. The magnetic lines of force can no longer pull electrons from the neutron star's surface, so the emission will have to stop. It's thought that around 965 years ago, when the nebula pulsar was young, its rotation period was 16 milliseconds. Right now, it's 33 seconds, and the pulsar is still slowing down. Each 100 years, it slows down by about 1.3 milliseconds. The stronger the initial magnetic field, the faster the pulsar slows down. The magnetic field of young pulsars is about 10, 12, 10, 13 degrees Gauss. For comparison, the magnetic field of a refrigerator magnet is around 100 times weaker. These pulsars stay active for anywhere between 10 and 10 million years. This means that of all the neutron stars that have been born in the 13 billion years that the universe has existed, about 99% do not emit in the radio band. Even though they keep on rotating slowly, the light from their beacons has gone out. They've crossed the line and dissolved into the nothingness of space, joining the graveyard of neutron stars. I think it's fair to say that anyone who criticizes pulsars is a bit misguided. Not all pulsars remain inactive. Some are linked to a companion star. The gravitational forces pull on the matter of the companion radio pulsar, and they can rise from the dead. Scientists refer to the process of unwinding as milliseconds other pulses. December 29, 2016, was an unusually snowy and cold day in the Netherlands. There were still a few months to go before the supercomputer at the University of Groningen would get data from the slowest pulsar of the new GPS. It gave astronomers a belated Christmas present, though. Kees Bassa of the Netherlands Institute of Radio decided to take a look at Olaf's latest readings. After all, the telescope hadn't gone on vacation, so the search for pulsars continued. He was sitting in his bedroom, going over the latest data as usual. Bassa noticed a sudden peak in the signal, which could be a pulsar spinning at an extremely high speed. This was pretty interesting, so Bassa sent an email to his colleague Jason Hess at the University of Amsterdam, even though it was the weekend. The subject line of the email caught his attention. When Hess opened it and saw the data, he was greeted by a sea of dots. 2 of them had already been back from vacation. Among all the pulsars discovered is a new one. It's now known as NPJ 607, and it's the second fastest rotating pulsar. It's now almost as fast as the record holder, which was discovered in 2004. The rotation periods of both pulsars are measured in milliseconds. Imagine the base pulsar as a ball the size of Washington, D.C., spinning at 707 revolutions per second. The Fed told me that even before any testing, I should be able to tell from the Bassa letter that everything is spinning correctly and fast. A pulsar is what we call a millisecond pulsar. The first such pulsar was discovered by American astrophysicist Donald Charles Barker in 1982, after his graduate student Sri Carney processed data from the Alice telescope. This pulsar, which has been dubbed SNP 37+21, spins at an unusually fast rate, 20 times faster than nebula pulsars. It spins at 642 revolutions per second. It's held the speed record for more than 2 10-year cycles. So far, astronomers have discovered more than 300 other millisecond pulsars, most of them in the Arctic disk. We can draw on our own experience here. As of September 2022, we've identified about 500 millisecond pulsars, which are pulsars with periods of less than 10 milliseconds. They're densest inside globular star clusters with lots of old stars where gravity pulls them together. These clusters can have hundreds of thousands or even millions of stars. Even so, only about 5% of them are millisecond pulsars. Unlike radio pulsars, which make a few revolutions per second, millisecond pulsars are usually found paired with another star, most often a white dwarf. It's worth noting that the stellar pair hasn't always existed in this form. These double systems start out as a pair of ordinary stars orbiting each other peacefully. At some point, the more massive star runs out of nuclear fuel. The star then explodes as a supernova, leaving behind a neutron star. If the system makes it through the supernova explosion, that is, if the neutron star and its companion don't fall out of the system, they'll keep orbiting around a common center of mass. Pulsars emit energy in the form of radio waves, sometimes also X-rays and gamma rays, and rotate ever slower. Over time, this pulsar may slow down so much that it becomes silent, and our telescopes will no longer be able to see it. 1,000,000 years later, the pulsar that orbits a normal lower mass star will also run out of fuel. The star will start to grow and become a red giant. This is where it gets really interesting. As it inflates, the star approaches its companion pulsar, which is called noise castle. At some point, the pulsar will get so close that its radiation will heat up the red giant and cause matter to escape. When this happens, a jet is formed from the material of the pulsar's companion, aimed at the dead star, so that a disk of captured matter is formed around the neutron star. This process is what we call aggression. It can be described as a hot donut-shaped disk. The dough is broken up, and the matter flows through an opening that looks a bit like a bathtub drain. It swirls around the neutron star, gradually settling on its surface. The flow of matter onto the neutron star reduces its magnetic field, but nobody fully understands how this works. Because of this aggression, the neutron star gains angular momentum and starts to rotate faster. The neutron star's companion can be thought of as giving it new life. The matter falling on the neutron star interacts with its magnetic field. If the magnetic field is strong enough to overcome the gravitational force, the hot gas plasma is trapped along the magnetic lines of force and then starts to flow towards the magnetic poles of the neutron star. This causes the neutron star to form hot, aggressive spots. These are typically called hotspots at the magnetic poles. It's like a bump or a mountain on top of the poles. Once the hotspots start emitting in the X-ray range, the pulsar can be detected again, as long as the hotspot is in the field of view of our X-ray telescopes. This type of system is called a low-mass X-ray binary, or LPX for short. The companion star, which transmitted the neutron, was originally a low-mass star like our Sun. The pulsar emits X-rays. Since then, about 200 LPHs have been spotted in our galaxy, with 13 of them in globular star clusters. You can observe them with space X-ray telescopes like Chandra and X. But the discovery of these systems actually began with rocket launches. It was 1949. They mounted an X-ray detector on a converted Phow-2 rocket that was launched from White Sands Missile Range in New Mexico. The detector was designed to record X-rays from the Sun, and it was carried outside the rocket's atmosphere. It was thought that our own star might also be a source of X-rays. They knew that X-rays should be absorbed by the atmosphere. But they expected that stars and other cosmic bodies like our Sun, which contain very hot gases at temperatures between 10,000 and 10 million Kelvin, would emit X-rays. It was assumed that the Sun's X-rays would be considerably weaker than the visible light that our star emits, and that's why, according to astronomers, it was impossible to detect X-rays from more distant stars. In 1962, they realized that this assumption was incorrect. Italian astrophysicist Riccardo Gioconda installed an X-ray detector on the Era 150 rocket. It launched on June 12, 1962, which was the first time cosmic X-ray emission from a source outside the solar system could be observed. This source is now known as Scorpius X1, although it's much farther away from the Sun. Its radiation is 100,000 times more intense than the Sun's total output across the entire wavelength range. It's become clear that Scorpius X1 isn't a star. On top of that, the JACO detector didn't show that X-ray radiation fills the entire universe. X-ray astronomy was born. Just as Joe Bell had been working on this project at Cambridge in the mid-60s. Soviet astronomer Iosif Shklovsky kept on looking at the X-ray and optical data from Scorpius X1. His hypothesis was that the radiation came from a neutron star, which explained what happened to the companion star. At the time, neutron stars were only theoretical, but Bell later found the first NGM-1 pulsar and its three cousins. It wasn't long before they confirmed that Scorpius X1 is a double X-ray star, specifically a RX. It's still the brightest known X-ray source in the sky today. In 1970, the Gioconda group launched the Uhuru satellite, which was the first orbiting X-ray observatory. The observatory later made the first discovery of what is thought to be a black hole candidate. Uhuru is actually the unofficial name of the SAS, which is a small astronomical satellite. The name Uhuru has really caught on. In Swahili, the word means freedom. The satellite was launched from Italy's San Marco Space Center in Kenya on the country's Independence Day. Later on, Giacomo worked with the Einstein X-ray Observatory, the first X-ray telescope to image the source, which was launched in 1978. He then worked with its successor, the Chandra telescope of the Space X-ray Observatory, which was launched in 1999. The equipment wasn't as sophisticated as it is now at the time. David Buckley, of the South African Astronomical Observatory in Cape Town, says that at the time, it wasn't possible to get as good an X-ray image from Chandra or CDNP as it is today. We knew that there were X-ray sources in some areas of the sky, but it was difficult to find their optical counterparts. Some even used old-fashioned photographic plates to look for blue and variable objects in the sky. One of the first X-ray sources to be identified as a double system was Swan X1. It got its name according to the standard practice at the time. The astronomers who discovered these X-ray sources named them after the constellations where they were found, adding the letter X to indicate that they were X-ray sources. As more and more sources were discovered, the rule was gradually abandoned, as there were now over 1 million of them. These days, unexpected bursts of X-rays are being looked for by modern detectors like the Integral Swift and the MAXI instrument, which is used to monitor X-ray images of the whole sky. It was developed by Japanese scientists and installed on the International Space Station. There are other types of neutron stars that can be studied in the X-ray range, in addition to RXs. If the companion neutron star in a double system has an intermediate mass, the system is called an X-ray intermediate mass double system, or Abkhazia. If the mass of the companion star is more than 10 times that of the Sun, we're looking at an X-ray double massive system, or HMH. In this case, one of the stars explodes as a supernova and becomes a neutron star, although its companion is an extremely bright star that puts out a stellar wind. The radiation pressure prevents the matter from forming an accretion disk and instead causes it to settle directly on the neutron star's surface. The wind energy is converted into X-rays. You can also see HMH in the optical range, where the radiation from the massive star is the main thing. It's worth noting that not all LMKPIs contain a neutron star. Sometimes it can be replaced by a black hole. However, the systems are thought to be the most unusual, as they are believed to be the progenitors of the fastest and oldest pulsars. As the aggression builds up, the companion stars matter. Crossing over to the neutron star causes its magnetic field to weaken when it is reduced to 10/8 of a degree of Gauss. The matter ends up so close to the surface that, by transferring angular momentum, the pulsar can accelerate its rotation enough to become milliseconds. Once the secretion is complete, the X-ray emission from the disk stops. This 5-second radio pulsar is in the so-called spin-up phase, which is when a weakened magnetic field and accelerated rotation combine. This results in a longer pulsar lifetime. A visible pulsar lasts anywhere from 10 to 10 million years, while a neutron star can live for over a billion years. That's about the same age as the universe. Hello, twice dead zombie squared. This is the remnant of the core of a once massive star that has become a very old radio pulsar. Meanwhile, the second pulsar's companion turns into a white dwarf. It could either stay a white dwarf or be blown away by the pulsar's high-energy particles. This happens when the pulsar heats its companion to twice the temperature of the Sun's surface, gradually destroying it. That's why some pulsars aren't part of double systems. They exist on their own. They're called black widows because they act like the female spiders of the same name, devouring their spouses. For instance, the first millisecond pulsar was discovered by a hacker. So far, 18 of these pulsars have been found in our galaxy, and a few more have been spotted in globular star clusters that are part of our galaxy. As of September 2002, we've identified more than 40 of these pulsars. Some of them are on their own, while others are linked to extremely low-mass stars. This is the type of system that the BAS has discovered. The white dwarf companion pulsar had a mass of just 2% that of the Sun. It seems that it lost most of its mass because it was so close to a pulsar that was hungry for mass. If the companion star is slightly more massive but still struggling to survive, the pulsar will call on its Australian wingman for help. This is similar to how the spider analogy works. The pulsar will usually emit radio waves in these instances. Some of them aren't sure what to do and send out signals in either the radio or X-ray range from time to time. These unusual objects have been dubbed transient millisecond pulsars. In 2008, a team from the University of Amsterdam led by Archibald used the Green Bend telescope in West Virginia to discover a new radio pulsar now known as Retired J. 1023 plus 2038. When N and her colleagues looked at the old data, they found that 8 years earlier, in the same place, a neutron star had been spotted in the optical range. It's situated within an expedition disk. They started keeping an eye on the new pulsar with the global, including the Green Bank and West God telescopes. The pulsar was visible until June 2013, and then it just disappeared. A few weeks later, the disk reappeared, and the star was visible again in the optical range. The disk was quite aggressive, making the star very bright. Later observations made in both parts of the spectrum by space X-ray observatories and optical telescopes on Earth showed that the system was switching back and forth between radio and other frequencies. Studying the X-ray band shows us when the pulsar becomes visible to the naked eye. It's pretty unusual for a double system like this to consist of two neutron stars pulsating. As of now, only one such double pulsar system is on record. J0737 plus 3039A. We haven't seen any outbursts from the slower pulsar, also known as Pulsar B, since 2008. Its less second partner A is still emitting radio waves safely. Another way that some neutron stars can emit more power is through their magnetic fields. Their magnetic fields are so strong that they're basically the strongest magnets in the universe. As the magnetic field weakens, these neutron stars start to emit X-rays and gamma rays that we can observe. These neutron stars are called magneto armies, and so far scientists have only been able to detect about 30 of them. We were discovered by chance, says Chris Kuetu, a professor of astrophysics in the physics department at George Washington University in Washington, D.C. She started researching magnets in 1979 when she was a master's student from Greece at the Max Planck Society Institute for Physics in Munich. This wasn't recognized at the time. At the time, the mystery of gamma-ray bursts was still a topic of discussion over the summer. Kuwait decided to focus her thesis on the extremely powerful flashes of gamma radiation coming from deep space. These bursts were first spotted in July 1967. 2 American reconnaissance satellites were designed to record gamma rays and atomic bomb explosions. Since they're in Earth orbit, they'll make sure that no one violates the agreement on banning nuclear weapons testing in space. The satellites suddenly picked up a brief burst of only 0.2 of a second. The burst of gamma rays had a signal that was very different from what you'd expect from a nuclear weapon made on Earth. 3 minutes later, the flash stopped. Then, 5 hours later, a weaker beam of X-rays was spotted coming from the same spot in deep space. The bursts went unnoticed by anyone except scientists working for the United States government space program, thanks to the Earth's atmosphere. Where did they come from? The U.S. military was concerned. Later on, other detectors picked up similar bursts. In total, 16 bursts were detected and studied. First, strictly secret at Los Alamos and the U.S. Department of Energy's National Laboratory, which was set up during World War II to develop nuclear weapons. At last, in 1973, the scientists at Los Alamos published their findings. They said these were signals from outside the galaxy that didn't seem to have anything to do with nuclear weapons on Earth. Nobody had a clue what was causing these flashes. Given that my thesis supported the most popular theory at the time, I concluded that the flares originate in the final stage of evolution. I'm talking about supermassive, rapidly rotating stars, when it collapses into a black hole. This theory still fits with current thinking when it comes to long bursts lasting more than 2 seconds, gamma-ray bursts. However, it was shown in 2017 that much shorter gamma-ray bursts, known as short bursts, are caused by the merger of 2 neutron stars. Given how bright gamma-ray bursts are, many scientists initially thought that the source was somewhere not far away, within our galaxy. This meant that the observed gamma-ray and X-ray power must be just below the Ellington limit. Ellington's limit is the maximum luminosity of very hot and bright stars. It's reached when the inward-directed gravitational forces and outward-directed radiation pressure are in balance. And then something incredible happened. On March 5th, 1979, a strong gamma-ray wave hit 2 Soviet automatic interplanetary stations, Venera 11 and Venera 12, which were in near-solar orbit. Just a few months earlier, a descent vehicle had detached from both stations and entered the acidic, toxic atmosphere of our closest planetary neighbor, Venus. The stations then continued on their orbit around the Sun. Russian astronomers noticed that the readings from instruments monitoring galactic radiation were pretty normal, at around 100 bursts per second. But when a wave of gamma radiation hit the stations in the early evening, the radiation levels shot up. The instruments registering over 200,000 pulses per second malfunctioned. The wave didn't stop there. Just 11 seconds later, it reached Achilles. 2 NASA vehicles were also in orbit around the Sun. Then, we switched over to Venus to get the American Piper Venus probe out of orbit. Next up was Earth. The radiation stream reached detectors on 3 satellites. The U.S. Department of Defense and the H. Einstein Observatory were the first to use an X-ray telescope to image the source and the Soviet satellite. That's all there is to it. At last, he moved on to the NPP probe and 3 others designed to study the magnetic fields around the Earth. Luckily, a year before the NPP and 3 launches, scientists studying gamma-ray bursts had asked to add a pair of gamma-ray detectors there. This area of research was still pretty new, and the probe didn't have detectors like that on it. They got what they asked for. When the data from the NPP and the 3 Quasars started coming in, she was working at her desk at the Max Planck Institute for Extraterrestrial Physics. Before she could defend her thesis, she had about a year. Kubilius recalls that at first, everyone thought the incredible peak was due to an instrumental error. But when data from other satellites came in, it was clear there was no error. The flash was really quick, just a fraction of a second. But the gamma-ray wave that swept through the solar system was 100 times more powerful. Kubilius and her colleagues were blown away when they saw the data from the Bell satellites in 1967. All the gamma-ray bursts that had been detected before were thought to be the result of one big explosion that then disappeared. But now, on March 5, 1979, after the first peak, we saw regular pulses for another 100 seconds. What really stood out was the periodicity of this tail. The periodicity meant that the compact object had a surface. In other words, it was a neutron star, says K. Uvedet. Before long, other, albeit less intense, bursts were registered, but the direction of the signals clearly pointed to the same place in the sky. And their description didn't fit with any of the known theories about how gamma-ray bursts are created. Koval says, "It was all so mysterious that we were simply confused. Some scientists even suggested that the first burst was caused by a comet hitting a neutron star. They were soon able to pinpoint the source of the March 5th event. It was in a big new cloud and was linked to the young supernova remnant N49, which was about 5,000 years old. This meant that the source was about 1,000 times farther away than we originally thought, based on how bright it was. This source had a luminosity at least 1 million times greater than the limit. Given the periodicity of the tail pulses, it seems unlikely that a black hole is the source. But there was a supernova remnant. Could a neutron star be the source? At the time, we only knew that pulsars are rapidly rotating neutron stars that emit radio waves. However, the X-ray burst observed on Earth was too powerful to be correlated with a radio pulsar. On top of that, it seemed like the neutron star, if it was actually a neutron star, shouldn't be right in the center of the supernova remnant, but somewhere on the edge. This meant that when it was born, it was thrown out of the place where its predecessor star was at a speed of about 1,000 kilometers per second, which was much faster than any of the then-known pulsars. Over the next 4 years, scientists at the Physico-Technical Institute in Leningrad, now the IOFA Physico-Technical Institute in St. Petersburg, observed 16 more bursts coming from the same location. Some were stronger, others weaker, but all were less noticeable and shorter than the March 5 outburst. Later on, groups from 3 different locations in the sky recorded a few more similar events. Nobody really knew what they were. At the time, most scientists thought they were gamma-ray bursts. The thing is, these bursts didn't have as much energy as normal gamma-ray bursts. Since these events kept happening, it was clear they weren't linked to any catastrophic occurrences. More and more scientists agreed that gamma-ray bursts were much more powerful and originated outside our galaxy, but closer to us in the plane of the Milky Way. The source continued to emit bursts of energy, which were observed for the first time. March 5, 1979. It looks like the last ejection was spotted in May 1983. I'm confident that I was on the right track to solving this mystery. The issue was that there were no instruments available to investigate these mysterious bursts, and no high-resolution equipment to determine their source. Kuwait had to wait for more than 10 years. She had no idea that 2 theoretical physicists were getting closer to solving this mystery. As it turned out, their paths would cross again soon enough. In 1979, when a wave of gamma radiation covered the Earth, Chris Thompson was still in school, and unlike Sky Violet, didn't even know gamma-ray bursts existed. But in 1986, Thompson, along with Robin Duncan, started looking into the magnetic fields of radio pulsars. At the time, He was a master's student at Princeton University, and Duncan had just defended his thesis there. The young men were interested in finding out how magnetic fields affect the rotation of pulsars and why some pulsations are stronger on the magnetic than others. They found an important clue in a paper on newly formed neutron stars. Adam Burrows of the University of Arizona and James Vladimir of Stone and Brook University in New York State published a paper shortly before that showed how a computer model could be used to demonstrate that the dense liquid inside a still hot neutron star circulates by convection for a few seconds before it begins to cool. All stars have weak magnetic fields and only transfer some residual magnetic fields to the neutron star. However, as Duncan and Thomson suggested, it can sometimes become much stronger. This won't happen with every pulsar, just those that spun really fast at birth, which triggers the dynamo effect. This effect is also seen on our planet and in most stars. This happens when an electron-conducting liquid or gas moves in cycles. The hotter areas rise to the top, then cool down and sink back down again. It's a bit like the way a tongue sings in a pot. In water, the magnetic field depends on the charged particles in the liquid, so it is pulled and amplified as it moves. At this point, the interior of the neutron star is still a regular, non-superfluid liquid. This only forms when the star cools down significantly. This hot neutron fluid swishes up and down at a speed of a few thousand kilometers per second. If Duncan and Thomson are right, the newborn neutron star has a strong initial magnetic field and rotates pretty fast, more than 200 times per second. The dynamo effect kicks in gradually, but everything happens pretty quickly, in just a few seconds. This is enough to increase the magnetic field to over 10 to the 15th power. This is 1,000 times the magnetic field of a typical neutron star, and it's rotating too slowly for convection to start and the dynamo to kick in. What this means in practice is, as a point of comparison, the Earth's magnetic field is only about half a Gauss, while the magnets on a refrigerator are about 100 times weaker. The magnetic field of sunspots in the sun's most magnetic places is about 3,000 times stronger than the Earth's magnetic field. The stronger the initial magnetic field, the faster the neutron star dies. Eventually, it starts to rotate too slowly to emit radio waves. It can take anywhere from 10 to 1 billion years for a pulsar to fade away. Thomson and Duncan decided to look into how the process of increasing the magnetic field works in more detail. We were curious about how these fields would show up. We might even be able to find their calling card, Thomson tells us. In 1992, they published a paper that led to the exploding bomb effect, where they introduced the term magnets, or on-magnetic, to describe these strange objects. Star magnets are neutron stars with a stronger magnetic field than anything else in the universe. Thomson and Duncan figured out that the highest magnetic field a star like this can create and hold is about 1017 Gauss. When this limit is reached, the nuclear fluid inside the star starts to move, and the field weakens. Theorists also looked into how a really strong magnetic field affects the rotation of a neutron star. It didn't take long to realize that this field slows down the rotation of the magnet pretty quickly and significantly. Eventually, almost all of the rotational energy is converted to magnetic field energy. The magnet should rotate faster than a normal pulsar when it's born, but its rotation rate drops a lot at a field of 1015 G. Gauss is responsible for the magnetic waves that collect the rotational energy. After about 5,000 years, it reaches 8 seconds. On top of that, a magnet's rotation speed isn't always the same. Initially, they slow down rapidly, with their rotation period doubling from a few minutes to a few hours. Thereafter, the deceleration rate gradually decreases. While neutron stars, especially millisecond pulsars, are known for being stable, magnetars are a different story. The rotation speed is always changing and can go up or down by as much as 10 times. It turned out that the periodicity of the event on March 5, 1979 was exactly 8 seconds. This showed there was a link between the sources of soft recurring gamma-ray bursts and the super-strong magnetic fields from Thomson and Duncan's magnetic dynamo theory. For theorists, the 1979 burst was also really useful because it was so big. Energy and brightness. It became clear that super-strong magnetic fields could explain the very high brightness at the peak of the giant magnet flare, the 1979 event which was 1,000 to 10,000 times or brighter than the repeated bursts. They could also explain the long tail of regular pulses recorded following the bright gamma-ray peak. Since the magnetic fields and what was ejected in the flare are carried away by the rapidly rotating neutron star, astronomers have recorded a burst every time the star looks directly at Earth. Thomson and Duncan said there were two ways to figure out how strong the magnetic field of a neutron star could be. The first one, according to their numbering system, used a combination of the observed rotation period and the age of the supernova remnant 69. But if the magnetic field was responsible for the 1979 outburst, it had to be stronger than 1014 degrees. The theorists also figured out that when a really strong magnetic field passes through the solid, normally stable crust of a star, so much stress builds up in it that the crust collapses. The star is shocked. This causes the magnetic field outside the star to twist and transfer energy to clouds of electrons and positrons, which releases a huge amount of magnetic energy in the form of hard, high-energy gamma radiation. This is similar to the radiation of a solar flare, but much more intense. It turns out that the pulsating tail is powered by the remnant. It gradually reduces in size until it's just a fireball of a hot cloud of electron-positron pairs captured by the magnetic field near the rapidly rotating neutron star. The cloud remnant cools down as it emits X-rays from its surface. Thomson thinks the energy release outside the neutron star is probably due to a process called magnetic accretion. For instance, an explosion on the sun or a solar flare is an example of magnetic accretion, which is when magnetic lines of force near the surface are rearranged quickly. This process releases magnetic field energy, which is often studied as gamma rays. However, the specifics of this process in a magnet are now being actively studied, according to Thomson. These kinds of magnetic fields can lead to some pretty unusual new phenomena. X-ray photons join together and then split in two. It's thought that atoms can deform completely, becoming long and thin like spaghetti. Neutron stars that are nearby have the most energy, making them the hardest. X-rays don't travel in the usual way. The strong magnetic vacuum around a neutron star must act like a modernizing filter, letting radiation through like sunglasses. Just linear polarization, please. In 2016, this effect was confirmed by direct observation. Thomson and Duncan also figured out how the rotation of the magnet slows down, based on the star's magnetic activity. In 1995, they published another paper together that built on their theory. In it, they proposed 7 different ways to calculate the magnetic field of the outburst that occurred on March 5th. All 7 methods yielded the same result: a magnetic field strength greater than 10 to the 14th Gauss. Many astronomers were skeptical of Thomson and Duncan's bold claims. They weren't convinced by the science. It had been waiting for the right tools to come along for a long time. Was the 1979 event really just a short burst of gamma rays? And what do these bursts represent? In reality, though, after reading an article that suggested the possibility of magnetous existence, Koval, with a small group of colleagues, decided to test this claim. On December 13, 1995, NASA was gearing up to launch a carrier rocket with the WASP-XD satellite and the Rossi X-ray Time Characterization Explorer on board. The probe had one very specific goal: to track the time variation of various X-ray sources, focusing on black holes and neutron stars. She put together a project to observe the sources of soft, repetitive gamma-ray bursts that she was hoping would show up over the lifetime of WASP-XD. The project got the green light by summer, as luck would have it. Not long after the satellite reached its designated orbit around Earth, it picked up a burst from one of the sources, the 1979 event. 2 years earlier, the Japanese satellite GAE had already observed this world, pinpointed its exact position, but hadn't been able to determine the rotation period of the star. Violet's group has now shown that pulses of X-ray emission occur every 5 seconds. As the neutron star spins, so do the hot spots in its magnetosphere. They're either visible or invisible. This means that the star rotates every 7, 5 seconds, which is almost the same as the 8-second pulsation period observed in March 1979. I'm pretty sure she started observing this object. She wanted to figure out how long it took to complete one rotation and how fast it was slowing down. This would help us figure out if Thomson and Duncan were right, that an extremely strong magnetic field causes a magnet to slow down very rapidly. As it turned out, by the summer, she was using a chronometer to observe this object. This was a common method for studying pulsars. She was able to determine the exact moments when one or more pulses arrived. The idea is that if they notice changes in the timing of the pulses, it could be a sign of something going on in space. For instance, when a neutron star and its companion are orbiting in a binary system around a common center. The original data were pretty faint because of lensing noise, so her timing technique was clearly a bit different from the usual ones used by radio stations. When it comes to pulsars, radio observations are pretty accurate, which lets us relate rotation periods at different times. For instance, let's say that at each rotation, the radio brightness has two peaks, a big one and a small one. This means we can measure the rotation period so accurately that we can even predict when the large peak will appear in the future. Since the next measurement will be a few days or months later, the time of its appearance will be slightly shifted due to the slowing down of the star's rotation. The Kuwaiti method was a bit more straightforward. It was based on the technique used by astronomers who were trying to fix the periodicity of the X-ray signal of X-ray pulsars. We got the reading in just a few hours. Then, after a while, the same measurement is taken again. But since the accuracy of the measurement is lower than for radio pulsars, it's more difficult to relate the rotation periods for these two intervals. As you might imagine, after 5 years the chronometer earlier, it had become clear that the pair's rotation period had decreased by 2000, which meant that it was decreasing by 1 second every 300 years, faster than any known radio pulsar. The increase did the math and figured that if the star was slowing down at this rate, giving energy and angular momentum to the magnetic field, its strength would be 8 by 1014 degrees. Gauss. This value was pretty close to what Duncan and Thomson had estimated, and it was much stronger than any other magnetic field in the universe. The precision of the measurement was sufficient to demonstrate the significance of the rate of rotation deceleration, according to Thomson. That was all the confirmation we needed. Skye was pleased with the result, but to be sure she sent her data to 2 other groups for verification, without telling them in advance what period she had gotten. The period and the rate of change matched up perfectly. She now saw how important the discovery she'd made at the George C. Marshall Space Flight Center in Hunt, Alabama was. She got in touch with Duncan and Thomson. We were now 100% sure that it was all real. We were so excited we could have jumped for joy, says Kurilenko. We started putting together an article for This Is How It Was. We also started using the name magnet, since it was the first example of a magnet. The article was published on May 21st, 1990, and got astronomers pretty excited. It's a pretty amazing event, and it gives me a great feeling. We should know by summer who discovered the source of these soft, repetitive gamma-ray bursts. After all, I always said it was something new, and I stuck to that until they finally measured the magnetic fields. I was right about this. It is, in fact, a new source because its magnetic field is so large. That was just the start. In just a few weeks, 1900 plus 14 had triggered more than 50 times. In June 1990, astronomers discovered a fourth source, WASP 162741, which produced about 100 powerful flares over the next 2 months. On the morning of August 27, 1990, an extremely powerful wave of gamma rays and X-rays hit Earth. 7 satellites scattered throughout the solar system noted this flare, which was stronger than the one on March 979. It even caused a sudden change from the ionosphere to Earth's upper atmosphere, which affected radio communications at 3 F-22s in North American Pacific Daylight Time. The lower boundary of the ionosphere dropped suddenly for 5 minutes from 85 to 60 kilometers, which is normally where it is during daylight hours. This is when the high-energy photons from the sun support higher levels of air ionization. This was caused by the second giant gamma-ray burst recorded from the WASP 1900 plus 14 magnet, which triggered the events of 79. It's worth mentioning that by summer, the group had picked up on another rapid slowing of this one's rotation. This suggested that the magnetic field magnitude was on par with the first measurement. Thomson thought it was especially important that the measurements backed up the theory. As a theorist, I'm really happy that our work has been useful in planning a series of observations. As theorists in astronomy, we usually try to clarify things, systematize, and explain them after the fact. Sometimes our work is also important for justifying new experiments that would otherwise not have been performed. While scientists were looking for a scientific explanation of the nature of soft, repetitive gamma-ray bursts, another puzzle for astronomers working in the X-ray range was a phenomenon that had them scratching their heads. A year before the outburst reached Earth on March 5, 1979, NASA launched the Einstein X-1 Observatory, which was the first orbiting observatory that could focus X-rays from distant objects, along with many other probes. A wave of gamma rays hit it too, but it wasn't too badly damaged. However, in the same year, the Einstein H observatories made another discovery. It was already known that X-ray pulsars existed in pairs, and that their radiation was caused by the matter of the companion star aggregating. In December 1979, Philip Gregory and Greg Feynman of the University of British Columbia in Canada, who were using the observatory to study some radio pulsars, spotted a bright point source of X-ray emission in the constellation Shoal, about 10,000 light-years from Earth. This source looked like a gas cloud. Gregory and Feynman named 1 and 2259 plus 586 and suggested that this object was a neutron star inside its home. The supernova remnant was hundreds of times more luminous than the Sun in the X-ray range. Despite looking for a long time, astronomers never found a companion star in the Kosyaki constellation. This means that the source of its energy must be something else. The radiation couldn't be explained by the rotation of radio waves either. They didn't show up on the radar. And since the star rotates in 7 seconds, the rate of energy loss and the slowing down of the star's rotation are too small to explain how bright it is in the X-ray range. The reason for the new pulsar's emission remained a mystery. With better equipment, astronomers kept looking for the companion star, but didn't find it. It couldn't be spotted in deep optical observations, and the same was true when we tried to use a chronometer to detect the so-called pre-Perovskian frequency shift caused by the motion of two bodies relative to each other. Instead, astronomers have spotted 3 more single, extremely bright X-ray sources with a pulse descent period of around 6 seconds. The strongly magnetic neutron stars that we study in the X-ray range because of the aggression of the matter from the neighboring star rotate much faster. Given that we now have 4 new strange monsters to deal with, it's clear that we need to recognize that this is a new class of neutron stars. At a conference in La Jolla, California, in March 1995, Thomson and Duncan suggested that these pulsars might also be magnets. They dubbed them anomalous X-ray pulsars and CPIs. Thomson and Duncan gave an explanation. Young magnets, spinning and decelerating rapidly, should emit radio waves like a transient flywheel. The electric current causes their huge magnetic fields to slowly decay over 1,000 years, making the young magnets bright and continuously active sources of X-rays. For years, this model was just one of several acceptable theories, but Thomson and Duncan showed that if CPIs are in fact pair magnets, like sources of soft recurring gamma-ray bursts, they should occasionally exhibit bright flares that astronomers should be able to detect. However, researchers needed to come up with a new way to observe this phenomenon. The idea was actually conceived by Victoria Casper, an astrophysicist at McGill University in Montreal. The chronometer showed that XDs, like pulsars, have a very stable rotation. But just like pairs, they have powerful flares and brief glitches in the periodicity of the buckwheat rotation. Since then, astronomers have recorded lots of flashes from anomalous X-ray pulsars. The lines between them and GPS are so blurred that many people now refer to both as magnets. The bursts of radiation are usually of intermediate brightness, and they're only detected if someone happens to point an X-ray telescope at these sources. That's when the burst happens. Sometimes these sources are too faint for our wide-angle gamma-ray detectors, which are designed to look for really bright bursts, to detect them. Right now, only a few anomalous X-ray pulsars have been identified. One of them, which was also found in the Kosiaki constellation, gives off light in the visible part of the spectrum. As it spins, this very faint pulsar briefly appears and then disappears. Up until 2004, all the known magnets, there were about a dozen of them, were only detected because of their X-ray or gamma-ray emission. They all rotated slowly and were relatively close together. Most of them are in our galaxy. This piqued the interest of some radio astronomers who pointed a radio telescope at these magnetospheres. They decided to check if they were also emitting radio waves, but they didn't find anything. Starting in 2005, physicists started publishing research trying to explain why the pair's magnetospheres don't emit radio waves. It was thought that, compared to ordinary pulsars, their magnetic fields are so strong that some kind of quantum mechanical effect preventing radiation should show itself. Pulsations occur in neutron stars every 5 seconds, which is the same as the magnet's rotation period. The flashes were so bright that they were automatically labeled as radio frequency interference. This was the first time anyone had studied a magnet in the radio band, and it came as a complete surprise to those who had been studying pulsars. Why hadn't this source been spotted at a distance of 500 meters before? It turned out that before 2002, the neutron star was emitting very faint X-rays, but then it suddenly became 1,000 times brighter. It's not just a point source then, it's a pulsating source. It's a magnet. The astronomical community was taken aback. I'm sure there are others studying the radio waves of the magnetosphere. It seems they're not working at the moment, though. However, magnets' radio wave emission is different from that of typical radio pulsars. Typical pulsars have a stable magnetic field that's structured like a field, or like a conventional rod magnet with a north and south pole. Pulsar emission comes from regions near its magnetic poles, and radio waves travel along and are confined to magnetic lines of force. The brightness of the radiation is actually inversely proportional to the square of the frequency, which is called flux density. However, the specifics of these relationships vary slightly from one pulsar to the next. If you double the frequency of the observation, the brightness drops by about 100 times. If you double the frequency, say from 1 to 100 gigahertz, the flux will drop by a factor of 100 squared, or 10,000s. The flux density of a magnet's radio flux is basically independent of frequency. We started by increasing the frequency to a few gigahertz, then to 40 gigahertz, and then brought the wavelength down to about 1 millimeter, which seems pretty extreme. We've never done that with any pulsar, Comey said. Even so, we could still see the individual pulses coming from the magnet quite clearly. On top of that, the spectrum was pretty flat, which meant that at all frequencies, the radio flux stayed pretty consistent. The highest energy radiation was at the higher frequencies, around 100 gigahertz, not the lower frequencies. This is less than 1 gigahertz, which is similar to what we see with ordinary radio pulsars. In a regular single pulsar, the radio frequency radiation comes from the rotation of the neutron star. The X-ray and gamma-ray emission from the magnet is due to the decay of the magnetic field. While we don't know for sure how the magnet produces radio waves, it seems that the luminosity in the radio band is due to the rotation of the magnet. It seems likely that there's a connection between the activity of the magnet's crust, changes in the magnetic field, and failures of the star's rotation, which manifest themselves in changes in the radio emission. For instance, the radio waves from the first magnet weren't detected until 2003, but they appeared around the same time as the X-ray flare. One thing is for sure, whatever happened on the surface and inside the star that caused the X-ray flare, it also caused the radio emission, says Camillo. But why does he keep going? We don't really know the ins and outs of this process. Could the flare have caused the X-rays, leading to the formation of lots of charged particles near the star that move around it along the magnetic field lines? Or could it be that the magnetic field itself is being rearranged and compressed, and that this is somehow accelerating all the existing charged particles more strongly? Camilla kept an eye on this magnet for another 2 years, and then she noticed that its radio emissions were getting weaker and weaker. It's impossible to know what we might have seen if we'd had the chance to observe it earlier. It might have been even brighter and more interesting, Camille says. We only picked up on the pulsations in B21006M, which was about 3 or 4 years after the X-ray flare. Meanwhile, the X-ray emission was getting weaker and weaker. When Camilla realized this, he also noticed that the average radio flux was decreasing. This magnet ceased to exist in 2008. Camilla was really disappointed, but he wasn't ready to give up hope. What if he suddenly came back to life? The only thing left to do was to wait and keep an eye out for other magnetas that might be studying radio waves. In June 2007, Camillo made another discovery, another magnet studying radio waves. More than 10 years later, another 2 were discovered by another group. In 2009, a survey of the Milky Way with the Parkes telescope found 3 magnets quite close to Earth, just 30,000 light-years away. The astronomers have named it Retired James 16, 22, 49, 50. At first it was thought to be a simple pulsar, but then it was realized that it is a slow, continuously slowing pulsar with a rotation period of 4 seconds. This means that, like a magnet, it has a large magnetic field. Scientists have determined that a magnet-like point source of X-rays is linked to it. Over the next few years, we'll be looking into this further. This source was observed with the Chandra X-ray telescope and was indeed seen in the X-ray range. Then, in 2014, it too died for 3 years. Camilo kept an eye on the first magnet radio for a few more years, checking it for a few minutes every couple of months, but it stayed dead. By April 26, 2017, Camilo was already in South Africa, working at the Mercado Observatory, which was still under construction. When the observatory first opened, it had 16 reflectors. When it was finished, there were 64. Camillo got a message in the mail just as he was leaving his office to catch a flight to Australia from Cape Town. The message included a quick summary of the magnet observations that his colleague had entered at Camillo's request using the Parkes telescope. He wrote, "For Fernando, magnet is still dead. The second magnet is up and running. It's still shining brightly. The third magnet is also shining very brightly." Camillo wondered how it could be glowing if it was already dead. At first, Camillo thought it was a mistake, but then he realized that if it wasn't, it meant the magnet had suddenly turned back on. He sent a quick reply to his colleague to ask him to keep an eye on the magnet in case he missed his flight. However, he replied that the Parkes telescope would soon be shut down for a month because part of its electronic system needed to be replaced. And on the flight back, I couldn't stop thinking about it. But what was the problem? He recalls that the source is in the southern hemisphere of the sky, and that Parkes is the only radio telescope in the world that can handle such a task. And then it suddenly hits him that he's the scientific director of a brand new telescope. The telescope isn't quite ready yet, but that's not an issue. Once I got to Australia, I sent emails to some of my colleagues in South Africa, Camillo said. Like obsessives, they made observations of this magnet for a few minutes each day, not only in radio but also in X-rays, with the help of the 4 X-ray telescopes, including Chandra, Swift, and Star. It was giving off a slightly different glow now, as its magnetic field had rearranged itself during the long period of inactivity. Camillo was amazed that the magnet had returned. Another magnet retired, James 17 and 22-0, discovered in 2013. It's well known for its location near the supermassive black hole at the center of the Milky Way. The discovery was a real shocker. The astronomers thought that, being so close to the tactical center and at relatively low radio frequencies, they wouldn't even be able to detect a pulsar, and they tried using a radio telescope too. They've been surveying this area for over 10 years, but haven't had any luck. The main goal has always been to find milliseconds of their pulsars, which can then be used as incredibly accurate clocks moving in fast orbits around the galactic center. To test the magnet's general theory of relativity, we don't need to worry about milliseconds of pulsars. It rotates every 76 seconds and has a magnetic field that reaches 10. It's got 14 Gauss degrees. Since magnetars are so uncommon, they're also pretty mysterious. It's understood that over a few thousand years, these X-ray sources will gradually fade. It's not yet clear how the magnetic field fades after the X-rays disappear. It's possible that the strong magnetic field remains in the star and that it's unlikely to fade. It's also more difficult to detect the magnet's radio emissions, which are already irregular. So, until the magnet comes back to life, it's really tough, if not impossible, to find it. Thomson says that searching for sporadic radio emissions is a promising way to find ancient magnetas, because the energy of the radio emissions that can be detected is very small compared to X-rays. We'll only be able to discover them with new, more sensitive radio telescopes, like the antennas of the Square Kilometre Array. It's thought that in a galaxy like our own Milky Way, one magnetar is born every 1,000 years. And since there are about 2 trillion galaxies in our universe, there are probably 2 lurking in space, multiplied by 10 to the 21 power, that are dormant with magnetas. Even the most outstanding ones will eventually awaken and be noticed by those who observe the sky. Over 1,000 of the known pulsars were discovered with the largest multi-beam survey of the galactic plane to date by the Parkes Radio Telescope, where the old-school Australian saucer is still in use. When Parkes started scanning in 1997, there were only about 700 known pulsars in the galactic plane. Just a year later, on November 5, 1997, the 1000 pulsar was added to the astronomers' list. This made headlines in many of the world's newspapers. The review wrapped up in March 2000, but we picked it back up again in December of that year. Firstly, the project was a huge success, and it was all down to a rather special instrument, a multi-beam receiver that was installed in the area of the Parkes dish in 1996. This receiver was also used in the Intermediate Galactic Latitude Survey done for the University of Technology and on many other occasions. In total, Parkes accounts for more than half of all known pulsars, including the famous and still unique double pulsar. The multi-beam receiver also discovered the first fast radio burst, or as Arby's calls them, a time burst. It's part of a new class of extremely powerful and short bursts in deep space, whose origin is still a mystery. The multi-beam receiver was originally developed to search for dim galaxies that can be identified by the characteristic spectral line of hydrogen atoms, which is 21 centimeters long. This wavelength, which is 1420 megahertz and falls into the microwave region of the spectrum, is where hydrogen atom gas can get through dust clouds that are opaque to visible light. But it didn't take long for astronomers to figure out that the multi-beam receiver, thanks to the radio telescope's much larger field of view, could be used to search for pulsars. When John Sarkisian, the on-site manager of the Parkes telescope, showed me the multi-beam receiver, my first thought was, wow, what a barrel. It's about 1 meter across and 1.5 meters high, and it looks like a metal barrel with a 6-carbon structure inside that has 13 small cylinders. It's a cross shape, and the temperature inside is 20 Kelvin during operation. This near absolute zero temperature helps get rid of noise and boosts sensitivity. The device used to measure the average temperature of the empty space between celestial bodies is around 73 Kelvin or minus 270, 42 degrees Celsius. The new beam receiver, which was kept in a small structure near the telescope, was replaced by astronomers with a better receiver because Parkes was tracking the Voyager 2 space probe leaving the solar system to observe pulsars at the time. It was later reinstalled, hanging high above the center of the antenna. One of the people who helped develop the new receiver is Andrew LeBigband, an experienced pulsar researcher and astronomer. He's the software and hardware guy in services, and he's responsible for making sure the receiver works properly. Not long after the new beam receiver was installed on the telescope in '99, Parkes was also put on the Hubble telescope with 4 holders. Before multi-beam receivers came along, most radio telescopes had just one horn, irradiation. When radio waves from far-off objects reach a pair of lower antennas, they bounce back and converge on the horn. One horn is exposed to the radiation, collects the signals, which are then amplified in receivers and converted into an electrical signal. With this setup, the telescope can only be pointed at one small area of the sky at a time, which makes it really time-consuming to observe large areas. This is where the multi-beam receiver comes in handy. The more persistent irradiations there are, the more areas of the sky the telescope can survey at the same time. This means that the whole sky can be covered much faster than with a single persistent wave irradiation. Each persistent receiver feeds into a separate receiver, and each persistent antenna has 2 polarization smart ray receivers. There are 13 persistent receivers, which means you get a total of 26 outputs. So the Parkes became a lot more than just a reflector. It effectively and cheaply became a radio telescope. Andrew Lyne was the one who came up with the idea of using the receiver to observe pulsars. He also developed one-by-one systems of analog filters to find them. Notes Matthews, an astronomer at the Humberto University of Technology. As we made gradual improvements, we ended up with sets of filters that had to be digital to survey the universe at high temporal resolution. Later on, these surveys were responsible for detecting the majority of the first 30 pulsars, which led to the conclusion that these mysterious bursts of radio emission were, in fact, real. Since 2004, we had a multi-beam receiver with 7 large irradiating forces. There are both at the Aristide Telescope in Puerto Rico and in China. The new Faust Giant Spherical Telescope has a 5-meter operator and a fixed main reflector. It's currently the largest radio telescope in the world. There's a strange subclass of unusual bright astronomical objects, a critical double system study in the X-ray range. They were first spotted in 2014, when astronomers detected pulsations that they thought were from a black hole. They're classified as ultra-bright X-ray sources, or X's, in the system. They've been around since 1980. At the time, astronomers first spotted extremely bright point X-ray sources that were brighter than 1 million suns across the board. A study from 2014 showed that at least some of these pulsations are from neutron stars. So far, we know of 6 such objects. As of September 2022, we know of 7 such objects. Lee Townsend, an astronomer at the University of Tomsk, first noticed the pulsations of one of these strange behemoths in 2016 when he spotted X-ray flares from the source. Townsend has been studying the object, which is a massive X-ray double system in the small cloud, for years. Its behavior matched what we'd expect to see from a normal X-ray exporting double system, and the emission was in line with what we'd anticipated. Out of nowhere, there was a massive flash that was 1,000 times brighter than anything we'd ever seen. It was also visible to Townsend in a way that put the object into X. This is one of the first times we've actually seen a normal X-ray double system transition into the X mode, according to Townsend. It's one of the few pieces of evidence we have that shows X-ray double systems can be linked to X. Townsend was amazed by the strength of the occultation, which was 10 to 20 times the Ellington limit, which defines the maximum luminosity based on a star's mass. Even today, we still don't know why this happened. Nobody really knows why these systems are so aggressive. Typically, the bursts of radiation from a single pulsar are so regular and so precisely synchronized that over decades, the stability of some of them can rival the precision of an atomic clock. Each pulsation happens at the same time every cycle or so, which makes the average pulsation profile pretty stable. This can be used to figure out when a burst reaches Earth. In about 10% of cases, though, when a pulsar moves into a double system with its companion, there might be slight but regular shifts in the arrival times of the pulsar pulses at the chronometer observation point. Sometimes, it's also said that this method of tracking the appearance of these pulses is a kind of timer. When the pulsar is orbiting around its companion and moving away from Earth, the wavelength of the pulses increases. We're seeing a redshift, and there are fewer of them being recorded every second. As the pulsar gets closer to Earth, the wavelength of the pulses gets shorter, and we can detect more of them every second. This is what's known as the doping effect. This is probably the most famous example of this effect in our daily lives. If an ambulance is moving fast towards us, the sound waves produced by the siren are compressed, which means that the wavelength of the sound decreases and the frequency of the pitch increases. The pulses are getting closer together. and we see and we see. But as soon as the ambulance picks up speed, the waves spread out and the pitch of the siren sound drops. Now, we can view the video. So, what's behind these changes in the time it takes for the signal to reach Earth? Normally, radiation travels in a straight line, but according to Einstein's general theory of relativity, when there's a strong gravitational field, like near-massive bodies, the fabric of space-time bends to match the curvature of space and the trajectories of photons. The denser the object, the more severe the curvature near it. Light. In 1919, Sir Arthur Eddington, director of the Astronomical Observatory at Cambridge, and the Astronomer Royal Sir Frank Watson, confirmed that the general theory of relativity was valid. During a total solar eclipse, they used a telescope to get an image of a patch of sky with the sun at the center and noted the position of the stars around it at the time of the picture. By comparing this image with one taken a couple of months later, when the sun was no longer near the same stars, they were able to see the curvature of light rays, the gravitational pull of the sun. When Einstein heard about this, he wrote to his mother, "I have some good news to share today. British expeditions have actually shown that light rays are bent out of curvature near the sun. It takes light longer to reach us than it would if it traveled in a straight line. The Pulsars companion bends the radiation on its way to Earth. The delay in sending the signal is called the Shapiro effect, which is the extra time it takes for the radiation to reach the telescope. By measuring these things and using Kepler's laws, we can figure out the orbits of both objects. This also helps us estimate the masses needed to create these orbits. The chronometer has been conducted for years by a variety of telescopes, including Ketcher in the UK, Parkes in Australia, FAST in China, the Green Bank Telescope in the US, and ALMA in Puerto Rico. It all started with a glitch in early March 1969. The pulsar had a seizure. Dick Manchester had just spent a full day at the Parkes telescope, which is located in Australia. He'd observed a pulsar that Alan Wolfgang and Michael Jr. had discovered using the telescope. Alan made his discovery just a few months earlier. Their discovery was the first to establish a direct link between neutrons in stars and supernova remnants. Manchester had been looking for the Army's pulse for about a year. He was a recent graduate from Australia's Newcastle University, who started working as a research associate at Parkes Observatory just 12 days before the journal article was published. On February 24, 1968, articles on the very first pulsation, PR by 1919 plus 21 or M1, armed with the coordinates of the pulsar M1 discovered by Jocelyn Bell, saw Manchester make his own observation of this object, which launched his career as a pulsar specialist. This is a diagram showing how radio pulses are emitted. You can even see these pulsars on Australia's first B-52. Polarization is probably easiest to understand using light waves as an example. The direction of the electric or magnetic field strength vector of non-polarized light waves, such as those coming from the sun, a lamp, or a campfire, changes randomly over time. But with a light wave, the direction of each vector is fixed. This is how these sunglasses are polarized. They have special coatings that let only vertically polarized light through and absorb horizontally polarized light. This helps you see the details of whatever you're looking at more clearly because it removes glare. Radio waves are also electromagnetic waves, just like light. They're not fundamentally different from light waves, even though they lie in a different region of the spectrum. Reich Krishna's observations on the radio wave polarization of the pulsars studied later backed up the pulsar model, which says that a beam of radio waves is ejected outward from the magnetic pole of the pulsar. Manchester was happy to help Cristiano. The pulsar was bright and, based on earlier observations, was thought to be emitting radio waves from it. Paralyzed and Rad, as agreed with Manchester, pointed Parkes' antenna at this pulsar. But then they hit a snag. The pulses were coming in more often than we thought they would. To put it another way, the pulsar's rotation period was measured with great precision. In the Parkes team's previous observations, it was just under 1/11th of a second, but this time it was 196 nanoseconds shorter. It was either the pulsar was spinning faster or the radio telescope was messing with them. That night, Rad was exhausted. He went to bed, leaving his young colleague to figure out if there was something wrong with the KOP radio telescope. Manchester spent the whole night double-checking the equipment. He even checked the rotation periods of other pulsars and saw that they hadn't changed. It looked like the equipment was fine. By the time dawn came, he'd finished checking everything and left a note. "I think something's wrong." It wasn't sparks. It was actually me. It all came down to the shaft ripple. It was no surprise that Manchester and Krishna were the first to spot Pulsar's signal. That is, a glitch, in this case consisting of a sudden change in the pulsation period by a tiny amount, just 2/millionths. But if we consider that even then astronomers were able to measure the periods of pulsars with great accuracy, this value was not insignificant. What's more, the period changed really quickly, probably in less than a second. As it turned out, a team at NASA's Jet Propulsion Laboratory in California also noticed the glitch a few weeks later. Thatcher's magazine ran 2 articles on the same day, one by Cristiano and Manchester, and the other by that group. We posted our article in the evening. Manchester says there was a bit of a dispute ahead of them about who saw the cry first. It's difficult to say exactly when the glitch occurred, but the folks at the Jet Propulsion Laboratory say the event happened between February 24th and March 3rd, 1969. So what caused the bitterness? Both teams thought that the pulse moment of inertia had suddenly decreased. This value shows how mass is distributed within the body. It's equal to the average of the mass times the square of the radius. It was clear that the radius of the ring had changed in the professor's case, but nobody could figure out how this glitch had happened. And the person who could have helped us out didn't even know about the discovery of the pulsar. It was Jess and Linda. As it turned out, the event had completely passed him by. That person was Gordon Geim of the University of Illinois, who was a visiting professor at the University of Tokyo in 1960, to pass the time on his daily commute from home to the office and back. On his way, he read a book by Soviet astrophysicist Iosif Shklovsky, The Universe, Life, Mind. He was doing physics and condensed their light. But Shklovsky's book piqued his interest in astrophysics. When Dan got back to Illinois a few months later, he found out about pulsars. He and his colleagues, David Pan, Chris Tretiak, and Joe Gavin Hall, threw themselves into studying neutron stars. They were theorists, so they wanted to get a good grasp on these new objects and figure out what they were made of. They were interested in them, in part, because they were studying the behavior of particles and phenomena such as superfluidity and dense forms of matter. These newly discovered neutron stars were incredibly dense. A number of both Cherry and Manchester, describing Greek pulsars, would soon come across the paper. Before Joe Bell made his groundbreaking discovery of the neutron star, only a few people had studied them. It's worth noting that in 1939, Oppenheimer and Volkoff calculated an upper limit on the mass of a neutron star of 7 solar masses. 10 years later, observations showed that the value was too low. In a 1959 paper, theoretical physicist Astor Cameron increased the mass limit to 2 solar masses. These papers pretty much cover it. At the time, not many researchers were interested in objects that seemed never to be discovered. Soviet physicist Arkady Kimik had a different take on it. He focused on studying dense matter, particularly atomic nuclei, and was the first to suggest that the atomic nucleus is a tiny version of a neutron star. Both objects are incredibly dense, which means that the matter in them is compressed into a very small space. On top of that, it's thought that a neutron star is more than twice as dense as the nucleus. But in a neutron star, it's thought that the atoms collapse rather than the mass being concentrated in the center as it is in an atom, with electrons forming clouds around it. Given the assumptions he made in his work back in 1259, this should result in a strange state known as superfluidity. This is probably the most incredible state that you can get very small objects described by quantum mechanics to be in. Normally, if there are no other forces at play, the flow of any fluid will inevitably slow down and come to a stop due to friction. For instance, when you spill water on the kitchen table, it stops after a few seconds, but the flowing liquid will continue to flow on top, As a matter of fact, this is what normally happens under normal conditions. Protons and neutrons are called clones together. They're independent thinkers and tend to avoid each other as much as possible. But at low enough temperatures, they form pairs. They start to act in a more coordinated way, moving together like a group of soldiers, and are in the same quantum state. This only happens with some atoms, and only when they're cooled to almost absolute zero. Collective quantum behavior allows superfluid to flow without friction and even climb up walls. This was all just theory until 1937. That year, Soviet physicist Pyotr Kapitsa made a significant discovery. He later persuaded Stalin to release Lev Landau from prison. Working with helium, he cooled it to see what would happen. A few years earlier, Kapitsa had worked at the Cavendish Laboratory in Cambridge with Ernest Rutherford. He'd gone there after losing his wife and 2 children to the Spanish flu epidemic in Russia. When he traveled briefly from England to Russia in the summer of 1934 to visit his mother and participate in a symposium, he was told he couldn't return to England without an explanation. Rutherford tried to help Kapitsa out and sent some equipment from Cambridge, which made it possible to set up a new institute in Moscow, the Institute of Physical Problems. One day in 1937, Kapitsa noticed a cold helium bath flowing through a tiny gap between 2 glass discs, about the size of a human hair. He discovered that at a temperature below 217 Kelvin, it is minus 270, 98 degrees Celsius, just 217 degrees above absolute zero. This temperature is known as the lambda point. The fluid flows pretty much without any friction. A paper on this phenomenon was published in the journal on January 8, 1938, and got the attention of scientists around the world. Helium below the lambda point goes into a special state that can be called superfluid, Kapitsa wrote in his paper. So Landau, who was released from prison in Formula 39, used the results of Kapitsa's experiment to create a theory based on them to explain superfluidity. Geim and his colleagues were familiar with the work of Kapitsa and Landau. They also knew little about the work that showed, because of the enormous density of neutron stars, their nuclei could be superfluid. They had just learned of the discovery of the first 4 neutron stars, which made these objects seem very real. When Gavin Hall and another colleague, Huberman, learned more about pulsars and then read about the discovery by Manchester, they realized that Galich might be the first proof that the conjecture was correct. It was probably the case that the cores of these newly discovered rapidly rotating neutron stars had a flowing liquid hiding beneath the solid crust above. The disruption could be caused by tiny whirlpools called quantum winds emerging above the flowing liquid. In 1947, physicist Lars He predicted the existence of quantum vortices while studying supercurrent helium. The theory was then developed by Nobel laureate Phil Anderson and theoretical physicist Richard Packard. We gave the vortex hypothesis a new lease on life. It turned out that this idea was the first hypothesis to be backed up by observations, he says. The physics of neutron stars is pretty unusual. In the 5 decades since, scientists have never been able to figure out what goes on inside these superdense objects. We can't just fly to one of them, drill a hole, and take a look inside. What I'm about to tell you isn't science fiction, but it's not quite science fact either. The issue is that the physical conditions that govern how matter behaves inside neutron stars are so extreme that our models have a hard time explaining them. What we've learned so far is already pretty amazing. When a proton-neutron star is first born from a supernova, it's extremely hot. The temperature inside is a whopping 1,000 billion degrees Celsius. In just a minute, the protons inside it start to turn into neutrons, which ejects a ton of neutrinos. As the neutrinos fly away, they take energy with them. As a result, the star's interior cools rapidly to around 1 billion degrees, while its outer layer becomes much colder. When the temperature reaches around 500,000 degrees, a solid crust begins to form. Over the next few decades, the neutron star keeps cooling. The star's internal temperature drops to a few 100,000 degrees, and it continues to lose heat slowly for another few 100,000 years. Meanwhile, heat from the inside gradually rises to the surface and then dissipates as radiation. A neutron star is like an egg, but spherical. Think of it as a magnifying glass, albumin and yolk. The solid crust, which is about 1 kilometer thick, is made up of iron nuclei from the same material that was in the core of the star before it exploded as a supernova. Why is the crust made of iron? This is because iron is formed as part of a thermonuclear combustion process. In regular stars, it takes about 1,000 years. Hydrogen burns and turns into helium, which then turns into carbon, and so on. Eventually, silicon and stellar ash are formed. Iron. The iron core of the parent star can't produce more energy, which is why some people think the first outer layer of a neutron star is made of iron. On top of that, there's a thin layer of gas, about a kilometer thick, that makes up the atmosphere. The motions that drive the star's magnetospheric magnetic field start just above the atmosphere. These magnetic fields of rotating pulsars push jets of particles and powerful streams of radiation out into space. The crust of a neutron star is a pretty complex structure. As we move towards the core of the star, the density increases rapidly, which causes the physical properties of the crust to change. In the outer crust, which is made up of iron crystals, electrons behave in the way we're familiar with. In each iron atom, electrons orbit around the nucleus. As the density increases, though, the energy of the electrons rises, and they get squeezed into protons. When a negatively charged electron joins with a positively charged proton, the proton turns into a neutron and releases a neutrino. As we go deeper inside the star, more and more electrons are squeezed into the nucleus, and more neutrons are created. This process continues up to a point where there are so many neutrons in the nuclei that they start to leak out. This transition from the outer crust to the inner crust is what we call the neutron instability point. At this point, free neutrons start to pair up to form the neutrons above. A fluid with zero viscosity is the Vatican. Neutrons occur at a depth of over 300 meters at a density of about 4 times 10 to the 11th power grams per centimeter cubed, which is still less than the density inside heavy atomic nuclei when measured under Earth conditions. Thanks to experiments in a lab on Earth, we can be pretty sure that the assumptions just described are based on the well-studied laws of nuclear physics. The thing is, though, that the squeezing of neutrons out of heavy atomic nuclei doesn't actually happen on Earth. There just aren't enough neutrons in the Earth's nuclei to kick off the flow in the innermost part of the crust, which is just above the outer core. It's about 1/3 as dense as the center of an atomic nucleus. The nuclei are packed so tightly together that scientists think they're starting to change shape. Before, the nuclei were like little meatballs and scattered all over space. Now they're deformed and floating in a sea in the inner crust. The neutrons that escape from this process form a phase state that scientists have nicknamed nuclear noodles. This state gives rise to a variety of structures, including tubes, bubbles, and sheets. The spaghetti-like structures have been aptly named the New York and Lausanne by the researchers. Of course, these are mostly just theoretical ideas, since we can't actually take samples of the substance and examine them. There's actually lots of good evidence from experiments that nuclear fission happens under terrestrial conditions. This mechanism is similar to the one that leads to the formation of nuclear noodles in the outer core, which extends to a depth of about 10 kilometers. The density is so high that isolated nuclei can no longer exist there. Basically, all matter becomes a nuclear slime soup of neutrons, protons, electrons, and possibly exchanges of heavy electron relatives with neutrons in a supercurrent state. It's similar to supercurrent liquids at ultra-low temperatures on Earth. The temperature in the outer core is thought to be around 1 million degrees Celsius because of the high density. Given these conditions, it's possible to achieve a supercurrent state. Gordon Geim and his colleagues came up with a hypothesis about why the rotation period of the Bell pulsar failed. This allowed physicists to propose a mechanism for what is happening in the outer world. While they were running their experiments with supercurrent helium, the scientists realized that their ideas about quantum vortices were right on the money. Supercurrent fluids don't flow like ordinary fluids. They form tiny vortices that make the supercurrent fluid rotate. It's thought that as a neutron star slows down, the rotation speeds of its solid and liquid parts change at different rates. It seems that the outer crust is rotating more slowly, but the vortices are still rotating locally. This makes the supercurrent component rotate slightly faster than the crust. When the lag in the rotation of the outer crust becomes too large, the two systems will align in rotation. the vortex starts bouncing around, trying to realign its rotation. This instantly makes the crust spin faster, and the rotation of the whole star speeds up for a while. This is how Galich, which was first spotted by Disk Manchester in 1969, comes about. After a period of time, which could be weeks or even months, the current system reaches a new equilibrium, and the neutron star resumes its normal rotation speed. Just 5% of pulsars have been observed to glitch like this. The Bell pulsar is particularly interesting because it fails about once every 3 years. When I visited Parkes Observatory in February 2019, John Sarkeesian was really excited to tell me that he'd observed another ancient Bell pulsar just a few days before, on February 2nd. This Galich, like another that happened on December 12, 2016, was particularly interesting to astronomers because they noticed that just before the pulsars failed, they suddenly slowed down. This effect had never been observed before. As we get closer to the center of a neutron star, things start to look a bit strange and less defined. Scientists have no idea what's going on in the inner core of a neutron star or what kind of superdense matter we might find there. If we ever figure it out, we might understand how particles interact with each other. At these densities, it would also help us figure out the ultimate mass of a neutron star at the moment when the gravitational force equals the internal pressure, then exceeds it and turns the neutron star into a black hole. Ultimately, we could grasp what occurs in the final moments before neutron stars merge. But how do we get inside a neutron star? The discovery of pulsars brought together two fields of physics that had developed in parallel: nuclear physics and astrophysics. They used radio, optical, and the very first X-ray observations, which quickly became a key tool for detecting thermal emission from the surface of pulsars. In the same year that the first pulsar was discovered, 1967, nuclear physicists at Stanford's Linear Accelerator Center started work that led to a few years later to the experimental discovery of quarks. Quarks are the building blocks of matter. Normally, triplets of quarks are held together by the bonding ions of their strong nuclear interaction carriers. These three quarks are the building blocks of ordinary matter, like the protons and neutrons in atoms. Quarks can't exist on their own, so we only deal with them in combination. Since they've been confirmed, physicists have been using all their creativity to come up with various models of superdense matter in the inner core of neutron stars. Some scientists think that the inner core is mostly made up of neutrons that have stayed intact even in high-density conditions. But according to Slavka Bogdanov, an astrophysicist at Columbia University, this model is the most standard and boring. Nothing out of the ordinary is taking place. It's still the same basic stuff, just neutrons, electrons, and protons, all packed together in a small space. Other models suggest that the neutrons don't stick around as they are, but decay into their component quarks. This makes the nucleus a soup of free quarks. This is the model for how quarks and the nucleus work together. Another idea is that quarks that are no longer bound within neutrons come together and form other more unusual shapes, such as hyperbolas. These particles are made up of one of the three quantum particles that make up a neutron, which has been changed to a strange quark. Normal protons and neutrons are made from top and bottom quarks, which are pretty normal themselves. Another idea is that high pressure causes particle clones with two quarks, one of which is strange to form. Or it could be something completely different. Theories like quantum chromodynamics are useful for understanding how quarks and nuclei behave. Unfortunately, it's really difficult to extend the apparatus to cold, ultra-dense environments, so we don't yet have a way to apply it and answer our questions. To figure this out, scientists have turned to the so-called equation of state for the inner core. This describes the relationship between the energy density and pressure of matter in the inner core. From this, we can derive the relationship between the mass and radius of a neutron star. There are lots of these kinds of relationships, and lots of models have been built to show what might happen in the inner core as a function of mass and radius. Different types of matter respond differently to gravitational compression. Let's picture the inner core as a ball. It can be either dense and hard, like a baseball, which is difficult to compress, or soft and pliable, like an inflatable. The two swords behave differently because they're made of different materials. If you have two neutron stars of the same mass, the larger one will have more mass. The denser core will have the greater radius. Since the star is larger, gravity will compress the matter more. This means the core must be able to withstand more pressure. Otherwise, the star will adapt into a black hole core, similar to a baseball can put out. If a star of the same mass has a core that is less dense or soft and can be compressed by gravity, it must be smaller to be able to resist that compression. Some scientists believe that neutron stars with a hard core, which is described by the hard equation of state, are likely to contain undeformed neutrons, but only very densely packed smaller stars with a looser core. The states described by the soft equation of state may contain free quarks in different configurations. This is because the formation of hyperons and free quarks in different configurations also leads to lower pressure. But there's still some debate around this question. To figure out what the nucleus is made of, scientists need to figure out how big a neutron star of a given radius can be. First, they need to measure the radius and mass of the neutron star using observations. Then, using these values, create an equation of state and, as you do the calculations, get rid of models that don't accurately describe the matter that the nucleus might be made of. The model is most constrained by the measurement of large masses, so the larger the mass of the star, the better. Theory allows for a maximum mass for each equation of state, and this must match what we observe. The heaviest neutron star we know of is WASP J0740 plus 6,620, which weighs 66, 20 solar masses, and is 214 times the mass of our Sun. It was discovered in 2012 using the Green Bank telescope. Before that, the record was held by the star PARP J16142230, which has a mass of 97 solar masses. Another pulsar with a mass of around 2 solar masses was discovered in 2013. These findings ruled out theories that used a soft equation of state for particularly loose neutron stars. These theories predicted that stars with masses around 2 solar masses should activate into black holes. Some models that assumed the inner core consisted of pockets or hyperions were also affected by this constraint. Scientists have discussed the Perron's mystery, wondering if we should say goodbye to the idea of Perrons being present in inner cores. In newer models, where phase transitions from one state of matter to another are sometimes assumed, Perrons are still thought to exist. When did you and Lee make the discovery about neutron star mergers? Scientists have figured out that the biggest a neutron star can get before it turns into a black hole is this much mass. My best guess is that it had about 217 solar masses. The mass of the current, huge monster with J equals sign 0, 40 plus 6620 is already pretty close to that value. One issue is that the lowest observed mass of a stellar black hole is much larger than about 5 solar masses. Some scientists think that a neutron star whose mass is above the upper limit might have started out as a hypothetical quark star with an intermediate mass. The word hypothetical in the title suggests that no such star has been discovered yet. For scientists, all of this is a pretty complex puzzle that still needs to be solved. Ultimately, none of the current models provide definitive answers about what lies at the core of a neutron star. To get new, more accurate values for the masses and radii of stars, scientists are still gathering data from telescope observations, particle detectors, gravitational wave detectors, and even a special device on the International Space Station. With each new data set, they get another piece of the puzzle, filling in a gap in our knowledge. Sometimes a series of lucky coincidences leads to a scientific discovery, like when your last name starts with the same letter as a Nobel laureate's last name, so you share a university email account. It's hard to believe that places like the Niels Bohr Institute at the University of Copenhagen used to have mailboxes signed with letters from and to in this age of email. It was in 1970 that Gordon Geim was working at the University of Copenhagen. Just a year earlier, he and his colleagues had written the first astrophysics paper arguing that observed pulsar rotations in period pulsars were evidence of the existence of superfluid inside neutron stars. And now he was going through his mail, sorted by letter, looking for anything that might be addressed to him, when he came across a postcard addressed to Hans. It was only 3 years ago. In 1967, Bethe won the Nobel Prize for discovering the energy sources of stars. I turned the postcard over and read the message, Babe said. It was from the journal Astronomy and Astrophysics. The editors were sending their thanks for sending me an article on neutron stars. After reading the postcard, I learned 2 things. The first thing I learned was that it was about neutrons and stars. The second thing I learned was that he was visiting Copenhagen. He was excited because he was going to meet a Nobel laureate with his friend and colleague, Chris Critic. He managed to get a copy of the article. I hope to have it all figured out by the time the author arrives, and to be able to have a joint discussion with him. When they read it, they found some mistakes in the article. They tried to improve the model, but in the end, they decided that the beta theory wasn't right. When the Nobel laureate arrived, the friends approached him and let him know that the conclusions in his paper seemed to be wrong. Babe recalled, and then he said in his great German accent, "We need to find a solution." So we sat down with the leading expert in nuclear physics to discuss the issue. That experience really changed the course of our scientific journey. From that point on, neutron stars and nuclear physics were inextricably linked for Geim. He set out to figure out what was really going on in these small, dense, rapidly spinning objects in deep space. He zeroed in on the inner core, since a lot of equations of state assumed the existence of free quarks in various combinations. BM wondered if it would be possible to smash neutrons and release quarks, and then study the resulting soup, which might be as close as possible to the matter of the inner core. The universe was in a similar state just a few millionths of a second after the Big Bang, when protons and neutrons hadn't formed yet. So, this early universe was basically a quark soup, a kind of soup of strange particles. Geim and other theorists, including James and Larry Mackler, had ideas about how to get free quarks on Earth. They figured the best way was to collide heavy ions, like lead or gold nuclei, head-on, by accelerating them first in particle gas pedals to high speeds. By doing this, we can use very sensitive detectors to find out exactly when the free quarks that form the plasma appear. Even if the quarks existed in a free state for just a split second before clumping together again, we could get a sense of what matter might be inside the core of a neutron star. To make this happen, he and his colleagues needed a bit of a boost. Luckily, they were able to draw on the expertise of one failed project that had been overlooked. It was 1982, and he'd just been appointed to the Nuclear Physics Advisory Committee. It was an executive body that put together reports for the U.S. Department of Energy and the National Science Foundation. The committee was talking about which nuclear physics facility should get the funding first. At the same time, he was also heading up a subcommittee on future research into dense matter, and then, in July 1983, something amazing happened. Well, at least in terms of that. It had been over 10 years since construction of the Isabel gas pedal had begun. And then the scientists at Brookhaven National Laboratory in New York realized that the magnets for this high-energy proton gas pedal weren't going to be able to produce protons. We need to think about the magnetic fields. Isabel is an acronym that combines counter-beam gas pedal with the French word for handsome. Isabel also told me that it's the name of a yacht owned by John Blue, who's a gas pedal specialist from the Vienna lab. Instead of finishing Isabel's project, the scientists decided to lobby for the construction of a more powerful superconducting supercollider. And this project was shelved in 1993 because CERN had already launched an alternative project, the Large Hadron Collider. On the French-Swiss border, scientists put the project on ice and forgot about it, even though they'd already spent $200 million on it. It was clear to Geim what needed to be done. Instead of giving a presentation on the proposed dense matter research, he showed how another type of collider, using heavy ions, could be placed in the already completed tunnel. The construction was basically done except for the magnets. He and a few colleagues thought it would be a great idea to build the gas pedal in Vienna after all. That's how he suddenly started thinking about building a gas pedal. BM was thrilled. He was telling me that the Alice Relativistic Heavy Ion Collider would help us understand the nature of matter that existed in the early universe before stars and planets formed, namely quarks and matter. I also said that WASP Alice would tell us a lot about neutron stars, which led to the creation of the Relativistic Heavy Ion Collider. A few years passed, and both the Alice and WASP Alice gas pedals were finally built. The results didn't start coming in until 2000. That same year, the first beams at HC began colliding lead ions, and their collisions produced record-high temperatures of 5 trillion degrees, nearly 400,000 times the temperature at the center of the Sun. At the WASP-Alice collider, gold ions collided with each other. When Geim found out in 2003 that quark plasma had been produced at Alice, and it was quickly catching up with the Vienna gas pedal in that area, he was really excited. He later commented, "In a sense, we always knew it had to have formed here. It's tough to wrap your head around this brand new matter that scientists have been able to produce. Just try to picture dividing a second by 10 to the 23rd power. The quark plasma you've created will only exist for one frame, and it's so small it could fit inside a virus for just 10 to minus 23rds of a second. This is the longest quarks can stay free. After that, they quickly regroup into protons, neutrons, mesons, and other particles. There's one issue, though. The temperature in the core of a neutron star is well below the temperature at which a collision occurs. In the collider in Alice, the temperature is close to what it was just after the Big Bang. From the start, Barium knew these colliders wouldn't reach the temperatures needed to create superfluidity, which are much lower than those in the core of a neutron star. He says that you simply can't see the light in fluidity in heavy ion experiments. He continues, sighing, "Temperature is a huge problem, so scientists only have to try to extrapolate their results to lower temperatures. It's a bit like trying to understand the properties of a vapor by studying ice. But it's still interesting to see what we can learn from these collisions. They seem to show a lot of similarities to the matter of a neutron star at the moment it forms from a supernova. The newborn neutron star hasn't had a chance to cool down yet, and these collisions could help scientists understand what happens when two neutron stars collide. After all, their remnant, formed after a terrifying explosion, is incredibly hot. And let's not forget Alice. Now, a new experiment is being built in Darmstadt, Germany, which is supposed to create quark clay plasma at the same temperature that exists in the core of a neutron star. We're kicking things off in 2024. The experiments at this gas pedal will compress matter and collide nuclei at high energies, pressing them against each other. The idea is to create very dense matter in a very small volume. Fireball. The gas pedal is now expected to open in 2025, and this fireball will explode. The explosion will produce about 1,000 particles that will decay into electrons, positrons, and smaller particles. The idea behind this project is to study ions because they aren't affected by the strong interactions that hold quarks together. It could also help us understand how nuclear matter behaves, at densities as high as you'd find in the cores of neutron stars. Right now, though, the best we can do with heavy ion collision data is extrapolate it to low temperatures. But of course, this extrapolation isn't enough to get all the constraints that are imposed on the quantities that enter the equation of state, or to rule out irrelevant models. To do this, we need to know the density and pressure, and therefore the mass and radius of the neutron star. One way to measure the mass is to use a chronometer to time the pulses from pulsars. Astronomers all over the world are timing out pulsars with a lot of different radio telescopes, but the best tool for timing out pulsars is located in a remote area of northwestern South Africa. By 2020, both parts of the observatory and Equipe and Mercado will start scanning the sky many times faster than all other radio telescopes, and over such a wide range of frequencies that they'll be 50 times more sensitive than all other radio observatories combined. The plan is that once this observatory is up and running, scientists will be able to detect more radio wave objects, particularly pulsars and burst sources, than ever before, and with much better resolution. Another goal is to search for and understand dark energy, the mysterious force thought to be responsible for the accelerated expansion of the universe. The telescope system will also be used to study how the first stars and galaxies formed. gaining insight into the magnetic fields that permeate the entire cosmos, and will even be on the lookout for signs of other intelligent life in the universe. The observatory will also be great for figuring out the masses of neutron stars based on the timing of pulsars. The first measurement of a neutron star mass was made with the Alice telescope. It all started in 1974, which was the same year that Anthony Hughes was awarded the Nobel Prize in Physics for discovering pulsars. Astronomers Russell Allen Haas and Joseph Cotton Taylor were working in the jungles of Puerto Rico in a tiny control room next to a 305-meter diameter antenna dish set in a natural depression in the ground. They made an exciting discovery: a pulsar, a new neutron star spinning at 17 revolutions per second. After observing the pulsar, they noticed some pretty strange but regular variations in the timing of the pulses. Sometimes it happened a little earlier than expected, and sometimes it happened a little later. The astronomers did some simple math and logical deductions, and they figured out that there was a second body orbiting with the pulsars around their common center of mass. This was the first proof that a pulsar in a double system, where the neutron star wasn't on its own, existed. They later discovered that the second component was also a neutron star, rather than a white dwarf. Over the next few years, though, it was the white dwarf that was seen more often as a companion to a neutron star. On top of that, Haas and Taylor's observations gave us the first accurate measurement of a neutron star's mass. They discovered that the masses of the neutron stars in the double system were about 4 solar masses, and 144 for the pulsar, 139 for the companion neutron star. The values of both masses were pretty close to the Chandra-Cecilia limit. This pulsar is now known as Taylor and Taylor's pulsar, B1513 plus 16. So far, astronomers have used pulsar timing to figure out the masses of about 35 neutron stars, ranging from 117 to just over 2 solar masses. The team at Cairo Observatory has started using pulsar timing as part of a project called World of Time. Fernando Camilo, an astronomer at the South African Astronomical Observatory, says that observing known pulsars with this antenna system is no longer necessary. The observatory's other telescopes, Mir, Cat, and Parcas, are in the southern hemisphere. The Cairo system antenna can focus on pulsars that have been detected over the years by the Parkes telescope, but that cannot be seen by the Green Bank telescope, which is in the north. Camilo says that from the Parkes observations, the mass of a neutron star is often calculated with a large error, and thanks to the sensitivity of the Cat measures, we can make these measurements much better and faster. Just picture this. You can observe 20 well-known double systems with the Merc, and within a year or less, you can really accurately measure 2 or 3 large masses. That could make a big impact. However, measuring masses alone isn't enough. Scientists are also trying to get a really accurate measurement of the radius of neutron stars to find constraints on their equation of state. But getting an accurate measurement of the radius is a bit more challenging. A team of researchers led by Michael Kramer, director of radio at the Max Planck Astronomical Institute in Germany, has been trying for years to use data on the only known double system formed by the 2 poles of a double pulsar to find limits on a neutron star's moment of inertia, which is a function of mass and radius. Since we already know the masses, we can get some idea of the radius from this. However, the most accurate size estimates are based on observations of the brightness of the total X-ray flux from the surface of the pulsars and taking into account the known distance to Earth. This isn't a simple calculation, but it has allowed astronomers to determine values of radii that agree with the best theories. We're going to be describing neutron stars. Scientists think neutron stars are about 9 to 11, 2 kilometers wide, but some are probably closer to 14 kilometers. Another way to find the radius is to observe very rapidly rotating pulsars, with the understanding that the largest mass measurement represents the upper limit on the radius. So far, only one measurement of the upper limit value of the radius has been made. The current record holder for spin rate was observed in the fall of 2004 by Canadian Jason Hess, who was then a graduate student at McGill University. Hess used a telescope to make his observations as part of his thesis. Greenberg. This thesis was partly based on the results of a search for millisecond pulsars in the Quasars star cluster. Tarzan 5 is about 18,000 light-years from Earth in the Sagittarius constellation. He knew that at least 20 millisecond pulsars were located in this cluster. This is where one of the most famous pulsar factories is located. I was keen to find others that hadn't been discovered yet. On November 10th, 2004, Jesus recorded repeated pulses of radiation that came so tightly one after another that he realized it was a neutron star spinning very fast. The issue was that it only showed up once and then disappeared. Day after day, month after month, but it never came back. His colleagues started to think it might be a phantom. But Jesus, who is now working at the University of Amsterdam, didn't give up. He figured the pulsar might have been eclipsed by another star, and he hid behind it, and all that junk in the double system that the pulsar makes, which is invisible from time to time. After about a year, he saw the pulsar again, and it was the fastest spinning pulsar discovered so far. It was later named WASP-J 174824446 Eddy, and found to spin at a rate of 716 revolutions per second. It was moving at a speed far in excess of the previous record of 642 revolutions per second in a period of 155 milliseconds. For the pulsar, WASP 1937 plus 21. This pulsar was first spotted by astronomer John Baker in 1982. It was the first millisecond pulsar to be discovered, and it's now thought to be about 200 million years old. The record-breaking rotational velocity wasn't the only thing Jesus discovered. He also figured out the upper limit for the radius of this neutron star from a distant cluster. If the pulsar's radius was even slightly larger than this value, Jesus said, it would have to be spinning so fast that the matter that makes it up would fly off its surface and the pulsar would vaporize. Jesus couldn't measure the mass, but by using the largest pulsar mass we've measured so far, which is about 2 solar masses, and its rotational velocity, he found that the radius of the pulsar couldn't have been more than 16 kilometers. The 2 typical masses for pulsars are equal to 1, 4 solar masses. The upper limit on the radius is 14 kilometers. Since then, I've been on a mission to find a pulsar spinning even faster. I'm hoping to also measure the mass and find the constraints imposed on its equation of state. While we've been observing pulsars for decades, 2 new ways of measuring mass and radius have recently emerged, or otherwise. The NASA instrument was sent to the International Space Station in 2017. It's used to study the internal structure of neutron stars. It's a box that weighs 372 kilograms and is about the size of a dishwasher, with an X-ray telescope inside. It was launched on SpaceX's Falcon 9 rocket in June 2017 and reached the International Space Station. It took the astronauts a couple of days to use the robotic arms to attach it to the station. Now that the USSR has been used by scientists, including YouTube, it can be used to very accurately measure both the mass and radius of any nearly neutron star. On December 12, 2019, NASA shared the first results of the most precise mass and radius measurements of a pulse. It took NASA 4 years to put this instrument together. The NASA is designed to study single pulsars. It has 56 X-ray photon detectors inside it, which record the energy and momentum of the photons. Most pulsars emit radio waves and are made up of particles that are accelerated in the magnetosphere surrounding the neutron star. These particles have to come back to the surface to keep the star electrically neutral, so they probably reverse the current by hitting things. The surface is heated by the star's polar cap, which creates glowing hotspots that study X-ray waves. That's what NASA is here to do. Instead of recording all of the neutron star's X-rays, it tracks the exact shape of the pulses of X-rays from the hotspots, which depend on the neutron star's mass and radius. This is precisely what Watts was studying even before the USSR was designed one day, in 2015, by you. As luck would have it, she was in the NASA lab at the time. She was giving a presentation at MIT at the same time the USSR designers were testing the detector. She was interested in seeing what technological developments had been made and was allowed to take a look around the lab. The detectors are really delicate, so she had to wear a hazmat suit. She was also feeling a bit nervous because, as Watts joked, she was a bit clumsy. A year and a half later, she got an email from NASA. She was asked to join the team. She was interested in joining, but at the time she wasn't sure if her participation would be helpful. However, she did end up joining the team. Her theoretical work on hotspots suddenly became more important. Scientists had already spotted hotspots with earlier versions of X-ray detectors, but until now it hadn't been a priority in any of the projects. The plan was to see how the intensity of X-ray emission from a specific hotspot changes as the neutron star rotates. When this hotspot shows up in the field of view, it then disappears as the neutron star is a very dense object. The general theory of relativity suggests that the paths of photons studied by hotspots will curve out. The curvature will be so strong that when the star rotates, the light from the hotspots on its surface will curve around them. Meanwhile, Nye will be able to see these dots even when they're on the backside of the star from the Kremlin. The instrument tracks how the intensity changes over time and plots the relationship. This means we can predict exactly what pattern the observer will see. For a star with a certain mass, radius, and rotation rate, in our case, we're solving the inverse problem about the picture we've obtained. Based on the X-ray registration, we're making a conclusion about the star's mass and radius. It's a complex issue, so in addition to searching for new neutron stars, the USSR is also looking into known millisecond radio pulsars to register X-ray radiation pulses from them. This is if their mass has already been found using the timing of radio pulsars. You might think that half the job is already done, because at certain times of the year, the sun is in a position to approach known pulsars in the sky. Sometimes, astronomers have to deal with interference from photons being studied by the sun. We've had to trim some of the data to make sure we only use radiation coming in at certain angles to prevent that extra squelched sunlight, says Farr. The data from observing a few nearby millisecond pulsars seems to agree with previous measurements of their total X-ray emission from other telescopes, which is encouraging. The mass of a pair of observed pulsars, obtained from data on the timing of their radio pulses, was more than twice the mass of the sun. For such a large mass, the curvature of light due to gravity is so great that if the radius of the pulsar is small, the pulses cannot be registered. So by observing how the emission pulsates, we can set a lower limit on the radius. In other words, the minimum possible radius. The results, published by the Nasser team on December 12, 2019, are promising, but not yet precise enough to determine exactly what kind of dense matter might be inside the nucleus. It seems that the radius is right in the middle between the values predicted by nuclear physics and the current constraints in astrophysics. The good news for theorists is that they can relax for now. But says that with all this uncertainty and the fact that the radii don't match any of the limits scientists have estimated, they can't draw any firm conclusions about the composition of the inner core from these results. These results might change when the team looks at the data for the next star, since they can only study one pulsar with the USSR. Upcoming X-ray telescopes like STEP will be more precise at determining X-ray, time, and metric characteristics. The Czech Observatory's strobe-con spectroscopy with high temporal resolution for a wide X-ray range will also help us study and critique the pulsar. Hotspots form when material from a companion star is transported to the magnetic poles of the pulsar. Thermonuclear explosions in the oceans on the surface of a neutron star are another source of heat. The crust is the outer layer of a single neutron star. In critical stars, matter transferred from the companion is deposited on top of the crust, forming an outer liquid ocean. The next generation of detectors is already in the works. They'll be 10 to 20 times larger than the previous ones and are set to launch into space within the next 10 years. I know you're looking forward to that. She says a telescope like this will let scientists record sudden changes in the nucleus. This could help us understand what happens during those mysterious phase transitions of quarks. It's thought that quarks and matter change state in a similar way to how water changes from liquid to vapor or ice. However, it's not easy to assess these transitions of quarks because we still only understand the strong nuclear interaction. which binds quarks to each other with the help of ions approximately. How significant was the signal that was detected? It gave us a new way to figure out the constraints on the equation of state. To do this, the scientists needed more information. But at first, they only had the gravitational wave signal to work with. They were hoping to record how the rotation rate of the two stars changed during their deadly dance. Indeed, they move in coordinated orbits, initially orbiting slowly around a common center of mass. Over the course of 1 billion years, they move closer together and lose energy contributed by the gravitational waves. Eventually, the two stars merge when they come closer together and their orbital velocities increase. The orbital period is always changing, and scientists are using these changes to learn more about the neutron star system. As the neutron stars draw closer, they start to deform. As they get closer, each star stretches and compresses the other's matter, creating tides. As we know, the moon's gravity causes tides in the oceans. On Earth, and just as gravitational waves take away energy from two neutron stars, tides do the same, causing the stars to collide a little sooner than they would without the tides. Although the detectors weren't as effective then as they are now, and there was a lot of background noise, the signal was strong and clear enough to estimate how much gravitational energy is lost to tides and scattering. Orbital energies due to gravitational waves, MDs that form each star. Scientists have tried to put the data into an equation to get a better understanding of how stars resist the pressure and reach of induced gravity, which without it would be too much for them to handle. It's tough to predict the final density pressure, but it's really the relationship between pressure and density that determines the size of single stars and how stars are affected by tides. The smaller the strain, the more flexible the equation of state can be. This will also let us set an upper limit on a star's radius based on the recorded signal from the gravitational wave. The radius info is tucked away in a tiny correction due to tides brought in by gravitational waves, which depend mostly on the mass of the stars. There are two ways to find these masses. The most reliable way is to use what's called the chip mass, or a special combination of the masses of two stars, which you can get directly from the original signal frequency change. Once the scientists had calculated the additional effects and assumed that neutron stars rotate at typical speeds for observed pulsars, they calculated the masses. That gave us 146 and 127 solar masses. But Reed said that, so far, this method of determining the masses of the components of the double system isn't particularly accurate. It's a very promising method, but so far the masses of radio pulsars have been determined more accurately. Other scientists, including Nissan herself from the University of Amsterdam, have been working on observing the brightness of a clanova, which also allows them to determine the masses. All you have to do is count the mass ejected during the merger. The observations put a cap on the mass of a neutron star at around 1 to 2 solar masses. As the woman said, though, because of all the uncertainties associated with this method, it didn't end up being the best approach. The new masses in general create a huge mess with a lot of matter floating around. Next, Reed Hudson and other scientists used gravitational wave signals to calculate that stars can't have a radius greater than about 13.5 kilometers. This value is in line with previous X-ray measurements of radii, which suggests that tides haven't caused much deformation. The small radius helped us get rid of the most rigid equations of state, and it even predicted the existence of larger neutron stars. This suggests that the pressure is quite low. Hudson says we were able to rule out some models that assumed high pressures. If the stars were larger, the tidal forces would have a much stronger influence on their orbits, so the pressure inside couldn't have been high enough to make them bigger. Even so, there's still a need for high pressure to resist. The crush gives a gravitational force that's equal to 2 solar masses. This suggests that the pressure will increase a lot with increasing density, when we might see more neutron star mergers. Next, we need to collect more data on how they are deformed by the tides. This will help scientists understand how the radius changes as the mass changes, and see what equations of state predict the same changes in radius. Once we've got the masses and radii of several neutron stars nailed down, we can ditch the irrelevant equations of state. Even if we figure out the size of the stars, we won't know which particles inside them are creating the pressure. We're talking about non-decayed neutrons, free quarks, hyperbolas, compressed coronas, and so on. It's a bit more unusual. Put simply, the same mass and radius can accommodate both quarks and neutrons inside a star. Knowing the magnitude of the pressure doesn't necessarily tell us what the star is made of. So the challenge will be to analyze the different structures that can cause this pressure. Once we've got all the pieces of the puzzle, we can start to put them together. For instance, we can look for phase transitions in quarks and matter by observing more neutron star mergers. As we learn more about how pressure changes, we'll also understand how the radius of a star changes with mass. Scientists think that neutron stars with masses within a certain range will have roughly the same radius of pressure. How big a star's pressure inside is depends on what matter its interior is made of. The usual particle ions contain strange quarks, or perhaps there's even a soup of quarks in there. It's tough to figure out which particles match the radii we're seeing because of how complex their interactions are, according to Reid. But if stars are going to have such small radii and still be so massive, it might mean that there's something more exotic going on than just neutrons. If they find a star with a smaller mass and a larger radius than we currently accept, the upper limits of A Lagoida will find a star with a larger mass and a smaller radius. This could mean that something really interesting is happening to the particles in the core of the star. It would tell us a lot about what kind of matter creates the right kind of pressure and constraints on the type of model. If these observations lead to two different points of view, two different types of neutron stars, we could not only understand exactly how the equation of state behaves, but also figure out what particles or fundamental interactions make it behave that way, Hudson says. We could get rid of some of the models that don't add anything by putting together what we know about phase transitions, cooling rates, how different particles carry energy away when they emit, and how neutron stars slow down their spin over time. Experiments with quarks and plasma at future colliders could eventually give us a clearer picture of what's inside these dense bodies. But is it ever going to be possible to rule out all the other theories and stick with just one? Even though we're not totally sure about it today? From what I know about theoretical physicists, I'd say that's unlikely. The thing is, they're always building new theoretical models to explain observations. This is particularly true if the observations contradict an existing viewpoint. We might be able to rule out some extreme models like large quarks and nuclei, but there's always the possibility that there are just a few quarks in the nucleus. It's impossible to rule out all the gas, dust, 1 million stars, some number of pulsars, and a monster black hole that's several 1 million times more massive than our sun. This is roughly what the center of our galaxy looks like. This is where the heart of the Milky Way beats, and all the stars and planets have been orbiting around it for 5 billion years. This area is very crowded. It's so densely populated that it's impossible to see anything with optical telescopes. Visible light often can't get through all this dust and gas. Luckily, infrared wavelengths and longer wavelengths of new radiation managed to do so, and they told us that in addition to gas, there are old red giants living there, as well as several 1 billion younger massive stars that will explode supernovae in many 1,000 years. Just before the official opening of the Meerkat radio telescope in North Africa on July 13, 2018, astronomers took a quick look at the center of the galaxy and took a picture. The result was a clear and detailed image of the center of the Milky Way. It's the best image we've ever gotten. It looks like a picture of a campfire or a burning furnace. There are filaments of fire stretching out in all directions. The strange round clouds on the left side of the image look like smoke coming out of a chimney. There are two huge radio bubbles. One is stretching its neck upward, the other downward. It looks like an hourglass of mating monsters. At the center is a supermassive Sagittarius black hole, but there's more. It seems that the center reveals another secret, some matter that is completely invisible to all our instruments. The mass of this unusual substance is thought to be 5 times that of the usual matter made up of atoms, which scientists call pregnant matter, the stuff we're all familiar with. This is the same matter that forms stars and planets, You, me, and even my cat Quark. We don't know what this mysterious matter is. It was first introduced into the theory by physicist Fritz Zwicky of the California Institute of Technology, who noticed that it was needed to explain the observed motion of stars and galaxies. So now we just call it dark matter. Roughly 23% of the universe is made up of dark matter, 72% is mysterious dark energy, and just under 5% is ordinary matter. There's just one issue. It seems that every time scientists think they found the key to understanding dark matter, they're faced with the same old challenge that knocks their theories back to square one. The neutron star is the one that gets in the way. Most astronomers think there's enough evidence to suggest that dark matter is real. They can see how its gravity attracts stars and how it binds light that passes near it, and it all fits together nicely. But only if you accept that Albert Einstein's general theory of relativity is right when it says that gravity is a property of massive objects, and it also binds together space and time. There are other theories of gravity that try to explain the structure of our universe without assuming the existence of dark matter or dark energy. But these theories are up against some tough challenges, especially when it comes to intact stars. Even so, if the general theory of relativity is right, we can't explain how ordinary matter moves under gravity without assuming dark matter exists, as is the case with many other theories that seem far-fetched at first glance. And it all started with Junkyard, who in 1933 first suggested there might be a link between neutron stars and supernovae. At the same time, he was looking at galaxies and galaxy clusters that were similar to our own. The local group, which includes the Milky Way, the Andromeda Galaxy, and many other dwarf galaxies, knew that galaxies in a cluster orbit around the cluster's center of mass as well as its axis, and also interact with each other. But he wanted to see for himself. He got his colleagues to build an 18-inch telescope with a wide field of view and took pictures of the galaxy clusters. Veronica's hair coma is about 323 million light-years away from Earth. This cluster is home to more than 1,000 galaxies. Each image that Color took turned out to have more and more galaxies. He also summarized the luminous star matter and gas that he was able to discern in the telescope in the cluster. He also worked out the speed of the galaxies and saw that the cluster was much more massive than the total mass of the luminous matter. The results were pretty surprising. The galaxies seemed to be moving too fast for the calculated mass to remain bound together in a single cluster by gravitational forces. With such a small mass of luminous matter and the gravity it created, it was unlikely that the galaxies would stay together. Shouldn't clusters of galaxies have simply disintegrated? On the other hand, the observed gravitational forces required the presence of 400 times more matter, which Zwicky called excess matter. That's what we call dark matter. Zwicky's theory didn't get much attention until recently, but the name stuck around. It wasn't until 970 years later that scientists realized Flowers was right. Two American astronomers, Vera Rubin and Kent Ford, calculated the mass of our neighboring galaxy Andromeda by measuring the speed of its stars. As with Flowers in the coma cluster situation, they discovered irregularities. The Andromeda Galaxy is a spiral galaxy, similar to our own Milky Way. It has a galactic bulge and a disk filled with interstellar gas and stars. Before Rubin's work, astronomers thought that stars rotated faster the closer they were to the galactic center. They also assumed that spiral arms farther away moved more slowly because of the weaker gravity. However, Ruby saw that this wasn't actually the case. The stars on the outskirts of the galaxy were moving at the same speed as those closer to the center of the Andromeda Galaxy. This meant that the galaxy must be filled with something invisible, with enough gravity to hold the whole system together. Some dark matter, which helps ordinary matter move at the same speed throughout the galaxy. Rubin and Ford later did similar calculations for many other galaxies and showed that the planes of rotation curves seen in all the galaxies they examined provided a convincing argument for the existence of dark matter. This was a turning point in the debate over this invisible substance. It's now thought that dark matter takes the form of huge spherical clouds across the universe, with one or more galaxies floating within each cloud. These formations, which resemble futuristic cities in the sky, are called dark matter halos. Later on, astronomers saw more proof that dark matter exists. This is because light in space is bent in certain ways. This is what's known as gravitational lensing. When we look at a faraway galaxy, we often see it distorted, like an arc. Sometimes, instead of seeing one object that we know should be there, we see several images of it. This is because there might be, for instance, clusters of galaxies that act like giant lenses between the object we're observing and the Earth. Even the lenses at the Kremlin can still bend light rays, but if we add up the mass of all the stars in this cluster based on how much light we're seeing, we realize that with such a large cluster, the curvature should be almost undetectable. In reality, the image of a distant galaxy shouldn't be so distorted. When astronomers try to model the distortion they see in reality on a computer, they often have to increase the mass, model the cluster 9 times the mass of the object between them, and only then everything fits together. This suggests that the cluster contains a lot more dark matter than we would normally expect. Despite spending $1 billion in 10 years with various detectors, scientists have not been able to find any direct evidence for the existence of dark matter. So far, attempts to produce it in high-energy particle collisions in accelerators like the Large Hadron Collider at CERN have not succeeded. While I was in Italy, I came across a laboratory that was hidden deep beneath the highest mountain in the Apennines. Qualcomm Grant is about an hour outside of Rome. In the lab, I was shown a giant tank that was about 10 meters in diameter and 11 meters high. It resembled a large granary. It's the most sensitive dark matter detector on the planet. Let's get the xenon ready. But even after 10 years of searching and working with it, as well as all the other detectors, the scientists haven't detected the signal they were looking for. And yet, astronomers aren't throwing in the towel. Based on what they've seen happen in gravity, they think that the densest concentration of dark matter around a galaxy or group of galaxies should be in the cluttered stuff of the galactic center. This assumption is based on the idea that, according to the accepted models of how galaxies formed in the early universe, the first halos of dark matter formed when gravity created a pure structure called the cosmic web, with dark matter at the nodes. These clumps are the halo of dark matter, which is a huge cloud that looks like an American soccer ball with the highest concentration of dark matter in the centers of galaxies. So the thinking is that if you're trying to find dark matter, the best place to look is the center of our galaxy. Dan Hooper, an astrophysicist at the University of Chicago, is well aware of this. He's been searching for dark matter throughout the Milky Way for the past 2 decades, looking for any signs that might prove its existence. Hooper has concentrated his search efforts on the center of our galaxy. He's also looking into the galactic plane, where most of the mass of our disk-shaped galaxy is located. But every time he thought he might have seen some sign of a dark matter signal, he was disappointed when a pulsar showed up. Sometimes they produce signals that look like the ones we're looking for from dark matter. They're kind of like dark matter antagonists, he jokes. When you see something unusual, what do you think it could be? Do you think there's a chance it could actually be a pulsar? The story of the battle between pulsars and dark matter started in the late 1990s when a ground-based detector in New Mexico picked up on extremely high energy diffusion, gamma rays from the entire galactic plane. Gamma radiation is the form of electromagnetic radiation with the highest energy we know of. The World Detector has recorded this radiation with a maximum energy of about 5 electrons, which is also known as 5 trillion electron volts. This is the energy gained by an electron in an electric field when it travels through a potential difference of 1 volt. Just to give you a frame of reference, in older TV sets with electron beam tubes, the electrons were given a boost of about 30,000 volts. That means that when they hit the screen, they had an energy of 30,000 electron volts, and the energy of 5 TV is about 100 million times greater. This also means that the speed of an electron with that energy is much higher than in electron tubes, almost reaching the speed of light. It's no surprise that the entire galactic plane is permeated with gamma rays. Gamma rays are produced when atomic nuclei decay. On Earth, they're created by nuclear explosions and lightning strikes. In space, they're created when cosmic rays, usually high-energy protons, interact with interstellar gas or when electrons are swept through starlight or galactic radiation fields. Gamma rays in space are also created in events that release a lot of energy, like supernovas. They're also created in the areas around black holes and neutron stars. But when scientists looked at the data from the Gamma Ray Observatory, they compared it to how much gamma rays should be generated in the galactic plane based on how many cosmic rays they'd observed. They were amazed to discover that there was at least 10 times more of this radiation than they expected. Later on, in 2006, another space experiment called Pamela, which was on a Russian satellite, found another particle that was present in excess. This time it was high-energy positrons, which are antiparticles and electrons. Scientists think that when the Big Bang happened, equal amounts of matter and antimatter were produced. But then, for some reason, matter ended up dominating antimatter. Today, there's hardly any antimatter left in the universe, although we can create it in labs, even on Earth. The magnetic field makes it so that we can't really pinpoint where these positrons are coming from. But Hopper knew that electrons, positrons, and pairs scatter starlight, giving up their energy and turning it into gamma rays with energies on the order of TeV. Could these two effects be related somehow, and what caused them? When the Pamela Project team published their data and demonstrated the positron excess, Hopper was quick to share his first thoughts with the scientific community. One idea was that the source of these extra positrons could be the dark matter he'd spent his whole career looking for. There are a few different ideas out there about what dark matter might be. One of the most widely accepted ideas is that dark matter is made up of weakly interacting massive particles. One type is the hypothetical neutrals. E. Hooper thought that these neutrals might sometimes collide, and in their annihilation, produce streams of exotic particles that can then decay into ordinary elementary particles, like electrons and positrons. This could explain the observed excess of positrons. If this is right, then these electrons and positrons, moving at almost the speed of light, spiral around the force lines of the galactic magnetic field. This creates what is known as SING radiation. It's electromagnetic wave radiation. These electrons are also scattered by the low-frequency photons that make up the light of the surrounding stars. This process, called reverse Compton rotation, converts these photons into high-energy gamma quanta. Hooper thought these might be signals of dark matter, but he wasn't sure, so he also considered another possibility, that the excess positrons could have been caused by pulsars. In this scenario, the strong magnetic fields of neutron stars orbiting with them create electric fields that pull electrons from the surface of pulsars and accelerate them. When these high-energy electrons hit the magnetic fields, they give off high-energy gamma quanta, just like in the dark matter scenario. And when they leave the pulsar's magnetic field and start moving through space, some of them can turn into electron-positron pairs as large as Hooper on their own. Many other physicists were interested in this problem. Over the next 10 years, more than 1,000 papers were published trying to explain this mystery. Most authors stuck to the pulsar hypothesis, but there was still some debate about the origin of the gamma rays. But to prove it, we need to see if these gamma rays emit themselves, and then figure out how many electrons and positrons it would take to produce that many high-energy gamma quanta. We also need to see if they can explain the observed excess. In 2017, Hopper and a few other colleagues figured out a way to solve this problem. They remembered another detector receiver at the Cherenkov High Altitude Observatory near Pueblo, Mexico. The construction was finished in 2015. The observatory has observed two neighboring pulsars, Domenko and Munk-Henrik. Some people just call it Munk, which is located less than 1,000 light-years from Earth. It's important that they're close by because electrons with energies on the order of TeV can't travel very far from the source. They lose most of their energy in the magnetic fields of our galaxy and also from starlight scattering. I discovered that the extensive halos around these two pulsars emit gamma rays of high electron volts per energy. It's thought that these gamma rays could have been created when high-energy electrons and positrons flying out of the pulsars interacted with low-energy photons and their nearby stars. In the collisions, the electrons could transfer a lot of energy to the photons, similar to how a golf club transfers energy to a sword, sending it to the other side of the course. The scientists looked at the FX data and figured out how bright both sources are. They compared the brightness of the two pulsars with the brightness of their halo to figure out how much of the pulsar's energy is converted into electrons and positrons. That percentage turned out to be about 10%, which Hooper said is almost enough to explain the observed excess of positrons. He said this was the final piece of the puzzle. There are about 3,000 radio pulsars in our galaxy, but most of them are either too dim or too far away. That means Higgs can't think of them as separate sources. If we assume that all pulsars are equally efficient at converting their kinetic energy into positron electrons, then when we add up the contributions of all the Milky Way pulsars, we see that they result in a gamma-ray signal with energies on the order of 2 electron volts and almost exactly the same intensity and energy spectrum as the excess electrons detected by the detector. It seems that most people now agree that the positron excess is most likely due to the alternative theory. It comes from dark matter. Pulsars are no longer in the running. The pulsar won this battle, which was a bit of a letdown for Hooper, but he wasn't too discouraged. He studied the strange signals from the galactic plane in search of dark matter, placing most of his hopes on the heart of our galaxy, the galactic centers. A while back, in 2003, a young Princeton guy named Doug Finn Banner was looking at data from a space satellite in the Wilkinson microwave probe chain. Like Hooper, he was fascinated by the idea of searching for dark matter and was hoping to find traces of it in the BP data. He knew that if propellers existed, they'd have to generate them from time to time. He also knew that the annihilation process would be accompanied by bursts of gamma-ray microwave radiation and a cascade of other high-energy particles near the center of the galaxy. He noticed something strange in the microwave radiation. It was different from the relic cosmic microwave background radiation. It seemed to be coming from inside our galaxy rather than from the scene barrier like the relic. Fen Bayer's article on the unusual microwave haze at Phillips, and especially the suggestion that the culprits might have been propellers, caught Hooper's attention. The situation became even more complicated in 2008, when NASA's Fermi Gamma Ray Space Telescope, which was launched into space by NASA, sent its first batch of data. Fink Heiner, who is now a professor, and his 2 graduate students, Tracy Slater and Mansour, discovered that the microwave haze matched perfectly with the gamma-ray haze around the center of the Milky Way. But no one was sure where this haze came from. Radio telescopes focus on a specific area of the sky and pick up signals from things like stars or pulsars. The Fermi Space Telescope has a much wider field of view. It can see about 1/5 of the sky at any given time and gradually surveys the whole sky at 3 a.m. However, the picture it produces is not very clear. The telescope has a resolution of only 1/10 to 1 degree for most energy values. So, it basically smears the stars out to the size of the moon, if not larger. So, even though Fermi could figure out which way the photons were coming from, he couldn't pinpoint exactly where the haze started. Eventually, it was dubbed the Fermi haze. There was no doubt among the scientific community that it was happening in the area around the galactic center. Not long after, in 2009, Slater and Weiner noticed that the haze had some kind of outline. This was a surprising and unexpected discovery. Instead of seeing a single blob with no clear edges, they suddenly saw 2 giant, fantastic bubbles. It's shaped like an hourglass, about 50,000 light-years long, and centered in the Centauri galaxy. The brightest in the gamma-ray range was the Fermi haze, which then transformed into a Fermi bubble. Newspapers around the world ran a striking image of a vast cosmic figure 8 on their front pages. In 2014, Slater Sue and Finn Banner were awarded the Bruno Rossi Prize by the American Astronomical Society's High Energy Astrophysics Division for their discovery. Hooper found the bubbles revealing but also a bit disappointing. He said that the microwave emissions recorded by the MR detector and the gamma rays detected by the Fermi telescope couldn't be signs of dark matter. He says dark matter annihilation shouldn't produce such bubbles. The glow region should be somewhat blurry and not have clearly defined boundaries. It's still not clear what caused the Fermi bubble to inflate. Some scientists think the bubbles may have formed when our supermassive black hole exploded long ago. While Sagittarius is currently quite inactive, unlike other galaxies' active nuclei, which have been recorded as emitting radiation. Another idea is that the bubbles could have formed if the many giant stars that formed from the gas around the black hole exploded almost at the same time as supernovas. But Hooper was determined to keep at it. Once he found out that the haze couldn't be dark matter, he and New York University graduate student Lisa Goodwin decided to take another close look at the data from the Fermi telescope. And in that data, they made an exciting discovery. The gamma rays were much more intense near the galactic center than the theory suggested. It was more intense than all the other known physical sources combined. It was a combination of supermassive black holes, cosmic ray protons colliding with gas molecules and electrons, cosmic rays interacting with photons and gas molecules, as well as supernova remnants and Fermi bubbles. The excess gamma ray emission was about 10%. On top of that, the radiation spectrum and distribution didn't match what you'd expect from pure astrophysics. Hooper was amazed when he got to the source. Could this be proof of dark matter? The extra radiation seemed to have a maximum at energies from 1 to 300, 0.000000000 electron volts 13 GeV. This meant it had about 1.00000000000 times more energy than what we would consider to be light. It was brightest right at the center of the galaxy, and it got dimmer the further away from the center you went. This suggested that the source was almost spherical in shape. It would take at least 5,000 light years to stretch the highway from the center of the galaxy. Hooper figured the excess came from nickel, and he teamed up with Huda to write the paper and post it on the server. The Cork Project. It's a popular online platform developed by Karelian University that makes it easy to share scientific articles. You can post them for free before they even appear in peer-reviewed journals. But it seemed like no one was paying attention to this publication. Hooper tried to get people's attention on his results. That same year, he gave a conference presentation and talked about the calculations his team had made. He remembers how thrilled he was to share that they might have finally found evidence of dark matter at the center of the galaxy. But the audience was strangely silent. After the report, one attendee approached Hooper and called him an unprofessional who doesn't know how to interpret the results from the Fermi telescope. He got similar negative reactions at other conferences, especially from members of the Fermi community, the main people who used the data produced by the telescope. They saw Hooper as an outsider, interpreting the results that they, members of the Fermi team, had made public. They spoke to me in a very arrogant way, he says. A few months later, when another batch of data from the Fermi telescope was made public, Hooper and W were pretty sure that the source of the radiation was still there. We got a lot of criticism, so we tried to improve our data analysis. We used a more sophisticated instrument-related correction program and made the processing of point sources and background in this part of the sky more accurate. After processing the data, we saw the same signal. It didn't amount to anything, Hopper says. They published a second paper in 2010, but this time it didn't get much attention. For Hooper, though, that paper was a turning point. He's now convinced the signal wasn't a phantom. He wasn't convinced that dark matter annihilation was the source. He was certain the signal was real. In September 2010, Tim Linden, a young graduate student from the University of California at Santa Cruz, who had attended one of Hooper's first talks, came to the opera. Linden was at Ohio State University at the time, and when we spoke, he told me about the hostility Hooper had encountered. To say that the Fermi community didn't take Dan seriously is an understatement. Some people were very dismissive of his method of analysis for years, but I always thought his analysis was correct. Could there have been another source for the gamma rays? Yes, I think it's always a possibility. It's still a possibility, Linda says, but he was intrigued by Hooper's hypothesis and felt he'd really got to the heart of something important. In October 2011, Linden and Hooper published a paper in which they explained how they obtained the same amount of excess gamma rays using a different technique for measuring them and mapped the gamma ray sky. Eventually, other teams of scientists also looked into this and found that there was more gamma radiation than expected. However, it was still tough to get the Fermi community on board. Lots of other astrophysicists thought the excess radiation couldn't be taken seriously, and Hooper saw that it was time to put together a strong paper on this excess radiation and either prove his case or move on from it. So in 2012, Hooper decided to reach out to some of his colleagues who were analyzing gamma-ray radiation. This included Banner Fenn and Slater Slide, who were still studying the origin of the bubbles at the Institute for Advanced Study in Princeton, New Jersey. One summer afternoon that year, they ran into Cooper at a conference in Colorado and started chatting about what was going on with the bubbles closer to the center. By then, few people thought the bubbles could be a sign of dark matter, but the claim of similarities between bubble emission in the microwave and gamma bands was based on the comparison. Gamma radiation is coming from far away from the galactic plane, while microwave radiation is coming from near the center of the galaxy. Since the comparison was between things that couldn't be compared, Hooper and Slater thought that maybe the inside of the bubbles could still be related to dark matter. We talked about whether the part of the bubbles closest to the galactic center could have been contaminated by excess gamma-ray radiation from the galactic center. I suggested that this could be due to dark matter. Hooper agreed. Slater was intrigued. She was aware of the gamma-ray excess and agreed to look into the bubbles, joining Hooper's research and focusing on the optical center. Over the next 2 years, she and Hooper published 2 major papers, the second of which took 6 months to write and was 30 pages long. I co-authored this with Wenger and Fenn Banner. They went over everything twice, or even 3 times, answering questions from anyone who might have a question. It's a pretty big article. We put our all into it, working on it full-time for 6 months, Linda recalls. No matter what models they used or how they processed the data, the gamma-ray excess remained. The authors looked at different parts of the galaxy separately to avoid any influence from the others. I worked on the part of the problem that involved the analysis of the galactic center, and I wasn't aware of the conclusions reached by colleagues working on the other part of the galaxy. Tracy and her team were looking at the other part of the galaxy and didn't know what they'd found. And then we managed to put the pieces together to get a full picture, Linda says. They discovered that there was an excess of gamma rays even at a distance of a few thousand light-years from the center of the galaxy. Nobody had realized before that the radiation was not confined to the center of the galaxy, but was also found far away from it. Snyder says that in other parts of galaxies, this was particularly interesting because it immediately ruled out the idea that the region around the black hole where it was absorbing surrounding matter could be glowing. Once it became clear that this radiation was coming from regions 1,000 light-years away from the black hole, these explanations simply ceased to be relevant, she says. Their paper also showed that the gamma-ray cloud has a roughly spherical shape centered at the optical center, and that its energy spectrum looks the same everywhere, even far away from the galactic center. As the co-authors were putting their results together, they realized that they were probably dealing with multiple sources formed from either dark matter or something else. And these sources are pretty evenly distributed around the center of the galaxy. This article was posted on the Archive Point online server in February 2014. The paper was called Characteristics of the Gamma Ray Signal from the Central Region of the Milky Way. Linden said that testing the possible role of dark matter annihilation immediately generated a lot of press coverage. The article was eventually published in the journal, but not until 2 years later in June 2016. It was the first article about this mysterious phenomenon that journalists would discuss on a daily basis for weeks. The Fermi community couldn't ignore the unexplained gamma-ray excess any longer. Even NASA put a press release about the article on its website, acknowledging that the excess existed. The press release was up for about 20 minutes before they changed it, but I was able to send the link to my mom, Linda recalls with a laugh. The article inspired a flurry of follow-up pieces over the next 3 months, with numerous references to it, over 150 times. A year later, the Fermi community published an article on the topic. Eventually, the focus shifted from debating whether there was any excess gamma rays at all to figuring out what might be their source. Some scientists agreed with Hooper and his dark matter theory, but most of them preferred the more familiar pulsar explanation for the origin of the glow. This possibility was even raised by Hooper back in 2010. The stars at the center of the Milky Way are much older than those at the outskirts. The oldest stars in our galaxy are about 5 billion years old. So it seems likely that the massive stars in the center should have exploded in a supernova a long time ago, producing many neutron stars. The density of stars at the center of the galaxy is extremely high. These neutron stars could form binary systems, where one star could eventually pump out the matter of its companion, making it rotate very fast. This would make it old and unwound. We're also looking at a second pulsar that might be emitting gamma rays and possibly radio waves. Based on what we know about millisecond gamma ray pulsars, the scientists figured that the observed excess could be the result of several thousand pulsars clustered at the center of the galaxy and joining together in a cluster. Even though they're point sources, their spectrum would be similar to what you'd get from annihilation. But when Linden and Hooper looked through the catalogs of known gamma-ray pulsars in the region, they didn't find any. Hooper then asks how likely it is that 000 pulsars are hiding in the heart of our galaxy without us knowing about them. How come we can't see them? One reason why Hooper's question is still open is down to technology. If you were to put the brightest second millisecond pulsars we've ever discovered at the center of the galaxy, they'd still be pretty hard to detect. It's not that astronomers haven't tried. Yes, they have. Slater says we're almost there in terms of detecting them. One of the most sensitive telescopes on the lookout for millisecond pulsars in the area is the one in Djibouti. The Greenberg telescope in West Virginia was the main tool used until the Mir telescope started taking pictures of the galactic center. In 2006, G. Betty made an exciting discovery: the compound Augusta MIT, the largest interstellar molecule with a bond, as well as other organic molecules in space. It's helping us understand the chemical composition of the interstellar medium. That same year, the radio telescope picked up a big, coil-shaped magnetic field in the molecular cloud Raven. And in the constellation Snake, there's a huge cavity filled with hot gas with a density less than that of the surrounding interstellar medium, about 33,000 light-years away. The telescope has some great features that make it an excellent tool for searching for and measuring the rotation periods of pulsars. Its superior sensitivity, huge default zone, very low noise receiver, and advanced technique for finding pulsars make it a remarkably advanced instrument. Over the years, Beatty has discovered more than 200 pulsars, many of them milliseconds. He's even found a few millisecond pulsars in gamma-ray sources that were previously identified by the Fermi telescope. This means we now know of several neutron stars that emit in both the radio and gamma-ray bands. Ryan Lynch, an astronomer working on the Betty telescope, says it's the best pulsar telescope in the world. If you're looking to search for a large population of millisecond data pulsars in the galaxy center, Djibouti is a great place to start. It's the best in the world, and in the future it'll be even more sensitive, maybe even the Chinese pole. Slater says there's still more to be done. It'll be tough to detect pulsars at the center of the galaxy, even for us. In 2009, Beatty spotted 3 pulsars near the galactic center. These weren't second pulsars, but rather young neutron stars, and they weren't gravitationally bound to the central black hole. Most astronomers are more interested in the millisecond pulse armies, because if they were bound to a black hole, it would allow scientists to test the general theory of relativity by observing tiny changes in the course of their clocks. Even so, the discovery of these 3 pulsars showed that Jay could see things in the layer of debris around the galactic center. This debris is a huge cluster of gas and dust that orbits around the galactic center, which makes it difficult for us to see. The more gas there is in stellar space, the more free electrons are carried around, interacting with radio waves of lower frequencies. The pulsars we're looking at are, This means that the signal recorded by astronomers will be distorted or dispersed to some extent, and that makes it harder to identify a point source. Another thing that makes it tricky to identify the source of the signal is the gas that scatters it. The pulses are deflected by the gas column on their way to Earth, so they have to travel long distances to get there. The signal arrives at different times, which makes it highly time-smeared. This makes it tough to spot the pulses. If the distance is significant, we won't be able to distinguish individual sources at all because the signals from them will overlap. However, J. Beatty is better at dealing with these issues than many other radio telescopes. It's incredibly sensitive. There are fewer high-frequency regions where the effects of Russia and dispersion, which make it harder to detect pulsars, are more likely to be found. On the other hand, as Lynch points out, pulsars don't make it easy for us to find them because their brightness decreases as we move to higher frequencies. So, there's a trade-off between dealing with the negative effects of scattering and it's ironic that the gas experiences radiation on its way from pulsars to Earth, and we need to work in a region of frequencies where there's still enough sensitivity to detect pulsars, even though they're inherently weakly radiative there. In other words, astronomers have to find a radio telescope that can operate at high frequencies to get around the effects of the initiated gas, but also be sensitive enough to detect the weaker signals from pulsars at those frequencies if they're there. Most millisecond pulsars are found in globular star clusters in the far reaches of the Milky Way. Hooper says that, based on how they shine, there simply can't be that many such pulsars in the galaxy right at its center to explain the extra radiation that's been recorded. However, other astrophysicists think it's possible. It seems the debate has reached a standstill. That was until 2015, when two groups of scientists, one led by Christoph Wenger, an astrophysicist at the University of Amsterdam, and the other led by Peter, published papers supporting the pulsar hypothesis. The two groups used slightly different techniques to look at data from the Fermi telescope, taking into account its technical limitations. Since the Fermi telescope isn't pointed at the source, like in a traditional experiment, it looks at a huge area of the sky. It picks up radiation from all sorts of different directions. Bright point sources, including pulsars, show up as hotspots in this radiation, but it's possible that some weaker pulsars might get lost in the noise. The two teams of astronomers split the patch of sky around the galactic center into lots of tiny pixels. Next, they measured the changes in emission levels from pixel to pixel, counting the number of individual photons recorded by the Fermi telescope. They noticed that there were significant differences in the number of photons between these pixels, even after accounting for the variation in the expected emission from known sources. In other words, there were areas of the sky that were hot and areas that were cold. They said the bright regions could be explained by a single bright pulsar or a cluster of millisecond pulsars. The dim, cooler pixels matched the absence of pulsars, although some hot and cold spots could be the result of chance. The brightness variation was significant enough to be explained by the presence of clusters of pulsars, but so faint that they're difficult to detect individually. If you spot any divots in the image, they're related to the polka dot pattern. Linda says you can't say for sure that you're seeing an individual pulsar, but the authors of the paper argued that if the excess radiation was caused by the collision of dark matter particles, which still existed only in theory, then all areas of the sky should be glowing in the gamma ray range at the same level. It seems that pulsars have won the argument. Even Hooper had to admit that the case for pulsars was pretty compelling. He remembers that the two papers had a big impact on scientists and convinced many that it was probably the rapidly rotating neutron stars that were the source of the radiation. There used to be a new paper on the properties of dark matter every few days, Cooper says. But then the number of these papers suddenly dropped by a factor of 3 or 4. That's how interest in the subject basically dropped to zero. But Hopper still had doubts about the polar theory and was very vocal about what he saw as the flaws in both papers. I thought there were lots of reasons why this alternation of spots might be happening. After all, most of the gamma radiation detected by this telescope isn't due to the excess radiation we're talking about. It's due to more ordinary, physically based processes. It's likely that these other factors also cause spots, but we just don't know about them. He thought it was a good idea to consider the possibility that the data might also hide a big, steady excess of radiation linked to dark matter annihilation. He put forth his arguments, but was unable to sway others. Luckily for Hooper, Slater didn't think the issue was completely solved and kept looking into it, even though she'd already published a strong paper in 2015. In early 2019, she decided to stop looking at her own calculations and at the same time Wenger's previous calculations, along with fellow MIT physicist Rebecca Ellen. This time they put together a digital model of the Milky Way, including all the stars, gas, dust, and known pulsars. Then they added in some hypothetical dark matter and some dim pulsars that weren't in the original digital model. They analyzed this artificial Milky Way and found that the extra pulsars made it look like a galaxy that contained very little dark matter glowing in the gamma-ray range, even though they knew it must be there because they had introduced it themselves. Then they added dark matter to the actual Fermi data to see what would happen if it were introduced into our real galaxy. Once more, they discovered far less dark matter than the signal they had added should have produced, but a great many more point sources. They discovered a new kind of pulsar. This meant that instead of the smooth pattern they expected to see, they got a clean one. The scientists couldn't detect any of the dark matter signal they added until they injected more than 5 times the signal that would explain the observed excess radiation. So, the paper basically shows that the previous analysis didn't detect dark matter. The signal from it somehow got hidden. You have to infer it manually to get a smooth profile picture, and it turns out to be spotty. It just means that the analysis method you're using is mistakenly identifying smooth radiation as spotty, Hooper says. It doesn't mean it has to be smooth, but it also doesn't mean it's spot forming. The 2015 analysis wasn't as reliable as we'd hoped, but it still gave dark matter a chance. The paper didn't offer any new evidence for the existence of dark matter, though. It weakened the evidence by explaining the excess gamma-ray emission of galaxy glow pulses. Hooper said it's still unclear whether the excess radiation is distributed smoothly or forms spots, at least based on the data we've analyzed so far. One possible future test experiment could be based on data that the Fermi telescope will collect by studying tiny galaxies, dwarf galaxies, and distant galaxies orbiting the Milky Way. If dark matter particles are responsible for the excess radiation, the VMPs in them should give off a very similar signal, only slightly weaker. Once the Fermi telescope has collected more data and we've discovered many more such dwarf galaxies, we'll be able to test this idea. However, Slater's paper has reignited interest in the dark matter mystery. She herself thinks a pulsar is a more likely explanation. Hooper knows there are many scientists in that camp. Out of the 10 cases where a signal is picked up that could be linked to a new and unusual phenomenon, in 9 cases, it turns out to be related to something already known, he says. And that's how things really happen. In most cases, you don't discover new exotic physics. You just learn new things you didn't realize were new. If they discover dark matter, that would be a huge discovery. It would give us a whole new way of looking at a part of the universe that we could only see through its gravitational effects before. It would also be a significant step forward in our understanding of cosmology. By looking at gamma-ray luminescence, astronomers could figure out the mass of dark matter and understand how it relates to the standard model of particle physics, which is currently the best way to describe how all known particles, and 3 of the 4 known fundamental interactions, are electromagnetic. Weak and strong, but not gravitational, are connected to each other. That would be a total game changer for my field, Snyder says. Even so, she has a different take on Cooper's view that pulsars aren't particularly fascinating. She thinks that discovering an entirely new population of millisecond pulsars at the optical center would be a significant discovery. If we can find them, it might prompt astronomers to investigate how the Milky Way evolved and how these stars got there. I think it'd be pretty ungrateful to say something like, "This isn't dark matter. I didn't manage to find what I was looking for. I was disappointed, and I've decided not to pursue this further," Slater says. The discovery of a whole new population of neutron stars that we never knew existed will give us a lot of valuable insights. It'll help us understand the history of our galaxy. I'm more concerned about what we may never know. So the race for discovery continues. If, in the next 10 to 20 years, the observatories like Betty Peace, Cat Parks, Rhode Island SIB, or future ones like Key do detect a pulsar in the galactic center, well know that neutrons, stars, and dark matter are on equal footing. Andrew Lyon had been on tenterhooks since morning, sitting in a conference room brightly lit by huge chandeliers. He watched as more and more people came into the crowded room. On Wednesday, January 15th, 1992, at least 1,000 people had come to hear him speak at the Astronomical Society of America meeting in Atlanta. On the third day of the conference, we had a special session on the possibility of planets forming around neutron stars. 6 months ago, Andrew Lyon and his colleagues at the University of Manchester made a big announcement. They discovered a planet outside the solar system for the first time in history. It's orbiting a star. The planet was found to orbit around a star, which wasn't like our sun, but was actually the dead core of a massive star that had become a pulsar. This was seen as the first real proof that other planetary systems might exist in the universe. When the team announced their discovery in July 1990, the scientific community was really excited about it. Now Lyon was going to tell a huge audience that it was all a mistake. Before he started his presentation, he was a little reluctant to read. He now had a good understanding of where the mistake had originated. Back in 1985, a telescope at the General Bank Observatory picked up a series of pulses from a previously unknown neutron star. Lyon and his colleague, astronomer Trevor Lipton, named it WASP, 18B2910, and added it to the catalog. They also started tracking the pulses to figure out how fast the star was spinning. As the Earth orbited the Sun, these moments changed. As with any double system, when our planet was closer to the pulsars came in sooner. When the Earth moved to the opposite side, the pulses came in later. We also used a chronometer to time the pulses over several months. They were able to figure out roughly where the pulsar was in the sky. It was in the constellation Shields, about 35,000 light-years from Earth. However, in May 1990, the astronomers noticed something odd about the pulsars period. Every 180 days or so, the regularity of the bursts of radiation was disrupted. At first, they didn't think much of it, assuming the irregularity was just noise from the pulsar's uneven rotation. Such irregularities can happen at random, and astronomers aren't sure why they occur. After looking over the data, graduate student Cher suggested that the oscillations could be due to a planetary mass body that orbits the neutron star with a period equal to half a year. Andrew Wang and Matthew spent several years observing the pulsar and noticed that the oddities remained consistent in period. In other words, the magnitude at its deflection was stable. At the time, the only explanation we could come up with was that these deviations could be due to the orbit of a very small planetary mass body around a neutron star. Sherman's calculations show that the planet should have a mass similar to that of uranium and orbit in a way that's similar to Venus' orbit around the Sun, with a half-year period around the pulsar. It's pretty amazing to think that a planet could orbit a pulsar. Lyon and Bell published their paper in the journal on July 25, 1991. It was called The First Planets Outside Our Solar System. These are called planetesimals. This discovery got a lot of attention in the media. The media picked up on it and ran with it for weeks, and astrophysicists were quick to congratulate the discovery. Even so, something about the planet's 6-month orbital period seemed fishy and kept him up at night. He was worried that there might be a mistake in the data, and that the strange changes in the period were related to the Earth's motion around the Sun during the Christmas and New Year vacations, when he finally had some free time. He decided to double-check all the calculations on January 2, 1992, line and go over the results again in detail. He and his colleagues had recorded 2 different positions of the pulsar after a certain period of time, with only a slight difference of 1/9 of a degree between them. Normally, when a new position is determined, the two are mutually corrected. But that didn't happen this time. When line entered the new pulsar position into the model, the 6-month periodicity vanished. Line's team had just misinterpreted the cyclic fluctuations in the pulsar's arrival time, attributing them to the gravitational influence of the planet. As it turned out, they had made a mistake in how they accounted for the elliptical orbits of the Earth around the Sun, so it turned out there was no planet orbiting this pulsar. I was pretty blown away, Klein said. I was in an office at the other end of the observatory by myself. And can you imagine all the thoughts that went through my head after all the build-up and everything? And then I realized that our discovery was a mistake. The Earth's orbit isn't a perfect circle. It's slightly oval, which is about 1% more than a perfect circle. If you use a circle instead of an ellipse, you have to make a correction of the order of seconds. The calculations provided by the Lin team, they made a tiny mistake in making that correction, and it resulted in a 6-month periodicity. When Line updated his calculations to reflect the pulsar's actual location and ran the analysis again, he realized that the planet wasn't there. Bell recalled that the Neutron Star seemed to be a lonely one. A few weeks before the 1992 conference, Lane showed up at his home in the early morning hours. He said, "Do you know why I'm here?" he inquired. "Were you worried?" "The planet?" Bell asked, looking a bit nervous. She suddenly left. Line let out a sigh. "I'm afraid so." War and his team had to prove that their article was wrong, and the chance came up at a conference where Line was invited to speak about finding a new planet. The audience was caught off guard by the unexpected turn of events. Even before the speaker had finished speaking, journalists were already running out of the room to report the sensational news. Unfortunately, it seems that a new exoplanet has not been discovered. The audience was so surprised, they applauded. People thought I said it because I was brave, but I had no other option. I knew that other scientists would look into it and would probably come to the same conclusion pretty quickly. I wonder if anyone will discover it soon. Liam came clean. For me, and even more so for Line, that experience still sticks with me like a thorn in my side, Bank said. Line stepped off the stage and looked at the next speaker. It was Alex, an astronomer from Cornwall. John Bach, the president of the Astronomical Society and an astrophysicist, was the only other person involved. The event organizers knew in advance that Wang was going to refute his own result. He was flattered and went on stage, turned on the projector, and began showing his slides. Even the day before, he felt like he'd come in second place in a marathon. But late that night, just a few hours before Line's presentation, he found out that the winner of the marathon had been disqualified. He told the audience that it was actually him, Alex, who had discovered the first planet outside the solar system, and not just one, but two. He later discovered a third one as well. He said that these planets orbited around Copper, a second pulse, and that this time the discovery of exoplanets was for real. There are lots of scientific achievements associated with the Russell telescope. He helped scientists discover the crab pulsars of the Prominent Nebula in 1960. Just a few months ago, a white pulsar was discovered in the Sales Nebula. These discoveries proved that neutron stars are real and are born in supernovas. In 1974, a double pulsar was also discovered, which helped prove the existence of gravitational waves and confirm Einstein's general theory of relativity. These studies earned scientists Russell House and Joe Taylor a Nobel Prize in Physics. That same year, a message was sent to the N13 cluster addressed to any extraterrestrial civilizations that might be out there. In 1982, astronomers used this telescope to detect the first millisecond pulsar, which spins at 642 revolutions per second, the same speed as on Mars. Alex is honored. He was the first to discover exoplanets orbiting pulsars in June 1990. He was flattered. He looked at areas of the sky above and below the galactic plane to find millisecond pulsars. One of his goals was to test the idea that millisecond pulsars, because they're so old, might have had time to move from where they were born outside the galactic plane during their lives, to regions below or above. He thought there should be lots more of these pulsars out there. At the time, only 4 milliseconds of their pulsar were known, and he was on a mission to find more. It was a pretty bold move to step out of the plane and try to find a new pulsar, which would actually confirm the assumption that there must be a lot of them in the high galactic latitudes, Valentine says. To prove it, he needed to get access to the telescope for a longer period of time. It's not easy to get access to the telescope. Astronomers have to apply in advance to justify their research goals and are usually only allowed to work on the telescope if their application is approved. And then only for a few hours or days at a time. But he was lucky enough to be able to make his observations for almost a month, because then it was time to make some preventive repairs to the supports that held the triangular platform over the reflector. The supports had to be replaced because they had developed some cracks due to metal fatigue. So the telescope was closed to outside researchers, and a few permanent staff members got to use it full-time. Even though it wasn't possible to track the radiation sources by moving the receivers and pointing them at specific areas of the sky, the dish could still observe those areas that were currently passing over it. The reflector is huge and has great sensitivity, so the signal could be registered. Even if a particular point in the sky was only visible for about 30 seconds, Wolfowitz also spotted 2 lunar pulsars that were well above the galactic plane during his quick look at the sky. One of them caught his attention more than the others. It was a double system, just the 4th one that had been discovered up to that point. It had certain characteristics that made it an excellent object to test Einstein's general theory of relativity. I was really excited about it, he says, with a hint of frustration, and put off analyzing the other pulsar I had discovered for a while, not knowing what surprises it might have in store. As it happened, this other pulsar, which was only the 5th millisecond pulsar discovered at that time, and which had been overlooked for a while, would change not only Valentine's life but also our understanding of how planets and galaxies were formed. When Valentine finally took the time to look at his notes on this pulsar again, he noticed some of its unusual features. As with any new pulsar, he started timing it. This meant measuring the time it took for pulsars to arrive, which was needed to build a model. But Wolfson says that modeling the time behavior of this pulsar was really tricky. It just didn't act the way I thought it would, and no one could have predicted that at the time. The pulses weren't regular, which seemed strange because millisecond pulsars are usually very stable. I also noticed a pattern in the irregularity, but I couldn't figure out what it was because millisecond pulsars are usually found in double systems. It's well known in astronomy that the arrival time of a pulse from a pulsar in a double system is different from that of a pulsar that is not paired. As a general rule, we saw similar discrepancies, but they were pretty minor. The smaller the object orbiting another star, the smaller these deviations are. But in this case, we're seeing something different. The deviations were too small to be caused by a white dwarf typical companion or a second pulsar in double systems, but that wasn't the only issue when Valentine tried to link the data to a specific orbit. At first it seemed to be working, but then the observed data stopped fitting into that orbit. He kept trying to make the model better, but nothing worked. He was getting frustrated, so he started observing the pulsar very carefully every day for 3 weeks to figure out exactly what the deviations were. Thanks to his hard work, he realized that the system he was observing was definitely not standard, double impulse. He also dismissed another widely held belief at the time, namely that seismic processes within a neutron star could have caused it to behave atypically, creating what are known as time bingo noises. There was a difference in the timing of the transitions and pulses. This hypothesis seemed pretty unlikely to him, since it was an old second pulsar. Goldstein then took a look at his method for analyzing the data and checked for any technical issues with the archive. But it turned out that the second double pulsar system he'd detected didn't show any of these strange effects. If the instruments are working right and the data analysis is correct, the oddity must lie in the pulsar itself. Despite its unique sensitivity, he could no longer determine the exact location of the pulsar, and this was crucial because any mistake in pinpointing its location could lead to confusion about what was actually going on. Wolfson asked fellow astronomer Dale Freud, who worked at the observatory with 27 antennas in New Mexico, to help him figure it out. Freud was able to pinpoint the pulsar pretty quickly. Now that he had the exact coordinates, W. Pulsion was ready to make a scientific breakthrough. It was obvious to me that what I was looking at was similar to a beat when you add two sine and data waves. I knew there had to be two objects orbiting the pulsar, he says. When he measured the amplitude of these waves, he realized that their sources must have planetary masses on the order of Earth's. When he finally got the results, he looked at the screen and was pretty blown away. It's true that at the time, astronomers didn't realize that planets could orbit neutron stars. This was because Andrew Lyne hadn't yet published his erroneous paper. That happened later that year. So, while he generally thought that two planetary mass bodies could explain his findings, he wasn't sure it was the right thing to do. He couldn't stop thinking about his results, whether he was looking at the antenna dish at sunset from the platform or sunbathing on one of Puerto Rico's famous sandy beaches. That's where he usually went to unwind on weekends. He'd stare at his computer screen, running through various alternative scenarios and discarding them one by one. He wanted to think through any questions or criticism his colleagues might have when he announced such an unusual explanation for the pulsar's behavior. He was involved and left Puerto Rico in September 1990 to return to Cornell University. And that's what led to New York State. He processed a full year's worth of data collected since June 1990 and tested his model of pulsars under the assumption that he had detected two Earth-mass planets orbiting in a circular orbit. He ran another full and decisive test and finally concluded that no alternative explanation worked. As it turned out, he was right. The only explanation that made sense was that he had indeed discovered a dead star around which two planets orbited. He said he had a gut feeling in his office in Cornwall. He made a huge discovery. There's a planet outside our solar system. I looked at the result and it was spot on, he says. I finally got it. I had to face facts. It had to be the planets, no question. The original measurements of these exoplanets came in at 3, 4, and 2, 80 times the mass of Earth. Involved knew that 2 months earlier, Wine had published a paper about finding planets orbiting a pulsar. He found out that he wasn't the first to make this discovery and accepted it. Anyway, both Freud and Wine published their paper on January 9, 1992, just a few days before speaking at the American Astronomical Society conference. When Valentine drove to the conference, he knew he was up after 8. At the time, he was still new to speaking in public, so he practiced his talk a lot in front of a mirror. He got to Atlanta the day before the event and was just about to have a glass of wine. John Hall, the president of the Astronomical Society, pulled him aside for a quick chat. He asked Wolf to take a seat. He told me that Andrew was coming, not to confirm his findings, but to refute them. He was trying to give me a heads up that I should be nice and delicate. In a situation like this, he knew about the military rebuttal of his discovery in advance, which gave him an advantage. But he needed a few hours to make some changes to his report. That same evening, he came up with a plan for a conversation. They both felt a bit uneasy. He says he regrets how things went down, and that's understandable. He must have been pretty embarrassed by the whole thing, but he didn't show it in public. He kept his composure. When Lyne came on stage and said he'd made a mistake, he even mentioned Valentine's discovery, saying that it would probably hold up to any criticism or scrutiny, but the audience had already stood up. Vauchin remembers it as quite a commotion. When he got up on stage, he was ready for some tough questions, but he wasn't asked a single question. Maybe, the honoree suggested. I think it was because people were blown away by Linus' statement, or maybe because he'd thought through all the other possible explanations and shown why they didn't add up. His colleagues were on the same page when it came to the conclusion that planets were orbiting the pulsar. Valentine's discovery was more than just observing a strange case of planets moving around the remnant core of a massive star. He showed that planets can orbit different types of stars and form in the same way as planets around stars like our Sun, from a disk of gas and dust surrounding the star. The key difference is how this disk is formed. Right now, scientists have two main ideas about how this disk might have formed. One is that there is a disk made up of matter that was thrown out during the supernova explosion. Instead of flying away into space, this matter might have traveled back to the dead core. Or maybe the newly formed neutron star collided with the companion star of the original star. In this case, the star would have ruptured and started ripping around the matter proper, forming a disk. Scientists who published papers based on Valentine's discoveries soon came up with the idea that planets could probably form around any type of star. They also thought that the process of planet formation must be pretty universal. It's a universal phenomenon. Years later, the Kepler Space Telescope confirmed this by finding lots of exoplanets orbiting all kinds of stars, including white dwarf planetary systems discovered by the team, which he later added a third planet to. He didn't notice it at first. This was preceded by what the Kepler telescope discovered 2 decades later. It turns out that the most common planetary systems are super-Earth systems, which have planetary masses slightly greater than Earth's. These planets orbit their star in very close orbits. In the 1990s, nobody thought that would happen. 25 years ago, no one could have predicted that we would see a planetary system like this in the near future. No one would have believed it, Valentine laughs. Is it possible that life could exist on planets like the ones Wolf discovered? He thinks this idea is more science fiction than anything. But in recent years, there have been some interesting articles exploring the possibility of habitable zones around neutron stars. Maybe one day we'll find life on exoplanets orbiting pulsars. Maybe not a fully fledged civilization, but at least some primitive microbes. In this case, we're talking about life in the interstellar medium, which will help us solve another of those mysteries that make our cosmos so unusual and mysterious. Neutron stars are definitely worth studying, but for some scientists, they're becoming more than just an object of observation. They're looking to use them as kind of galactic-scale instruments. One possible use is to use pulsars as space beacons for a global positioning system, or GPS. It's been demonstrated that this system is feasible and could be the breakthrough that eccentric billionaire entrepreneur Elon Musk has been waiting for. And it's not just for helping people navigate spaceflights to Mars. It could even be used for journeys to other planets in the future. Here on Earth, lots of car drivers, truckers, pilots, ship captains, and most smartphone owners use navigation systems like Galileo or GLONASS to find their way. These systems work in sync. Signals are sent from above by precise atomic clocks that are mounted on satellites orbiting the Earth. Applying these principles to space. Some scientists have long suggested using the intervals between pulses from the most relevant pulsars to help spacecraft find their way in the vastness of the Milky Way. To make sure a spacecraft is still on the right track, it has to constantly communicate with Earth through giant deep satellite antennas that were designed and built at NASA. As the ship travels farther into space, this method becomes less reliable, more complex, and more expensive. If we use pulsars as radio beacons, the ship could position itself on its own. It would be a better space compass. In November 2017, NASA demonstrated that it's possible to use pulsars as radio beacons using the X-ray detector aboard the International Space Station. The detector is also used to determine the mass and radius of neutron stars, which helps scientists understand the internal structure of dead stars. The USSR also mounted a small instrument, the Sectarian X-ray, Time Domain and Navigation Explorer, which can record the pulses from the many neutron stars scattered across the sky with great precision. That's exactly what he did in 2017. He timed X-ray pulses from 5 pulsars over times ranging from 5 to 15 minutes for each. Sectant measured tiny changes in the arrival times of the signals as the ISS orbited the Earth, which allowed them to calculate NASA's exact location and thus their own. In the future, we could make similar instruments lighter and fit them to any spacecraft. Timing out the pulsar array could also help us understand some of the mysterious phenomena that astronomers have been trying to understand for decades. Scientists know that most galaxies have supermassive black holes at their centers. These black holes are millions or even billions of times more massive than the Sun. For instance, the black hole at the center of our Milky Way galaxy weighs in at around 4 million solar masses. It's thought that when galaxies collide, their black holes merge, and at that moment, send gravitational waves into space. However, detectors on Earth won't be able to detect these waves because they're too long, and the waves are too weak to be picked up by a ground-based detector. This has been going on since the 1980s. Astronomers started using a network of pulsars to detect these Rabi effects in spacetime. They were trying to turn these neutron stars into natural detectors of galactic-scale gravitational waves, especially sensitive to black hole systems with masses ranging from 100,000 to 100,000,000 solar masses. If scientists ever detect these waves, they'll be able to test Albert Einstein's general theory of relativity on a universal scale and confirm the existence of double systems and supermassive black holes. This could also help us learn more about the mysterious beings that live in the densely populated galactic center. The pulsar array method is probably going to help us find out more about what's behind these objects. At least partly it's about understanding how supermassive black holes are formed and the secrets of neutron stars. It's true that when a massive star dies, it either collapses right away into a black hole, or it first forms a neutron star. And later, when two neutron stars collide, a black hole is usually born. One idea is that after lots of mergers, these stellar mass black holes eventually form supermassive monsters. To try to picture these galactic monsters, let's set the pulsar chronometer aside for a moment and take a trip to the edge of the world. The snow in Antarctica is blinding from a few hundred meters away. A 10-meter radio antenna dish looks tiny and is so white it almost blends in with the lifeless United Them polar plateau. The South Pole telescope is designed to detect short millimeter and submillimeter electromagnetic waves from space. The telescope was originally built to search for faint traces of the oldest light in the universe, cosmic microwave radiation from the Big Bang. It has recently become part of another sci-fi project, though, together with other antennas located around the world. The N5 telescope is part of a virtual radio dish that's about the size of an Earth-sized telescope and almost as big as a telescope-sized event horizon. This giant virtual instrument has allowed scientists to learn about the colossal supermassive black hole at the center of neighboring galaxies and capture it for the first time. The telescope has been around since 2007. Mormon B21010M came up with the idea to connect it virtually as a component to several other ground-based antennas so that together they formed an array of telescopes. This planetary-scale telescope has an event horizon, which is the imaginary boundary of the spherical region around the black hole. Nothing, not even light, can go outward from there. It's thought that a black hole is left behind when a massive star, more massive than those that make neutron stars, is crushed by its own gravity. In a black hole, all the mass is concentrated in a tiny area at the center, called a singularity. This is different in a rotating black hole, where the singularity is a ring. The singularity is shown as a ring. On April 10, 2019, the community made history by publishing a snapshot showing what looks like a reddish-orange donut on a black background. The image was a bit blurry and didn't seem particularly impressive, but it was the first ever image of a shadow. This is a supermassive black hole at the center of the largest galaxy, Messier 87, in a nearby cluster of galaxies in the constellation Virgo, taken at high resolution. This black hole is 5 billion times more massive than the Sun and is located 55 million light-years away. Scientists have long believed, based on Einstein's general theory of relativity, that a black hole should be like a shadow, putting it against a bright background of glowing gas. They've now got the first proof of that. The gravity and black hole act like a lens, increasing the frequency and intensity of light from the side that rotates toward the observer. That's us. We can't see what's behind the black hole, but most of the light that would have to come to us from there is bent by the lens, which is circling the black hole. This means that only a tiny amount of light reaches us directly from the space in front of the black hole, because any light that comes straight towards us is deflected and out of our field of view. As Moroni explains, light in front of a black hole is mostly deflected around it by gravity or captured by the event horizon. Since the black hole is so far away, scientists needed a really big high-tech camera and a huge telescope to get an image of it. This is exactly the kind of instrument he uses. It's based on the super-long baseline interferometer metric, which is created by synchronizing several radio telescopes spread around the globe. This uses the rotation of our planet to our advantage. This system of telescopes is basically an Earth-sized instrument with a resolution of 20 angular milliseconds that can record wavelengths down to as little as 3 millimeters. Macaroni figured that setting up a dish of 5 in Antarctica would give the telescope a big boost, especially when observing the center of the Milky Way and its supermassive black holes. Sagittarius. A** has a special relationship with this black hole. He wrote his thesis on it in November 2011. He applied to the National Science Foundation, which runs the telescope expedition, for funding. He explained that the radio telescope would be key to imaging our own black hole because it would double the resolution of the telescope system. Our galactic center is best seen from the southern hemisphere, and there's nothing south of the South Pole. A small telescope based in Antarctica can observe the center of our galaxy at all times. Scientists have known about the Sagittarius, a black hole, and its location at the center of the Milky Way for a long time. In 1906, Carl Jankowski picked up a radio signal that seemed to come from near the constellation Sagittarius. So, the radius source was named Sagittarius A. When astronomers figured out that the point source was part of the radio source, Sagittarius A, the name was changed to Sagittarius A** with a star. For a long time, scientists have thought that the presence of this component in the signal is a clear sign that there is a black hole there, which radiates by absorbing the surrounding matter. Over the past 10 years, several teams of scientists have published both theoretical and experimental results. In these papers, the authors used measurements of the velocities of stars near the center of the Milky Way to determine the limits of the radius of the sphere in which the bulk of the mass of the central part of the galaxy is concentrated. In 2002, Richard Handel and his team at the Max Planck Society Institute for Extraterrestrial Physics published a paper based on 10 years of studying the motion of stars around the galactic center, especially a star called R2. From these data, it seemed that R2 was orbiting around a very compact and bright central radio source about 60 million kilometers in diameter, which was too compact to represent a very dense cluster of stars. This provided more indirect evidence that the source was likely some kind of medium with extreme properties surrounding a supermassive black hole located about 26,000 light-years away from Earth. It took Barona 6 months to get his grant approved in 2011. Once that was done, he started designing and building the right equipment for the small radio telescope needed to observe black holes. Specifically, he developed the original receiver, which measures the electric field of whatever source the telescope is pointed at. Crow says the receiver is like a really cool radio that operates at a temperature of 4 Kelvin, which is almost as cold as interstellar space. So, all the noise is taken care of. The radio telescope uses this receiver, along with an ultra-precise atomic clock, every time it operates. The M87 galaxy isn't visible from Antarctica. The F5 telescope has also helped astronomers to be more confident in the final result, as it has allowed them to observe Quasar 279. Otherwise, I think we would have been a lot more nervous, Morozov says. The 6 papers, which came out around the same time as the Japonchik photo, give us the mass of the central black hole, N8 and N7, as well as the direction of its rotation. Aaron says they now have some of the first insights into its immediate neighborhood, which will help astronomers understand what makes up a relativistic jet. Blackbody jets. Over the years, the observatory's 8 telescopes have been used to observe the center of Galaxy 87 and collect detailed data on our Sagittarius A black hole. This data is combined with data from the ALMA telescope, which is located on the Chillón Plateau in Chile. These results should soon let researchers get an image of our own black hole, or rather its shadow. The image was revealed on May 12, 2022. With these images, scientists hope to learn more about the supermassive black hole's environment, which is made up of superhot gas and dust. These are bathed in and devoured by the black holes, as well as the huge jets that are shot out when the black holes consume the gas and accelerate. How do supermassive black holes come about? It's still a mystery. But even smaller black holes that form from the death of massive stars were, until recently, just theoretical concepts and curiosities. In 1916, mathematician Karl Schwarz solved Einstein's equation of the general theory of relativity for spherical mass. Their solution was the now famous Schwarz radius to a black hole. Then, in 1958, David Finkelstein, a physicist from the Georgia Institute of Technology, showed that black holes have an imaginary boundary, which he called the event horizon. And anything caught under this boundary, including light, can't escape. For them, the rest of the universe is forever inaccessible. Even so, for decades, black holes, both those with stellar mass and supermassive ones, were just theoretical concepts that everyone recognized, but there was no real proof of them. It wasn't until the mid-20th century that astronomers started gathering evidence to prove they existed. They were also the first observations of quasars. The galactic X-ray source Swan 1 was discovered in 1964, and scientists later figured out that it was probably a black hole. The detection of gravitational waves from the collision of two stellar mass black holes on September 14, 2015, has also proven to be very useful. Now that we can see them with the observatory, we know that supermassive black holes are real. But how did they get so big? That's a question scientists are still trying to answer. Some experts think these supermassive black holes might have formed when multiple black holes of stellar mass, tens or hundreds of solar masses, merged in the early universe. When they merged, they absorbed gas, increasing their mass and eventually becoming supermassive black holes. It's thought that galaxies collided as the universe evolved. Our own Milky Way is in the process of merging with the Andromeda Galaxy, for example. In about 4-5 billion years, they'll merge much farther from Earth, at a distance of about 1,000,000,000,000,000,000 light years. Astronomers have even discovered a rare system of 3 galaxies called DJ0849 plus 1114. What's more, each of them has its own supermassive black hole. It looks like these 3 galaxies are gearing up for a physical collision. When galaxies merge like this, their central black holes should also merge and become even more supermassive. This is especially likely if there is a third black hole nearby that can pull them closer together. Computer modeling shows that truly massive black holes could experience up to 20 mergers during their lifetime. The black hole in the M87 galaxy could also undergo several mergers, since it is 1,000,000 times more massive than the Sun or any stellar mass black hole. At the same time, astronomers think that supermassive black holes get most of their mass by absorbing interstellar gas that falls on them when their parent galaxy is invaded by another galaxy. We don't really know which of these 2 factors is more important, gas absorption or merger. That's according to Scott Jensen, an astronomer at the National Radio Astronomy Observatory at the University of Virginia. It's all still just theory, but it's thought that when galaxies merge, the spiral collapse and final collision of their supermassive black holes should cause gravitational waves to be emitted in all directions. It's understood that large bodies in space affect the fabric of space-time by creating funnels. An individual mass doesn't emit gravitational waves on its own. It's the motion of 2 accelerating masses relative to each other that causes this. Sure, I can do that. The bigger the disturbance, the stronger the space. Time responds by sending out more powerful waves. Chaos and Taylor indirectly provided evidence for the existence of gravitational waves when they noticed that they were narrowing the orbit of a pulsar in the double system that they discovered. Then, in September 2015, LIGA observed gravitational waves directly resulting from the merger of 2 stellar mass black holes, and Marinka franchisee learned of gravitational waves produced by the first observed collision of 2 neutron stars. On the morning of August 17, 2017, after spending the night in a hospital in Urbino at her sister's delivery. However, the gravitational ripples from a hypothetical merger of 2 supermassive black holes would take longer to reach us and change more slowly. They would also have a lower frequency in the nanohertz range. so detectors won't be able to detect them under any circumstances. Right before they merge, stellar mass black holes spiral around each other, coming together at a common center of mass. It happens many times in a second. The gravitational waves they emit during this stage, which are caused by spiral collapses and collisions, have a very high frequency in the range of 7 kHz. The frequency range is from 43 kHz to 30 Hz, with a wavelength of 10,000 kilometers. Our ground-based detectors measure how much each shoulder compresses for wavelengths longer than their shoulders. The League has to measure shoulder compression that's much smaller than the wavelength. That means the detectors measure the shoulder stretch corresponding to 2 points that are close together on the wave. In other words, it's basically measuring the steepness of the incoming signal. As the wavelengths get longer, the peaks get steeper, and the detectors get less sensitive. However, when a supermassive black hole with a mass of 1,000,000,000,000,000 solar masses forms a binary system with another black hole of similar size, they will orbit each other for years before colliding as they spiral down and collide. That's ridiculous and wrong. No other ground detector will be able to tell us when or if such a wave hits them. The main issue is noise from the ground, which simply silences the lower frequency waves. The noise can be caused by anything from minor earthquakes anywhere in the world to ocean tides and even trucks passing by. The League can only see frequencies of a couple periods per second, because anything below that value gets swamped by earth noise and seismic activity, according to the Iranians. They'll just get rid of everything else. However, in space, you can make the system more stable over longer periods of time. That's where the pulsar comes to our rescue. Neutron stars can also be used as a source of gravitational waves when they spiral towards each other and collide. They can also be used to detect gravitational waves on a galactic scale. That's our best bet anyway. Researchers are hopeful that within the next 10 years, they'll be able to detect gravitational waves from the merger of two supermassive black holes using the timing technique on pulsars. And we can use the solar system as an antenna system to make sure that pulsars are safe and secure. In 1969 and 1970, Joe Weber, who was originally an electrical engineer but later became a physicist, announced to the world that his barrel-shaped aluminum cylinders had registered gravitational waves. Unfortunately, he was mistaken. At that point, it was still 10 years away from the first discussions of the idea of creating either. But even then, two astrophysicists, Soviet scientist Mikhail Sajin and American scientist Stephen Mailer, wondered if it might be possible to use space itself to register ripples in the fabric of spacetime with a difference of just a few months. In 1978 and 1979, they published articles in which they suggested that a chronometer outside the pulses from neutron stars could allow astronomers to observe gravitational waves. The idea is that you'd have to think of the solar system as the centerpiece of the scientific instrument. It's like the intersection of two arms, and some far-off pulsar is the end of one virtual arm stretching its axes through interstellar space. Pulsars emit regular pulses, so they're basically extremely accurate clocks. However, if gravitational waves are passing through and affecting local spacetime, the pulses from the pulsar will arrive earlier or later, in comparison to what astronomers have observed in the absence of waves. Two other theorists, Ronald Heller and Gabriel Jones, built on this idea by looking at groups of pulsars. If scientists want to know exactly how many times a pulsar spins between observations, they'll have to regularly record the exact arrival times of pulsars from several pulsars scattered across the sky over several years. They'd have to look for any tiny differences in the arrival times of the pulses, as well as link up unrelated delays between pulses from neutron stars 1,000 light-years apart, which would show clear signs of gravitational waves. The purely theoretical concept became more realistic in 1982 when Don Baker discovered the first millisecond pulsars. These aren't the typical pulsars that Joe Bell discovered, which spin at a rate of about 1 revolution per second. Millisecond pulsars spin at hundreds of revolutions per second. Baker saw that this feature of milliseconds in their pulsars would let them measure frequency more accurately, down to a few 10s of a second. This precision in pulsar arrival could make them a better tool for detecting different gravity in the future. So what exactly is a pulsar array chronometer? Let's say we have a group of 50 different pulsars that have been closely observed by astronomers for over 10 years. Over the past 10 years, we've been tracking a lot of full rotations. We've been able to measure the arrival of each pulsar to an accuracy of at least 1/1000th. For instance, if a pulsar is spinning at 500 revolutions per second, it has made about 160 billion revolutions in 10 years. It's thanks to this huge number of very precise measurements that this technique is so accurate and reliable. If the pulses from some pulsars suddenly start coming in earlier, then later, and then earlier again, compared to what we'd expect, it's probably because something shook the detector. If we can't explain the changes in arrival time with something that happened near the detector like an earthquake or a delivery truck, it could be a ripple from a gravity wave. We're covering the ground. If we saw a shift first toward leading and then lagging on the sequence of pulses from all the pulsars, and they still obeyed the schedule calculated by Felix and Jones, it would be a sure sign of gravitational waves stretching space between the Earth and the pulsars along the path of the pulses. It's quite similar to how interferon and Virka work, and the Earth and pulsars are like the test masses at the end of each arm of the detectors. The only difference is that with pulsars, you have to collect data for many years because the gravitational wavelengths are very long. Baker wanted to do just that in the early 2000s, with colleagues at the University of California, Berkeley, as well as astronomers David from Lafayette College in Pennsylvania and Ingrid Pierce from the University of British Columbia. He started with the outside millisecond pulsar group, taking great care to be precise. They used the Alice and Betty telescopes to analyze the data using the Phillips method. They were aiming to detect gravitational waves, or at the very least, put some constraints on their parameters. Once they'd set up a measurement window where they thought gravitational waves might eventually be spotted, the 5 scientists started to time the pulsars. At that point, they weren't putting much effort into it, according to Orangev. But word got out about the project, and other astronomers became interested. In particular, Dick Manchester, who lives in Australia, liked the idea so much that he applied for and received a large grant from the government in 2003 to start applying the technique on a large scale. Branson says that as a result, he was able to spend enough time working on the Parkes telescope and secure funding to bring in postdoctoral researchers. In a nutshell, he developed the Parkes antenna system for timing pulsars. Manchester was hoping that in 5 years, this antenna and system would be able to register gravitational waves. This optimistic timeline got other astronomers around the world thinking about how they could use their native requirements of pulsars to detect gravitational waves. At around the same time, European astronomers got involved, combining the Westerbork radio telescope in fusion with the Berg, Nancy, Sardinia, and Hubble radio telescopes to create a European antenna and pulsar timing system. Robinson was also excited about this in the US. We knew we had 2 of the best radio telescopes in the world, and there was Djibouti, he says. So, with about a dozen other American astronomers who were experts on pulsars, they set up a meeting. We invited Don Baker and his small group to the meeting and said, "You're working on this small project, and the Australians are working on this huge project full-time. Let's do the right thing here. We came here to work with you," Renzo recalls. After a few years and a few grants, they decided to work together. In 2009, they set up the Nanogrove, the North American Nanohertz, and the Gravitational Wave Observatory. This is the North American antenna, which is a timing system for timing out pulsars. Right now, we're studying over 70 pulsars. It's been over 10 years now that these 3 projects have been going on, but so far none of the communities have detected gravitational waves. Even so, the chronometer outside of pulsars often produces unexpected results. One day in 2012, Ryan Lynch, who was a postdoc at McGill University at the time, was looking through 10 years of Djibouti's pulsar observations. He came across a second pulsar, now called J0740 plus 6620, and after a few months of observing it, he realized it was an incredibly accurate clock. Lynch and a group of colleagues, including Scott Francis, started working on the chronometer in Germany by heating it up with the observatory. Lynch soon noticed that Pulsar might have a companion star. Accounting for this allowed Emmanuel Fonseca and graduate student Suffolk Marty to determine the mass of the companion and then Pulsar itself. C. Marty led the studies, which revealed that this pulsar was the most massive neutron star ever discovered, with a mass of 204 solar masses. But we haven't yet detected any gravitational waves. We don't know yet if supermassive black holes actually come close together and are ready to merge. They've also detected galaxies with 2 active galactic nuclei, which suggests that the 2 galaxies have merged and their black holes are starting to converge. It'll take about 1 million years for the merger to happen, maybe even longer, Renzo says. Luckily, there are always galaxies merging with each other throughout the universe. Scientists aren't ready to throw in the towel, though. In the last 10 years, we've learned a lot more about how galaxies collide. They've also made great strides in developing models and calculation methods that better clean the data from noise and the influence of the interstellar medium. All of these steps are helping scientists to gain a better understanding of and to describe the motion of the solar system. The RAS thinks that within this 10-year period, astronomers will finally detect gravitational waves and the descent of supermassive black holes using a chronometer outside pulsars. The first thing the chronometer will do is record the background of gravitational waves produced throughout the evolution of the universe by the merger of supermassive black holes. It's not going to be easy. Just picture this. You're in a crowded room and everyone's talking at once. It's an effort to detect specific gravitational waves. It's like trying to overhear a specific conversation in that room where there's a lot of background noise. All you can really hear is this and a similar hum. That's precisely what scientists are trying to track with antennae systems for timing systems outside the pulsar array. The idea is to pick up the combined signals of 1, 0, 0, 0, or even 1, 0, 0, 0, 0, 0, 0 supermassive black holes in the process of merging. But when they get really close, they give off gravitational waves. So there are these periodic ripples in the fabric of space-time. And when all the waves in the universe add up together, they form the background we're trying to detect. Once astronomers detect these long gravitational waves, they'll be able to figure out how many supermassive black holes are out there, how often they merge, and why. It'll be pretty fascinating to see what they find. Is it just gravity? Or maybe there's a lot of extra gas or stars around the black hole, which makes them merge faster than they would if they were doing it just from gravity. Meanwhile, other instruments are about to join the search for ultra-long gravitational waves with pulsars. The European Space Agency is planning to launch the first space-based gravitational wave detector, the FOX Laser Interferometer Metric Space Antenna, in 2030. It also detects high-frequency gravitational waves from stellar mass black holes as they make their last spins before colliding. We're using the system's antenna to time arrays of pulsars. Scientists are hoping to catch supermassive black holes orbiting at a rate of 1 revolution in a few years. FOX will study the middle ground in terms of orbits, which take a few minutes to complete. We're hoping FOX will be able to detect the merger of white dwarfs and the final merger of those supermassive black holes that the count will detect in the early stages of a special incident overnight, Lynch says. It's known that there are tens of thousands of double white dwarfs orbiting each other at that speed, but FOX also needs to see other interesting phenomena, such as spiral collapses of small black holes into much larger ones, to detect the low-frequency radio waves and gravitational waves that are produced by all these events. FOX should have a very long lifespan, and there shouldn't be any earthquakes or pizza-making machines around. So, we decided to use a group of 3 satellites following the Earth in orbit around the Sun for this purpose. Regarding the Time Young Pulsar Timing World, CAT has already launched the World of Mystery project we discussed earlier, which will focus on Time Young. There are 1,000 pulsars. It's thought that the antenna system for the timer is, with 1000 pulsars, we can really ramp up the search for ultra-low and high-frequency gravitational waves because the world of CAT is the most sensitive. The Southern Hemisphere telescope was used for chronometry at an earlier point in time. The Aristide telescope is more sensitive than the Mercator. Betty's sensitivity is almost the same. The new Chinese telescope is more sensitive than the others, but they're all in the Northern Hemisphere. The world of comets could be really useful for chronometers outside of those pulsars that emit irregularly. That is, they sometimes give a glitch in the period of bitterness, or their emission in the radio and X-ray range varies. There are only a few well-timed pulsars around today, mostly because astronomers have been collecting data on them for a long time, worldwide. It can also help us find more pulsars that are reliable and get these observations done much faster, since it's really sensitive and can get the same result in less time. Even if astronomers don't detect gravitational waves using system antennas to time pulsars. These system antennas could be useful for some other applications, such as creating a time reference based on timing pulsars. Right now, the gold standard on Earth is International Atomic Time, which is based on atomic clocks. But is this clock always accurate? There are lots of atomic clocks on Earth, and their readings are averaged to determine the time. But how do we even go about comparing them? George Hawks, an astrophysicist at CERN, ponders this. Even if you made the best clock, there's no way to compare it to anything. In 2012, he and his colleagues came up with a proposal to use the first pulsar-based timescale, similar to the atomic timescale, based on observations from the Parkes PLPL antenna system. The idea is to compare atomic time with time measured from pulsar signals. In 1996, atomic time was found to be slightly different from junk time, though only by a few microseconds. This shows, Hawks says, that we can use pulsar times as an independent reference. We also cross-checked the international atomic time. As we learned from Lee's experiments, pulsars can not only detect gravitational waves with wavelengths on the order of a galaxy, but they can also generate gravitational waves themselves. This also makes them ideal for checking the accuracy of Albert Einstein's most famous theory of gravity, the general theory of relativity. It's never easy saying goodbye, especially when you've spent years working on something. But that's exactly what happened in September 2017. Miguel Carnegie, a theoretical physicist at Berkeley's Center for Cosmological Physics, came to the Institute for Theoretical Physics in the Rockies near Paris to give a talk. It would be a few weeks before the community could rest easy, and the WGE would officially announce to the world the first ever observational merger of two neutron stars. There were still a few weeks to go, but in scientific communities with more than 1,000 employees, it's hard to keep the news secret. Rumors of the collision had already spread across social media from university to university and conference to conference. Reggie got ready to tell the audience that if this discovery was true, it would disprove a lot of alternative theories of gravity. Over a century ago, the scientific community adopted Albert Einstein's general theory of relativity, replacing Isaac Newton's theory of gravitation in what we now call the general theory of gravity. It's not a force, but a warping of space-time. This means that massive bodies bind the fabric of space-time, causing a beam of light to bend when it passes near them. But scientists know that the general theory of relativity has its flaws. It doesn't fit with the physics that describes very small things, like quantum mechanics. The general theory of relativity is great at describing gravity, like how a pen falls if you drop it from a table. The theory explains why, if you're in an elevator and it's moving down solely due to gravity, there's no way to know whether you're on the ground or in a spaceship that's moving at a constant acceleration. This is what's known as the equivalence principle, which basically says that gravitational fields are the same as accelerating reference frames. Similarly, the general theory of relativity explains how planets orbit a star and how galaxies collide. But if we turn on multiple magnification, we need quantum mechanics to explain how electrons orbit around an atom, why a plutonium atom disintegrates, or why two hydrogen atoms fuse to form helium. Some of the mass of the hydrogen atoms is converted into energy in the process. This is how stars get their energy until they run out of fuel and die. It's not possible to reconcile quantum mechanics and general relativity. When we try to use general relativity to explain the behavior of the small or quantum mechanics to explain the behavior of the large, it doesn't work. People start to think that general relativity is the wrong theory. So scientists propose to test it in different systems and environments to try to find errors. They also hope that by looking at different approaches, they can figure out what it takes to come up with a good theory. Alternative theories of gravity usually try to solve two big problems in the general theory of relativity that make it hard for us to understand the universe. First, we need to explain why we need to introduce dark matter, which is the invisible matter that Fritz Zwicky believed was held together. The galaxies in the Coma cluster are pretty amazing. Another issue is that we need to find a way to explain the expansion of our universe, which requires us to understand dark energy. As it stands, the general understanding of dark energy is that it is some kind of unregistered substance that causes the universe to expand. Some alternative theories suggest that it could be a force that's part of gravity. Some theorists believe that gravity is more complex than Einstein thought, and we just haven't seen situations where these complexities have had a noticeable effect, unless dark matter and dark energy are such situations. This is why scientists are developing alternative theories to modify the general theory of relativity. They're hoping to describe all of our observations in a way that doesn't contradict the theory and doesn't involve introducing any dark entities. Many scientists also try to modify the theory just out of curiosity. About a third of the unsolved problems in physics, including dark matter and dark energy, have to do with gravity. For instance, there are still unanswered questions about black holes, the challenge of integrating quantum mechanics and gravity into a unified quantum gravity theory, and the issue of the cosmological constant, according to Milk River. Even before astrophysicists could prove the existence of gravitational waves, they knew that the merger of two neutron stars would disprove some alternative theories of gravity. But Carnegie said that at the time he spoke at the conference, many scientists hadn't realized that their favorite theory was about to be disproven. And so in Sokol, he explained how the discovery of the League, which had already been rumored to have taken place, would disprove many alternative theories to the general theory of relativity. As soon as he finished speaking, lots of hands shot up from the audience. Other scientists were taken aback and asked if he was absolutely sure that a particular theory was dead. The conference was like a funeral, he says. He was the first to break the news of the deceased to some of the attendees. However, Carnegie adds that some alternative theories of gravity come about simply because they aren't yet fully understood. Before Einstein came along, lots of top scientists were trying to make sense of electromagnetism and the ether. He says that, although this approach was completely wrong, indeed, it was once thought that light needed a medium, the ether, to travel through. But it was later shown that the ether didn't actually exist. Given all this, it's not surprising that some scientists are questioning whether Einstein was wrong, and whether the general theory of relativity is on the mark. And it's not just about dark energy and matter. If alternative theories of gravity are going to be taken seriously, they'll need to be able to predict all those standard phenomena that the general theory of relativity so successfully predicts. As a rule, most theories don't meet this standard, with many of their predictions proving to be completely wrong. The scientists who came up with these ideas have to come up with ways to fix the mistakes and methods that would hide the wrong predictions for the scales where they can be tested. The most well-known alternative theories of gravity are variations on modified Newtonian dynamics, or simply MOND. In these theories, there's no need for dark matter because the very definition of gravity is changed. They believe there are two types of gravitational forces, not just one. Sometimes people who believe in the Mond theory say that the force of gravity is strong. In this case, objects follow Newton's law of gravitation. This means that the force of gravity between two objects decreases in line with the square of the distance between them. And when gravity is very weak, like on the outskirts of a galaxy, it decreases more slowly with distance, according to this theory. This could be why gravity seems cloudy. There isn't enough matter to hold fast-moving stars inside their galaxies, so there'd be no need to bring in dark matter to ramp up the gravitational pull and get rid of the inconsistencies. MOND is just a general concept. One way to make it a complete theory. The Sklar tensor vector theory of gravity, developed by TBC, has a mathematical framework that can be used to describe a wide range of phenomena, from the solar system to black holes, galaxies, and even cosmology. Like other versions of MOND, the TWS explains why the velocity of stars and galaxies is the same everywhere, given that gravity from the center is stronger than it should be. The theories of Einstein and Newton say that we can't forget about Galileo's theories either. It's part of a group of theories called Horn theories and extended Horn theories. The disks are named after Gregory Horn, the physicist who came up with them in 1974. His ideas really caught the attention of the broader physics community. It wasn't until around 2010, when he'd already retired from science and become an artist in New Mexico, that he published his findings. Most of these theories try to rule out dark energy and make corrections to explain how the universe is expanding and how gravity works. Other theories, like Abrams' gravity theories and Dicke and its variations, build on philosophical or mathematical ideas from the general theory of relativity. There are also some original theories out there, like the one put forth by physicist Eric Verlaine. His theory posits that the laws of gravity naturally emerge from the laws of thermodynamics, much like waves in the ocean are generated by water molecules. Scientists used to spend years developing these theories, deriving equations and refining them. All of this work came to a sudden stop when the first neutron star merger was discovered. When the League mirrors returned, they shook slightly, and the scientific community got to work recording the first such collisions. The Fermi Space Observatory also recorded a short gamma-ray burst coming from exactly the same place, but it arrived on Earth only 7 seconds later. So it was proven that gravitational waves move at the speed of light, which ended the Sklar tensor vector theory of gravity TBC. That theory would have survived only if the speeds of gravitational and electromagnetic waves were different. The League also put an end to several Galileo ion theories that needed an additional field to explain the accelerated expansion of the universe and that gravitational waves travel slower than light. However, not everything was dismissed. Some horn disk theories and extended horn disk theories made it through because they didn't require a difference in the speed of gravitational waves and the speed of light. Some so-called massive gravitational theories of gravity have also managed to stick around so far. Typically, physicists believe that particles associated with gravity have no mass. But these theories accept that it has mass, albeit very small, so it doesn't necessarily travel at the speed of light. Even so, the collision of two neutron stars has shown that some alternative theories of gravity are no longer viable. Scientists have already disproved these theories with other arguments that weren't as flashy but were just as effective. They used celestial bodies in our solar system as examples, and more recently, they've used pulsars, and they're still using these examples today. Time and again, Einstein's theory has been proven correct. But the stronger the gravity, the more likely that the general theory of relativity may be wrong. This is because the greater the density and the stronger the gravity, the more likely it is that the star will collapse into a black hole. Scientists are constantly looking for slight changes in pulsars to see if the pulsar system they're studying aligns with Einstein's theory. These observational results can also be compared to the conclusions of alternative theories of gravity, since the conditions are more extreme in such experiments. Testing the general theory of relativity with pulsars helps physicists draw more conclusions and further rule out some alternative theories. Typically, astronomers use a binary system, like a partnership with a white dwarf or other neutron star, to test the theory with a very accurate clock attached. They then calculate the orbits of the pulsars with great precision, timing the arrival times of the pulsars with great accuracy. Just picture this. We measure the arrival time of the pulse to microsecond precision at this moment, and then again in 10 years. We know exactly how many revolutions the pulsar has made between these two measurements, so we can calculate its rotation rate to the nearest microsecond in 10 years. That's 1 divided by 3 times 10, to the 14th power, or 1 in 300 trillion. On top of that, Astronomers can also look at how the arrival time of pulses changes because of the radiation that passes by. In this case, we're talking about radio waves passing by the Pulsar's partner star. They do this by measuring the Shapiro delay, which is the time delay due to light curvature and gravity. We're really good at measuring time, says Anne Archibald, an astronomer at the University of Amsterdam. She gives an example from when the Cassini space probe passed behind the Sun on its way to Saturn. Scientists recorded radar signals from it and got the time of its passage down to a pretty good accuracy. Obviously, since the light took a curved path due to the Sun's gravity, it took a little longer to reach the detectors on Earth. This is how Shapiro's delay was measured, and Cassini got the best measurements by measuring this delay. They also looked at the predictions made by alternative theories of gravity about light curvature. And of course, calculating this delay helps astronomers figure out the mass of the pulsar itself and its companion star. There are other effects that the general theory of relativity predicts. In 1990, Michael Kramer, who was then a student and is now the director of the Max Planck Radio Astronomy Center and a leading expert in gravitational phenomena, observed the Haas-Taylor pulsar with the 100-meter telescope at Berkeley. He noticed that the pulse shape looked different from what was shown in a paper published 24 years ago. He looked for other descriptions of the pulse profile of this pulsar in past publications and noticed that its shape was changing much more than he'd thought. I looked into it further and analyzed more data, and finally realized that I had seen the first real evidence. Kramer says that the geodesic precession effect of the general theory of relativity, which was predicted for this double star system right after it was discovered in 1974, is at work here. The geodesic precession effect is caused by a massive object from the Kremlin spinning around itself in space. In this case, the axis of the gyroscope is slightly off-center, tracing out an angle greater than 360 degrees per revolution. As the pulsar orbits its companion, the partner's mass pulls it into the gravitational pull of space-time, which bends the beam. The radiation, like a lighthouse beam, shifts ever so slightly, and at some point the beam begins to miss the Earth. Unfortunately, we can't detect the pulsar anymore. Kramer's observations weren't as precise as they could have been because the 100-meter telescope he used wasn't as sensitive as the one used to detect the pulsar. Later on, Joe Taylor, who was one of the astronomers who discovered the binary system, and Joel Weisberg tested the general theory of relativity to see if it was valid. Even so, Kramer figured out how the pulse shape would keep changing over time. He even had the guts to predict, based on his data, that the pulsar would disappear from view between 2020 and 2025. I think few colleagues believed my result, and that's not surprising, he says. A few weeks later, Kramer got an email from Taylor with the graph in it. After reading Kramer's paper, Taylor and Berg took a chance and made new measurements of the pulsar's pulses. It turned out that the pulse widths they had measured matched Kramer's prediction. Kramer says it was a pretty satisfying moment, and it gave him the motivation to keep working with the orbs and testing the general theory of relativity. Physicists like him are looking for ever more extreme conditions to test the theory of gravity. They're hoping that one day they'll find scenarios in which the theory's predictions don't come true, and that would give them a new and better understanding of physics. In 2000, they were fortunate enough to find such extreme conditions. Martha Burke, who now works at the Cagliari Observatory, discovered the unique double pulsar system PSR J073733039AB. She reviewed observational data at the Parkes Telescope in Australia. As we mentioned earlier, this is the only double system we know of where both objects are or were pulsating neutron stars. This system is so relativistic that astronomers have been able to use it to test aspects of Einstein's theory of relativity that have never been thoroughly tested before. On May 5, 2000, at Martha Stormy's, the day began just like any other in her scientific career. She was looking over a survey of pulsar observations made at the telescope. Parkes is always on the lookout for anything that happens near the center of the galaxy, and she suddenly spotted a rapidly spinning pulsar in a double system. At first glance, it was just another ordinary double millisecond pulsar with a not-too-interesting companion, similar to many other double systems. Andrew Line, who worked on Parkes, recalls that the discovery was nothing special, as is the case with any other double system. They started monitoring it to see how it behaved at different intervals. The scientists soon figured out that the companion was probably also a neutron star. It was similar to the double pulsar in Haas, Taylor. In this case, though, the double star system was really close, so Einstein's general theory of relativity had a big impact. The two massive bodies were moving so fast that space-time was extremely strong. Before long, Burke and her colleagues had put together a paper on the new double system. 4 years passed by. One day, astronomer Duncan Lorenz of West Virginia University wanted to test some new software and thought the newly discovered double system was perfect for it. In the spring of 2004, he started working on fixing the bugs in his program, gathering new data on the double system with the Parkes telescope. Then, out of the blue, he picked up some pretty distinctive periodic pulses, which meant that both stars were transmitting radio waves. He gave them a call right away to let them know, that is, on the other side of the globe. Line recalls the moment the phone rang. It was Duncan on the phone. He called to say he'd found a 3-second periodicity and wanted to know what to do about it. One of the two pulsars was spinning really fast, about 45 times a second, while the other was spinning relatively slowly with a period of 7 seconds. Why is this 3-second periodicity so important in a double star system when a second neutron star is forming? It acts like a regular pulsar, and you can't cross into it from a very dense companion. It slows down and shuts down pretty quickly, and then only the milliseconds remain. The 3-second period of the unwound first pulsar was a defining feature of the unwound pulsar. As we saw, the periodicity did change as it should have if the slow pulsar was in a shared orbit with the second pulsar, Wang says. The two neutron stars in this double system are subject to some pretty strong gravitational forces, given that they orbit each other in small radius orbits with a period of just 4 hours. From a cosmic perspective, this makes them pretty close to each other. We can see the system from almost the edge, which means the Earth is almost in the plane of the orbit. This means we see one pulsar pass almost exactly in front of the other, eclipsing it. In March 2008, the slower pulsar vanished. They still haven't picked up a pulse from it. The disappearance of the pulsar is another example of geodesic precession, and scientists think we'll see its pulses again in 2035. This system has allowed scientists to test the general theory of relativity in a much more detailed way than ever before. Before the radiation from the slow pulsar disappeared, astronomers were able to observe two neutron stars orbiting each other with a period of 4 hours at times when the slower pulsar passed in front of its companion. The strong magnetic field blocked the beam of the mini-second pulsar for about 30 seconds. The pulsar is really tiny, only about 20 kilometers across. We couldn't see it because it was blocked by a cloud of dense plasma that rotated with the slow pulsar and generated its own pulses. This bagel-shaped cloud of plasma is held together by the magnetic field of the slow pulsar and rotates with it. Randy Breton, an astronomer at the University of Manchester, was able to create a model of the system in which the bagel intermittently disrupts the pulses from the fast pulsar. As it turned out, the axis of rotation of the bagel, as described by the general theory of relativity, meant that the pulse from the millisecond pulsar reached Earth milliseconds later. Instead of heading straight towards us, it had to pass close to the second pulsar and latch on, which led to the already mentioned Shapiro delay and allowed the precession to be measured. The measurements matched Einstein's prediction exactly, within 99% accuracy. I remember when, at one of our group meetings, Ronnie asked about statistics, Archibald said. There were two ways to analyze the data, and one of them backed up Einstein's theory, while the other didn't. He wasn't sure which approach was the right one. "Hang on a second," said Vicky, our supervisor. "Tell us about the methods, but don't tell us which one agrees with the theory and which one doesn't." We had a bit of a debate and eventually agreed that one of the methods was more correct, and of course, it yielded results. This is in line with Einstein's theory. But we learned a valuable lesson. It's important to keep an open mind and not let personal biases influence your judgment. Kramer and his team have data that suggests the orbit of the two pulsars is shrinking by 7 millimeters every day. The indirect evidence for gravitational waves in the double pulsar is much weaker than the system proposed by Hans Taylor, which Joel Burke still follows today. The rate of compression of the double pulsar's orbit is in line with Einstein's theory, which says that energy is lost faster when gravitational waves are formed. This brings us to the unique triple system. In the summer of 2006, the engineers at the Green Bend Telescope in West Virginia noticed something was wrong with Wilson. The equipment meter was moving left and right on the azimuth. The telescope in Djibouti weighs about 77,000 tons, which is more than originally planned. The plan was to remove the old rail and install a new one, and this took all summer. Since the radio telescope couldn't move in azimuths during this time, it couldn't track sources across the sky, so normal operations were effectively halted. But, as with Alex's observations, the significance of what he saw during the repair was. Some of the astronomers who worked on the project were experts in pulsars. Among them were Archibald and Lynch, who later became an associate scientist at the observatory. James saw that they had a great opportunity to observe the sky. They decided they could use a low-frequency receiver, choose an angle, and just observe the starry sky on a monthly basis, or just floating by. This meant they could see any part of the sky for about 2 minutes, as no one else could work on the telescope while it was being repaired. They used it for almost non-stop observations for a couple of months and ended up with 120 terabytes of data, which went into a review called the Data Review Under Reform. These are scans from the Djibouti 350 Hz telescope. Once the telescope was fixed, Archibald and the forester started going over all their pulsar data. This took them a few years. By 2013, they'd already found several dozen new pulsars. As they were wrapping up their work, they came across something unusual in the last disk of data. They made an interesting discovery: a binary system of a pulsar and a white dwarf located about 200 light-years from Earth. At first, they didn't see anything out of the ordinary, but as they tried to figure out how this double system was moving, they realized they could calculate the orbit of the pulsar by assuming it was orbiting another star. There was no way this solution could correspond to that orbit. Lynch says it suddenly occurred to us that something strange was going on, and then he had a thought. He noticed that the pulsar's orbit was gradually changing, and he suggested that another star might be influencing its trajectory. As it turned out, this system was actually a triple system. He sent an email to Greenwich, and then to everyone else in the group who was looking at the data. Then he and Ingrid SRZ Hal, Archibald, and a forester started testing his assumption. As it turned out, everything fit perfectly when we introduced a third body into the model. No one had ever seen a second white dwarf orbiting a double star like this one, which consists of a millisecond pulsar with 2 stellar mass companions. At that point, we had no idea how to work with a triple system, Archibald told me. She was wrapping up her dissertation at the time, analyzing another source they'd found in the same 2-month sky survey. She was happily distracted from correcting spelling errors. She went through her emails. Colleagues were saying that they didn't know how to get the chronometer and slender system right. I thought there might be a simple solution. And at around 4 a.m., I started writing code using the same direct integration approach we still use today, she recalls. As it turned out, it wasn't the first time she'd written code to directly integrate equations for a system of n bodies, a system with more than 2 objects. At just 15 years old, she read the science fiction book World, The Ring. The book described an alien race that lived on 5 planets orbiting around their common center. Did she think I'd written some kind of code to simulate the motion of this system? Of course, at 15, I didn't have the experience to know what I was doing, and the integration code itself was unstable, so I never got an answer. It was obvious that integrating an n-body problem shouldn't be a challenge. Lynch says that with the triple N system, Archibald did a great job of finding numerical solutions that allow the orbits of all 3 stars to be perfectly described. Her work paved the way for this system to be used later on to test the general theory of relativity. Scientists discovered that in this system, the 3 bodies occupy a very limited space, with orbits smaller than Earth's orbit around the Sun. That's fantastic. To test one of the corollaries of the general theory of relativity, called the strong equivalence principle. The equivalence principle is the foundation of Einstein's general theory of relativity. The idea is that gravity affects everything the same way, regardless of what it's made of or how much mass it has. In most cases, physicists only work with the less stringent version. This is called the principle of weak equivalence, which basically means that objects fall at the same rate regardless of their composition or mass. If you remove air resistance and drop a pen and a hammer from the same height, they'll fall to the ground at the same time. This is an example of gravity in action. This experiment has been successfully demonstrated not only on Earth in NASA's huge vacuum chamber, but also on the Moon. The principle of strong equivalence adds one more thing to the principle of weak equivalence. Even objects that have a large intrinsic mass and gravity must fall in the same way as the others. An object like a planet or star doesn't fall apart because of gravity. Gravity is what keeps all its parts together, creating gravitational energy. Einstein's famous formula states that E is equal to U squared, which is equivalent to a certain mass. Does a body with this mass fall, or are they the same as the bodies made of ordinary matter that we deal with in everyday life? Let's consider a table, for example. Does a body with a lot of gravity fall like ordinary material bodies? As strange as it sounds, it's actually a fair question, says Archibald. Einstein's general theory of relativity says that a body with more self-gravity falls like all other bodies. But almost all alternative theories predict that it falls differently from ordinary bodies. Put simply, they say that if you have an object with a strong gravitational force holding it together, then that object will fall because of the force of gravity itself. Otherwise, you couldn't create an object with strong gravity in a lab. Up until recently, the best way to test the strong equivalence principle was in the Earth-Moon-Sun system. The Earth and Moon are held together by gravity, which also prevents them from flying apart. But the Earth's gravity is much stronger than the Moon's gravity. If Einstein was wrong, and gravity affects how things fall, then maybe the Earth would fall differently than he said. It's not possible to drop the Earth and Moon off a tower like the Flemish scientist Simon Stevin dropped a cannonball off the tower of a new church. However, since the Earth and Moon revolve around the Sun, it's as if they're constantly falling on it. This means that if they were experiencing different accelerations due to the different gravity of the Sun, they would break off the pair. The Earth would still be connected to the Moon, though, thanks to the reflector that the American astronauts from the Apollo spacecraft and the Soviet Lunokhod left on the Earth. We have some pretty precise measurements, but not as many as we'd like. The data are available, and it seems pretty safe to say that there's no difference in how the Earth and the Moon are accelerated by the Sun, Archibald says. You don't need 3 bodies for this experiment, but there has to be some kind of external gravitational field involved. Astronomers have done gravity tests with double systems. For example, they've used a pulsar and a white dwarf experiencing the pull of the galaxy's gravitational field, so to speak, to test how they fall on the galaxy. The issue with these tests is that the galaxy itself causes minor accelerations in the pulsar system. It doesn't attract much, so the difference in how it affects the 2 bodies is also small. The great thing about pulsars is that they're super dense, just like white dwarfs and black holes. Plus, their binding energy is way stronger than that of ordinary bodies. For instance, for a pulsar, it's somewhere between 10 and 15% of its mass. So if this gravitational binding energy reacts differently to gravity than matter does in a neutron star system, it would be much more noticeable. The issue is that while we have a lot of information about our solar system, we don't necessarily know the mass of a neutron star or its companion. We need to figure out how the body should fall based on Einstein's theory, which is tricky if we don't know exactly how strong the external gravitational force is, Archibald says. For instance, when astronaut Dave Scott dropped a hammer and a pen from the Moon in 1973, he dropped them in a gravity-neutral environment, and they fell at the same time. To get accurate results, both objects must fall under the same gravitational attraction from outside. In the Earth-Moon-Sun system, the gravitational attraction comes from a third neighboring body. That means that the Earth and Moon are attracted or falling toward the Sun. The fact that an external gravitational field is needed for the test makes the triple system a pretty unique system for testing the strong equivalence principle. We can't recreate these conditions on Earth, or even on the Moon or Sun. They're just some objects in our galaxy's gravitational field. So Archibald and her colleagues used a computer model with precise parameters based on their observations. It turned out that the pulsar and the inner white dwarf are falling at the same speed in the outer white dwarf's gravitational field. Even though the neutron star is much more massive than its pairing companion, they built a model that allowed for a potential violation of the strong equivalence principle, with the discrepancy described by a parameter called d. If Einstein's theory is correct, the delta should be exactly 0. We weren't just looking for any deviations from the normal orbit parameters. In fact, we were trying to fit our measurements and data directly into the model. Archibald says the model was built under the assumption that Einstein's theories don't apply. The scientists created models of many different orbits with different parameters that showed how they would deviate from the strong equivalence principle. But they discovered that the orbits they created without any deviations, which were based on Einstein's theory, matched their observations. They found that the best value of the delta parameter wasn't exactly 0 because there was still some noise, but it was pretty close. As it turned out, the triple system behaved exactly as Einstein's theory predicts. The test showed that the difference between the calculated value and the observed value was only 3 million. Some scientists were disappointed to find that these calculations also disproved alternative theories of gravity that assumed the pulsar and white dwarf fall differently in the field of the outer white dwarf. Einstein was right again. What's next for general relativity and alternative theories of gravity? Carnegie says this problem keeps him up at night. Now that so many theories have been ruled out, we can focus on the few survivors and try to improve them. It would be great if the Quark Kilometer and other next-generation radio telescopes could find more of these unusual pulsars in the future. This will also let scientists run a more precise test of the general theory of relativity using the timing of pulsar levels. The Weiss Observatory will also be a big help with that once it's up and running. Nevertheless, Archibald says that theorists will probably keep coming up with new theories regardless. One thing astronomers are hoping to find out soon is how the general theory of relativity works. Even more precisely, they're going to study the black hole pulsar system for the first time using either an existing telescope like Betty Rossi or Meerkat, or a new telescope that's just been commissioned or will be up and running soon. For instance, hard disk gravity is strongest in black holes, so a pulsar orbiting around a black hole could be the perfect test subject for studying the structure of spacetime near a black hole. It'll also help us learn more about black holes, for example by measuring their rotational speed. The project, called Black Hole Cam, uses a telescope and other parts to combine data from pulsars and supermassive black holes. Scientists are hoping to detect a pulsar orbiting around a black hole, ideally around CAA. And if we detect more than one pulsar, we should know soon whether the source of the excess gamma rays at the center of the galaxy is dark matter or a pulsar. Neutron stars could either prove Einstein's general theory of relativity is wrong, or show that all alternative theories of gravity are wrong forever. When astronomers observe a pulsar and see that its orbit obeys Kepler's laws of planetary motion, which describe the revolution of the planets around the Sun, they usually determine it using what are called Keplerian parameters. These are the parameters we're talking about. If the orbit is found to have a deviation, scientists tweak the Keplerian parameters to fit the new conditions. These tweaks help scientists describe what they see. One such parameter is the Shapiro delay. Pulsar companions are dense bodies like white dwarfs which bind the pulsar's measured light, or in this case, radio waves. Einstein's general theory of relativity says that this radiation should fall into a hole in the fabric of space-time when it passes by a pulsar companion and then come out the other side and reach our telescopes. This means it takes longer to get here than it would if it were moving in a straight line. In a flat space-time, Shapiro's time delay doesn't test the general theory of relativity. But this delay is something that the theory predicts. If Einstein is right, and we use the general theory of relativity, We can use the characteristics of Shapiro's delay to calculate the mass of the companion. Once we know the mass, it's pretty straightforward to work out the mass from it. Pulsar. But most gravitational checks aren't based on measuring the Shapiro delay. They're based on tracking changes in an object's orbit, usually tiny ones that accumulate over time. For instance, when a pulsar and its companion move around their shared center of mass due to the emission of gravitational waves, the system loses orbital energy. This means their common orbit must narrow, and the pair will gradually converge. In the final stages of the dance that led to the collision, Haas and Taylor's observations in 704M indirectly confirmed this scenario, and the interferon metric experiment provided direct confirmation. When a burst of gravitational waves with a wavelength of 17 nanometers was recorded during the merger of two neutron stars, this was a crucial, direct proof and an important test of the general theory of relativity. Another realistic effect and post-Kepler parameter that astronomers are trying to figure out based on observations of double systems. It's the distance between the closest point on a celestial body's orbit around a star. The general theory of relativity says that in a system with an elliptical orbit, which would be perfect according to Newton, the system isn't closed. Each revolution, the orbit shifts a little bit. It's the same phenomenon as Mercury's perihelion shifting. As it orbits the Sun, it doesn't follow the same path. Its perihelion, the point in its orbit where it's closest to the Sun, shifts by 43 arc-seconds per 100 years due to the curvature of space. By measuring the Castro shift in neutron star double systems, astronomers can figure out how fast the orbit is shifting. This helps them calculate the masses of pulsars and their companions. Once more, let's assume Einstein was right. But if Einstein was wrong, and these formulas are wrong, scientists could get different values for the masses using the two methods. Shapiro's delay is something that happens because of the general theory of relativity. It's a phenomenon that isn't explained by Newton's theory of gravitation. Einstein said that any differences from Newton's theory should be connected in a specific way. In this case, that means they should all lead to the same mass for the pulsar and its companion. If that doesn't happen, it means there's a problem with Einstein's theory, says Archibald. If you know the parameters of two post-Kepler objects and measure a third, you can check whether the value it gives agrees with the others. This was predicted based on the other two, again using Einstein's theory. If you add a fourth parameter, you can test Einstein's theory of relativity again. If scientists find any measurable differences from these predictions, it could mean that Einstein's general theory of relativity might not be the best theory of gravity. But so far, no measurement of post-Hitler parameters has given us any reason to doubt the correctness of Einstein's equations. From the perspective of the general theory of relativity, most pulsars and their systems aren't particularly relevant. They don't allow astronomers to observe any straightforward Hitlerian parameters. It turns out that only a few neutron star systems are relativistic. That means they're massive and move fast enough to make the effects of the general theory of relativity possible to observe. One of them is a chaos double system, among others a double system that Alex Watson discovered in 1990, as well as a pulsar around which 3 planets orbit and which they first discovered in 1992. One of the biggest astrophysical discoveries of the early 21st century was fast radius bursts, or ARBs for short. The mysterious and extremely powerful, ultra-short bursts of radio emission in space, lasting only milliseconds, went largely unnoticed. This discovery could help astronomers figure out what these different galactic environments are made of and how they move around each other. It could also help us measure how strong the magnetic fields are in these different galaxies and shed light on other mysteries. Radio bursts that happen really quickly were once thought to be pretty unusual. They were hard to spot, and because the pulses were so short, it was tricky to pinpoint where they were coming from. We still don't know what these bursts are or where they came from, although there was a lot of interest in neutral stars. The main theory is that these bursts could be coming from magnets. What we do know is that these bursts are 1,000,000 times more powerful than the pulses of radiation from typical pulsars, emitting energy equivalent to that of 500 million suns. They come from objects far beyond our galaxy. It's only recently that scientists have been able to pinpoint RB's sources, even the ones that have only been recorded once. And in recent years, they've recorded more signals than ever before. We can thank two factors for the success of these observations: a more advanced telescope and aliens. It's not the aliens themselves, but the search for them. Many astronomers and astrophysicists are part of this community, trying to understand the nature of these mysterious signals. It was an eccentric Russian-Israeli billionaire who went so far as to become the son of an investor in one of the most complex and large-scale programs ever conducted to monitor radio signals in our universe, in his persistent search for intelligent life beyond Earth. Some astronomers think these flashes might actually be messages from aliens, but it's unlikely. In addition to Magnet, other scientists have put forward ideas about where the army might have come from. For instance, some think that the fast-moving sands might descend in cataclysmic events like supernova explosions or black holes colliding with neutrons or stars. It's also possible that these bursts come from the collision of dark matter, which looks like tiny primary black holes with stars, or they have a more straightforward origin. It turns out the signals aren't from outer space at all, but from microwave ovens. What sets EDRs apart from most other pulsars is that it's impossible to predict when and how they'll start emitting radio waves. Even today, they remain a mystery. Members of this mysterious population are most often detected when registering single bursts rather than periodic pulsars. Some astronomers know of several pulsars that do both. They emit both periodic pulses and sporadic singles. The most well-known example is the prominent nebula pulsar. It sometimes emits a beam of radiation that is more than 10 times more intense than its regular pulses. But EDRs are usually spotted by their unpredictable single pulses, some of which last only a few milliseconds and can be detected for no more than a second a day. We know they're unpredictable, but we quickly realized this is a way to search for a new kind of neutron star, complementing the search methods for traditional objects using periodic pulses, says Vladimir. Researchers soon realized that the radiation from giant single pulsars is so powerful that it can be detected even outside our galaxy. Most pulsars are pretty faint sources of radio waves, so with today's telescopes, we can usually only spot them inside the Milky Way or in the large and small Magellanic Clouds, in their clouds. Laurie and McLaughlin were hoping to find powerful pulsars and the downlinked source by them and other pulsars in more distant galaxies, and thus push the boundaries a little further. They were hoping to be able to detect these kinds of bursts. And there it was, a giant single pulse on the graph, brought in by Markiewicz. It was 10 billion times more powerful than the pulse of an ordinary pulsar and lasted only 5 milliseconds. From the way it was dispersed, Lorentz knew it probably came from far away. It came from outside our galaxy, somewhere in the direction of the Magellanic Clouds. His cloud. When Lorentz and Norkin calculated the dispersion, it was 10 times greater than what you'd expect if the source were in or near our galaxy. Our galaxy is about 100,000 light-years across, which is about 37 billion s. Eventually, he was convinced they'd made a significant discovery. He came home that day and told his wife they might have discovered a new space object. They spent the first few weeks trying to figure out what it was. Vladimir says he just put it aside for a while because it was so bright and so obscure. Bell says the signal was so overwhelming that it kept him up at night for a while. He kept imagining how incredible it would be if the signal was really that bright and came from so far away. That's why, even though the signal was still a mystery, astronomers had only half-jokingly named its source El Matin. The first one was called Little Green Men 1, and the other 3 pulsars whose signals Bell detected were named N2, LDPM3, and LDPM4, respectively. As she kept looking, she noticed a second pulsar, then a third, and a fourth. And they were all in different parts of the sky, which proved it without a doubt. These were natural objects, not extraterrestrial in origin. Laurie Mayer didn't have the same experience. As soon as they published their paper in November 2007, which got people's attention, scientists started sharing ideas about where these strange flashes came from. At around the same time, Laurie was in Melbourne. He read Laurie's article and was intrigued, so he reached out to her to discuss it further. Laurie thought the flashes were a kind of mysterious effect, but, like a lot of other people, he thought it might have been an instrumental artifact. And then, things basically ground to a halt. For the first 6 years after the discovery, neither Laurie nor anyone else saw anything similar. The general feeling was that the outburst was a hoax, and that the 16 similar giant pulses recorded on the park's telescope, which were caused by the accidental opening of a door while heating, did not support Laurie's findings. Astronomers were pretty skeptical about the outburst that Markiewicz first spotted. Maura McLaughlin even wrote a paper saying that her husband's discovery was probably based on a mistake. At the same time, he was looking into the idea of intelligent life on other planets and coming up with ideas about how we might find out if it's true. In one paper, he suggested that radio antennas used to detect the emission of hydrogen atoms in the early universe could also be used to detect alien radio signals. Each atom emits at specific wavelengths, and this property helps astronomers understand which gas atoms were present in space in the past, from planets about 10 light-years away. Another article proposed scanning the solar system with the Hubble Space Telescope to look for signals of artificial origin from aliens. Another article proposed a way to detect industrial pollution in the atmospheres of exoplanets. Laurie Meer, however, wasn't interested in alien worlds or following the work. Instead, he waited and hoped that someone would notice at least one more outburst as strange as the one he had once seen. And finally, that event occurred in 2013. An international team published a paper that named Dan Thorne, who was a doctoral student at the University of Manchester at the time, as the lead author. The authors said they'd spotted 4 bright radio bursts in a review of a year's worth of observations made at the park's telescope. The scientists figured the bursts were probably happening about every 10 seconds, or around 10,000 times a day. After some discussion, the authors came up with names for the bursts. Eventually, the scientists decided to go with a different name, which became established after they abandoned the idea of calling them fast radios, transients, or Ford for short. On top of that, Bell says the gamma-ray bursts called ARBs were already well known. By naming their bursts radio emission, they played on the similarity of the acronyms. As time went on, more and more astronomers around the world started to believe that these short bursts of radio emission were real. In fact, the mysterious Barbies were even mentioned in university physics courses. Lawrence became quite well known, although the theory about where these bursts came from wasn't fully understood. There were more theories about these bursts than there were bursts themselves. Spacetime, as a concept, revolutionizes our understanding of the universe. It's a 4-dimensional framework combining the 3 dimensions of space length, width, height, and 1 dimension of time into a single manifold. Instead of treating space and time as separate entities, they intertwine into a 4-dimensional fabric, dramatically altering how we perceive reality. Albert Einstein's theory of special relativity, published in 1905, was the first to introduce this concept. In this theory, the speed of light is constant for all observers, regardless of their relative motion. This invariance leads to startling effects like time dilation and length contraction. Imagine 2 observers, one stationary and one moving at a speed close to the speed of light. The moving observer's clock will tick slower, and their ruler will appear shorter from the stationary observer's viewpoint. This interplay between space and time dimensions was the birth of the space-time concept. Einstein's general theory of relativity, published in 1915, further expanded on the concept of space-time. Here, Einstein proposed that mass and energy warp the space-time around them. This warping of space-time creates what we perceive as gravity. So, a planet orbits a star not because of an unseen force acting at a distance, as Newton's gravity suggested, but due to the planet following the curved space-time geometry created by the star's mass. This notion of curved space-time leads to some fascinating and non-intuitive predictions. One is the gravitational redshift of light. When light climbs out of a gravitational field, it loses energy, shifting towards the red end of the spectrum. This effect has been confirmed through experiments on Earth and observations of stars orbiting around black holes. Another prediction is the bending of light around massive objects, a phenomenon known as gravitational lensing. Light follows the curvature of space-time, so light passing near a massive object gets bent, causing the object to serve as a lens. Astronomers have observed this effect numerous times, and it's a powerful tool for studying distant galaxies and detecting dark matter. Black holes are another stunning prediction from the concept of space-time. They represent points where space-time is extremely warped, so much so that nothing, not even light, can escape their gravitational pull. Theoretical work suggests black holes have a singularity at their core, where space-time curvature becomes infinite. Space-time also has implications for the expansion of the universe. Observations suggest the universe is expanding, and distant galaxies are moving away from us faster than closer ones. This makes sense in space-time. It's not that galaxies are moving through space, but rather, space-time itself is expanding. The concept of space-time is also crucial in quantum mechanics, the theory describing the behavior of particles at the smallest scales. However, reconciling quantum mechanics with general relativity's space-time has been a significant challenge. String theory, loop quantum gravity, and other candidates for a theory of quantum gravity are attempts to address this, suggesting that space-time may not be fundamental, but emerge from more basic entities. The concept of space-time also influences the interpretation of quantum mechanics. In the many worlds interpretation, every quantum event that could occur does occur in a separate space-time, leading to an infinite number of parallel universes. Space-time is a central concept in our current understanding of the physical universe. It intertwines space and time into a single entity, provides an explanation for gravity, and makes remarkable predictions, some of which we've observed. It's also central to ongoing attempts to unify quantum mechanics and general relativity into a single theory. The concept of space-time thus stands as one of the most profound and influential ideas in physics. Delving deeper into the concept of space-time, we encounter more complex and intriguing facets. General relativity's space-time is not static but dynamic. It can evolve over time, and its curvature can change due to the distribution of matter and energy. This dynamism of space-time led to the prediction of gravitational waves, ripples in space-time caused by the acceleration of massive objects. These waves were first indirectly detected through observations of binary pulsars in the 1970s, and later directly observed by the LIGO and Virgo collaborations in 2015, marking a significant triumph for general relativity. Moreover, space-time doesn't only respond to matter and energy, but also pressure and momentum flow. This is embodied in the Einstein field equations, the core equations of general relativity, which relate the curvature of space-time to the distribution of matter, energy, and momentum. These equations have numerous solutions, each representing a possible model of the universe, such as the expanding, homogeneous, and isotropic universe modeled by the Friedmann-Lemaitre-Robertson-Walker FLRW metric. The concept of space-time also has profound philosophical implications. For instance, it challenges our perception of now and the flow of time. In space-time, the concept of a universal now doesn't exist. Two events that are simultaneous for one observer may not be simultaneous for another observer moving relative to the first. This relativity of simultaneity upends our intuitive understanding of a universal present moment. Furthermore, the block universe or eternalist interpretation of space-time posits that the past, present, and future are equally real, and that time doesn't flow, but is just another dimension, like space. This interpretation is in contrast with the presentist view, where only the present moment is real, and the past and future do not exist. Space-time also plays a critical role in our understanding of the universe's origins and its eventual fate. In the widely accepted Big Bang model, the universe began as a singularity, a point of infinite density and curvature of space-time, about 13.8 billion years ago. On the other end, the ultimate fate of the universe, whether it will continue expanding forever, collapse into a big crunch, or end in a big rip, depends on the geometry and dynamics of space-time. In the realm of quantum gravity theories, space-time may not be fundamental but emergent. For example, in loop quantum gravity, space-time is a derived concept, emerging from more basic quantum entities known as spin networks. In string theory, space-time is a backdrop where strings vibrate, but the theory also allows for extra compactified dimensions of space-time. Finally, the concept of space-time is also relevant for practical applications. For example, in GPS technology, the time dilation effects due to both special and general relativity must be taken into account for accurate positioning. The concept of space-time, while counterintuitive, has become a cornerstone of modern physics. It has wide-ranging implications, from the fundamental understanding of gravity, the universe's large-scale structure, and philosophical interpretations of time, to practical applications in technology. It also points towards new, yet to be fully understood vistas of physics, such as quantum gravity, where the nature of spacetime could be radically reimagined. The speed of light, approximately 299792 kilometers per second in a vacuum, represents the ultimate speed limit in the universe according to our current understanding of physics. This limit arises from Albert Einstein's theory of special relativity, which states that the laws of physics are the same for all observers in inertial, non-accelerating frames of reference, and that the speed of light in a vacuum is the same for all observers, regardless of their motion or the motion of the light source. The constancy of the speed of light leads to some remarkable phenomena when objects approach light speed. For instance, time dilation occurs when an object moves relative to an observer. From the observer's perspective, the object's clock slows down as it approaches light speed. Simultaneously, length contraction happens, where the object's length in the direction of motion shrinks from the observer's perspective. These results are counterintuitive, but have been confirmed by numerous experiments, such as the time dilation of muons moving at high speeds or atomic clocks flown around the Earth. These effects essentially mean that as an object accelerates towards the speed of light, its time slows, and its length contracts, making it impossible for it to reach or exceed the speed of light. The speed of light as a cosmic speed limit also has profound implications for causality, the principle that causes must precede effects. If information or objects could travel faster than light, it would be possible, in some reference frames, for effects to occur before their causes, leading to logical paradoxes. By prohibiting superluminal faster-than-light speeds, special relativity preserves causality. Moreover, the speed of light limit implies that there is a cosmic information horizon, beyond which we cannot receive information. This horizon is set by the age of the universe and the speed of light. Light from objects beyond this horizon has not had time to reach us since the Big Bang. Therefore, there is a limit to how far we can observe the universe, known as the observable universe. The concept of the light speed limit also affects the synchronization of clocks in different locations, a problem addressed by Einstein's theory of relativity. GPS technology, which relies on precise time measurements, must account for the finite speed of light and the relativistic time dilation and length contraction to provide accurate positioning data. However, special relativity's light speed limit does not forbid the existence of particles that always move faster than light, known as tachyons. While tachyons are a mathematical possibility, they have not been observed and would possess unusual properties, such as having imaginary mass and moving faster the less energy they have. It's also worth noting that while special relativity prohibits superluminal motion through space, general relativity, Einstein's theory of gravity, allows for the possibility of warping space in a way that objects can effectively move faster than light without violating the local light speed limit. This concept is used in speculative ideas about warp drives and wormholes for faster-than-light travel or communication, though whether such phenomena are physically possible remains an open question. Finally, the cosmic speed limit set by light speed is a cornerstone in the quest for a theory of quantum gravity, which aims to reconcile quantum mechanics and general relativity. Some approaches, such as loop quantum gravity, maintain the light speed limit even at the quantum level, while others, such as some versions of string theory, allow for the possibility of superluminal communication via extra dimensions or other mechanisms. Thus, the speed of light acting as a cosmic speed limit has far-reaching implications from the fundamental structure of space and time through the limits of astronomical observation to the frontiers of high-speed travel and communication. It is a central tenet of modern physics, shaping our understanding of the universe and its workings. Continuing the discussion on how the speed of light acts as a cosmic speed limit, it's worth delving into some of the deeper implications and subtleties of this idea. One of the key consequences of the speed of light limit is that it establishes a maximum limit to the rate at which information can be transmitted. This is crucial not only in the realm of physics, but also in information technology and telecommunications. For instance, the latency in long-distance communications, such as between Earth and Mars, is determined by the speed of light. In the domain of computing, the speed of light limit has implications for the design and performance of microprocessors. As chips become more powerful and components are packed more closely together, the distances that signals must travel within the chip become significant compared to the speed of light, affecting the processor's maximum possible processing speed. A common misconception is that the speed of light limit is only applicable to objects in motion. However, the limit is just as relevant for objects at rest. When an event occurs, the information about that event propagates outward at the speed of light. Therefore, an observer at rest relative to the event will not be aware of it until the information reaches them, which could be much later if they are a significant distance away. Furthermore, the speed of light limit has implications for the concept of simultaneity. In the realm of special relativity, two events that appear simultaneous to one observer may not appear so to another observer moving relative to the first. This relativity of simultaneity stems from the finite and invariant speed of light. The invariant speed of light also provides the basis for the constancy of the laws of physics. It leads to the Lorentz transformations, which describe how quantities like length, time, energy, and momentum appear to change for observers in relative motion. These transformations ensure that the laws of physics look the same for all observers. At the quantum level, the speed of light limit also plays a role. Quantum entanglement, where entangled particles appear to influence each other instantaneously, seems to challenge this limit. However, it's important to note that while entanglement can be used to transmit quantum states instantly, it cannot be used to transmit classical information faster than light. The speed of light limit might also have implications for the ultimate fate of the universe. In a continually expanding universe, distant galaxies will eventually recede from us at speeds faster than light due to the expansion of space itself. When this happens, their light will no longer reach us, and they will disappear from our view. The speed of light is more than just a speed limit. It's a fundamental constant that shapes the structure of our universe and the laws of physics. From the smallest scales of particles and quantum phenomena to the vast expanses of the cosmos, the speed of light limit remains a central, unifying concept in our quest to understand the nature of reality. Now let's talk about time dilation and length contraction due to relativistic speeds. In the realm of special relativity, as objects approach the speed of light, they experience profound changes in the perception of time and space. Time dilation is a phenomenon where time appears to slow down for an object moving at high velocities relative to a stationary observer. This means that a clock on a spaceship traveling at near light speed would tick more slowly compared to a clock on Earth. The faster the object moves, the more pronounced the time dilation effect becomes. Consequently, if an astronaut embarks on a journey at relativistic speeds and returns to Earth, they would have aged less than the people who remained on the planet. Conversely, length contraction is the apparent shortening of an object along its direction of motion when observed from a different inertial reference frame. As an object accelerates to relativistic speeds, its length appears to decrease from the perspective of a stationary observer. This effect is reciprocal, meaning that from the object's point of view, the surrounding space appears contracted. The closer an object gets to the speed of light, the more extreme the length contraction becomes. If a spacecraft were to zoom past Earth at near light speed, its length would seem significantly compressed to an observer on the ground. These mind-bending effects arise from the fundamental postulate of special relativity, which states that the speed of light is constant in all inertial reference frames. Regardless of the motion of the source or the observer, light always travels at approximately 299,792,458 meters per second in a vacuum. This invariance of the speed of light has profound implications for our understanding of space and time. In relativistic mechanics, space and time are no longer absolute and independent entities, but are interwoven into a four-dimensional fabric known as spacetime. The faster an object moves through space, the more it experiences time dilation and length contraction relative to a stationary observer. These relativistic effects have been experimentally verified and are not merely theoretical curiosities. Time dilation has been measured using atomic clocks flown on airplanes and satellites, confirming that clocks in motion tick more slowly than stationary ones. The Global Positioning System. GPS relies on precise timing measurements and must account for relativistic effects to ensure accurate navigation. Similarly, particle accelerators, such as the Large Hadron Collider, routinely accelerate particles to near-light speeds, where the effects of time dilation and length contraction become significant. Understanding time dilation and length contraction is crucial for exploring the frontiers of physics and the universe. As we venture into the realm of high-energy particle collisions, astronomical observations of extreme gravitational environments, and the possibility of interstellar travel, relativistic effects cannot be ignored. They challenge our intuitive notions of space and time and remind us of the intricate tapestry of the universe, where the very fabric of reality is subject to the intricate dance of motion and energy. The relativity of simultaneity has profound implications for our understanding of causality and the ordering of events in spacetime. In special relativity, the notion of absolute simultaneity is abandoned, and the temporal order of events can differ between reference frames. Events that are simultaneous in one frame may have a different temporal order in another frame moving relative to the first. This leads to the fascinating concept of the relativity of causality, where the cause and effect relationship between events can be frame-dependent. The relativity of simultaneity also plays a crucial role in the resolution of apparent paradoxes in special relativity, such as the twin paradox. In the twin paradox, one twin remains on Earth, while the other embarks on a high-speed journey and returns to find that less time has passed for them compared to the twin who stayed behind. The resolution of this paradox relies on the relativity of simultaneity and the asymmetry introduced by the traveling twins' acceleration and deceleration. Moreover, the relativity of simultaneity has practical implications in various fields, including satellite navigation and particle physics. In satellite-based navigation systems such as GPS, the relativity of simultaneity must be accounted for to ensure accurate positioning and timing. The motion of the satellites relative to Earth affects the synchronization of their clocks, and relativistic corrections are necessary to maintain the system's precision. Similarly, in particle accelerators, where subatomic particles are accelerated to near-light speeds, the relativity of simultaneity becomes significant in analyzing the interactions and decays of these particles. The concept of simultaneity in special relativity challenges our intuitive notions of absolute time and highlights the intricate relationship between space and time. It reminds us that our perception of reality is shaped by our motion, and that the true nature of the universe is far more complex and fascinating than our everyday experiences might suggest. As we continue to explore the frontiers of physics and push the boundaries of our understanding, the relativity of simultaneity remains a testament to the profound insights and revolutionary implications of Einstein's special relativity. The concept of simultaneity and special relativity is a cornerstone of our modern understanding of space and time. It challenges our intuitive notions of absolute simultaneity and reveals the relative nature of temporal relationships between events. The relativity of simultaneity is a direct consequence of the constancy of the speed of light and has far-reaching implications for causality, the ordering of events in space-time, and various practical applications. As we continue to unravel the mysteries of the universe, the relativity of simultaneity serves as a reminder of the extraordinary depth and beauty of Einstein's revolutionary theory. Now let's talk about the concept of simultaneity and special relativity, a notion that challenges our intuitive understanding of events occurring at the same time. In our everyday experience, we often take for granted that events happening simultaneously in one reference frame will also be simultaneous in all other frames. However, Einstein's theory of special relativity reveals that the concept of simultaneity is relative and depends on the motion of the observers. To grasp the relativity of simultaneity, consider two events, such as two lightning strikes, occurring at different locations. In a stationary reference frame, an observer situated precisely midway between the two events would perceive the light from both strikes arriving simultaneously. This observer would conclude that the lightning strikes were simultaneous. However, the situation becomes more intriguing when we introduce a moving observer. Imagine another observer moving at a high velocity relative to the stationary frame who is also equidistant from the locations of the lightning strikes. Due to the relative motion, this observer will perceive the light from one strike arriving before the other. From the moving observer's perspective, the lightning strikes are not simultaneous, even though they appeared simultaneous to the stationary observer. This discrepancy arises from the fact that light has a finite speed, and the moving observer's motion affects the arrival times of the light signals. The speed of light, denoted as c, is a fundamental constant of nature with a value of approximately 299,792 kilometers per second, or about 282 miles per second in a vacuum. This value signifies the maximum speed at which all conventional matter and hence all known forms of information in the universe can travel. Notably, the speed of light isn't just critical for optical phenomena. It plays a pivotal role in the structure and dynamics of the universe. The constant c appears in many areas of physics, showing its fundamental nature. The speed of light's invariance, meaning it remains constant regardless of the relative motion of its source and the observer, is a cornerstone of the theory of special relativity. Special relativity, formulated by Albert Einstein in 1905, revolutionized our understanding of space and time by marrying them into a four-dimensional space-time continuum. The constancy of light speed leads to surprising outcomes like time dilation and length contraction, observable when objects move close to light speed. In the context of cosmology, the speed of light helps define the observable universe's size. The universe's age is about 8 billion years, but we can see objects that are now 46 billion light-years away due to the universe's expansion during the time the light was traveling to us. Light's finite speed also means that we see celestial objects as they were in the past, the time it took their light to reach us. This look-back time allows astronomers to study the universe's history and evolution. When we look at distant galaxies billions of light-years away, we are seeing them as they were billions of years ago. The speed of light also affects the fundamental limits of technology. For instance, the delay in communication between distant locations in space is governed by light speed. It takes light about 1/28 seconds to travel from the Earth to the Moon, about 8 minutes 20 seconds from the Sun to Earth, and over 4 years from the nearest star, Proxima Centauri. These light-time distances pose challenges for space exploration and communication. In the realm of quantum mechanics, light speed plays a role in the phenomenon of quantum entanglement, where particles can affect each other's states instantly over vast distances, seemingly violating light's speed limit. This apparent paradox, known as the EPR paradox, has led to ongoing debates in the interpretation of quantum mechanics. Moreover, the speed of light has practical applications in technology. For instance, it's used in measuring distances in space through methods like radar and laser ranging. GPS technology also relies on the speed of light. The time it takes for signals to travel from satellites to a GPS receiver is used to determine the receiver's precise location. The speed of light in different media, less than c, leads to phenomena like refraction, where light's path bends when it enters a different medium, and dispersion, where light is split into different colors due to varying speeds in a medium. In fiber optic communications, light's high speed allows for fast data transmission. However, light's speed in optical fibers is only about 2/3 of its speed in a vacuum due to the refractive index of the glass. Research into materials with a lower refractive index or technologies like quantum teleportation could potentially result in even faster communication speeds in the future. Finally, from a philosophical perspective, the speed of light as an insuperable cosmic speed limit speaks to our experience of causality, the idea that causes must precede their effects. Since information can't travel faster than light, effects can never precede their causes, reinforcing our everyday experience of time's arrow. Thus, the speed of light, a seemingly simple physical constant, is deeply woven into our universe's fabric. Its roles in physics, cosmology, technology, and philosophy underscore its profound significance in shaping our understanding of reality. Now let's talk about the historical understanding and measurement of the speed of light. In the 17th century, several astronomers attempted to measure the speed of light. The first quantitatively sound measurement was provided by Ola Romer in 1676, using observations of the moons of Jupiter. He calculated a speed of 227,000 kilometers per second, which is about 75% of the actual value. Then, in 1729, James Bradley used stellar aberration to calculate a speed of 301,000 kilometers per second, which is much closer to the real value. Later in the 19th century, Hippolyte Fizeau used rotating gears to actually physically measure the speed of light at 313,000 kilometers per second in 1849. Just 5 years later, in 1862, Léon Foucault improved on Fizeau's method to get a value within 0.6% of the correct measure we use today. Albert Michelson also made an indirect measurement in 1879 using a rotating mirror. This sequence of increasingly accurate measurements reflected the scientific community's intense interest in pinning down this fundamental constant of nature. Modern techniques using lasers can measure the speed of light to an incredible precision, matching the defined value to the limit of our measurement technology. The story of progressively measuring light speed is indicative of the diligence and ingenuity physicists employed to quantify key aspects of our universe. Their clever experimental designs and persistence set the stage for many of the precise physical constants we rely on today in physics equations and models. The speed of light, approximately 792,458 meters per second in a vacuum, is a fundamental constant in Einstein's theory of special relativity. It serves as the universal speed limit, dictating that no matter or information can travel faster than light. This constraint has profound implications for our understanding of space, time, and the nature of causality. In special relativity, the speed of light is invariant, meaning it remains constant regardless of the motion of the light source or the observer. This counterintuitive property challenges our conventional notions of space and time. As objects approach the speed of light, relativistic effects become increasingly pronounced, leading to phenomena such as time dilation and length contraction. Time dilation is a consequence of the invariance of light speed, whereby a moving clock appears to tick more slowly compared to a stationary clock. The faster an object moves relative to an observer, the greater the time dilation effect. This means that time itself is relative and dependent on the relative motion between the observer and the observed. Astronauts orbiting Earth, for example, experience a slight time dilation due to their high velocity, causing them to age marginally slower than people on the ground. Length contraction is another relativistic effect tied to the constancy of light speed. As an object approaches the speed of light, its length appears to shorten along the direction of motion from the perspective of a stationary observer. This apparent contraction is not a physical compression of the object, but rather a consequence of the relative motion and the finite speed of light. The effect becomes more pronounced as the object's speed approaches the speed of light, with the length theoretically shrinking to zero at light speed. Now let's talk about the paradoxes of time. those intriguing and often mind-bending concepts that challenge our understanding of the temporal universe. Time, as Albert Einstein famously demonstrated, is not an absolute rigid framework, but rather a flexible and relative entity intertwined with the fabric of space itself. This realization opened the door for a multitude of paradoxes that question our basic understanding of time and its properties. The first among these, the grandfather paradox, is a classic thought experiment. Imagine you have a time machine and you travel back to the past to meet your grandfather before he had any children. If you were to prevent him from having children, it would mean your existence is impossible. Yet, here you are, a product of a lineage that you've just negated. This paradox tugs at the threads of causality and deterministic views of the universe, highlighting the potential inconsistencies in the concept of backwards time travel. Next in line is the bootstrap paradox, also known as a causal loop. This occurs when an object or piece of information sent back in time becomes trapped within an infinite cause-effect loop. Suppose a scientist in the future sends a groundbreaking scientific theory back in time, and the recipient of this knowledge publishes the theory as their own. In the future, the scientist then learns this theory from this publication before sending it back. The paradox lies in the question, where did the theory originate? There's also the predestination paradox, somewhat of a cousin to the bootstrap paradox, but with a focus on the actions of individuals rather than objects or information. In this case, a person who travels back in time becomes part of past events in such a way that they were always meant to do so. Their actions in the past are part of the timeline and lead to their original future. This paradox suggests that time travel can be self-consistent and that it's impossible to alter the past in a way that would affect the future. The twin paradox, an outcome of Einstein's theory of relativity, is another stimulating concept. In this scenario, one twin travels into space in a high-speed rocket, while the other stays on Earth. Due to the effects of time dilation, the traveling twin experiences time more slowly and returns to find the Earthbound twin has aged more. This isn't a paradox in the traditional sense, as modern physics provides a resolution, but it does challenge our intuitive understanding of time's passage. The arrow of time paradox, derived from thermodynamics, refers to the one-way direction or asymmetry of time. According to the second law of thermodynamics, systems tend towards disorder or higher entropy over time. This is why we remember the past but not the future, and why we can't unscramble an egg. However, the fundamental laws of physics are time-symmetric. They don't distinguish between past and future. This creates a paradox. If the laws of physics don't favor one direction of time, why does time have an arrow? Quantum mechanics, another fundamental branch of physics, gives us the quantum Zeno effect, a paradox where unstable particles, when observed continuously, appear not to change state, effectively freezing in time. This is contrary to the expected random change of state over time when not observed, hinting at a paradoxical influence of observation on temporal progression. Finally, the Andromeda paradox comes from the relativity of simultaneity in special relativity. Two observers moving relative to each other will disagree on whether events at different locations occur simultaneously. Thus, an observer on Earth deciding to look at the Andromeda galaxy now is seeing light that is 5 million years old. However, due to the finite speed of light and simultaneity's relativity, what we perceive as now in Andromeda is undefined in our frame. It could be their past or future. These paradoxes stimulate ongoing discussions and research in philosophy and physics, fueling our quest to decipher the true nature of time. They remind us that time, an everyday concept so familiar yet so elusive, still holds many mysteries in its unending flow. The Fermi paradox, named after physicist Enrico Fermi, is a temporal and spatial paradox that revolves around the contradiction between high estimates of extraterrestrial life and the lack of evidence or contact with such civilizations. Given the vast number of stars, many of which are older than our Sun, it seems likely that interstellar travel would have already been achieved by an extraterrestrial civilization, and yet we have no definitive proof of their existence. This creates a paradoxical situation that continues to perplex scientists. The temporal paradox is a general term for a discrepancy or contradiction in the timeline of events when considering time travel. It covers a wide range of scenarios, many of which have been explored in science fiction. For example, if a person were to travel back in time and change an event that would otherwise have caused their birth, they would cease to exist and therefore couldn't have traveled back in time in the first place. This creates a loop that cannot be resolved, a fundamental paradox. The time travel paradox is closely related to the temporal paradox. This refers to any scenario in which a time traveler causes changes in the past that would prevent their time travel from occurring. For instance, if a time traveler were to go back in time and inadvertently delay their parents' meeting, they might prevent their own birth, making their time travel impossible. The unproven future paradox is a philosophical concept. It suggests that since the future has not yet occurred, it is inherently uncertain and unproven. While we can make predictions based on past and present knowledge, these predictions are not guaranteed. This paradox questions the very nature of reality and our perception of time. The less time. More time. Paradox is a psychological phenomenon. When given a deadline, we often feel that we have less time than we really do, leading to rushed decisions and stress. However, when we perceive that we have an abundance of time, we often waste it. This paradox reflects how our perception of time can significantly impact our productivity and stress levels. The Sleeping Beauty paradox is a thought experiment in philosophy about uncertain future events. Sleeping Beauty volunteers to undergo a procedure where she will be put to sleep. Once she is asleep, a fair coin will be tossed to decide how long she sleeps. If the coin comes up heads, she is awakened and interviewed on Monday. If it comes up tails, she is awakened and interviewed on Monday, put back to sleep, and then awakened and interviewed again on Tuesday. In the latter case, she does not remember the first interview. Upon awakening, she is asked about the outcome of the coin toss. Despite the equal probabilities of a coin toss, the fact that she could be awakened twice if it comes up tails leads to a paradox about the probability of the coin's outcome. The paradox of time and health is a sociological observation. The paradox is that as medical science progresses, human lifespan increases, giving people more time. However, this additional time is often fraught with illness and disability due to aging, diminishing the quality of that gained time. This paradox highlights the tension between quantity and quality of life in the context of time. Time and its paradoxes provide an endless source of fascination, raising questions that lie at the intersection of philosophy, physics, and human perception. The exploration of these paradoxes encourages us to challenge our understanding of the universe and our place within it. Now, let's talk about the grandfather paradox, a fascinating concept in the realm of time travel and its potential implications for our understanding of the universe. The paradox arises from the hypothetical scenario in which a time traveler journeys into the past and takes an action that prevents their own existence, such as killing their grandfather before he meets their grandmother. This seemingly simple act creates a logical contradiction. If the time traveler's grandfather is killed, then the time traveler would never have been born, and thus could not have traveled back in time to commit the act in the first place. The grandfather paradox highlights the inherent difficulties and potential impossibilities of time travel, particularly when it comes to altering past events. It challenges our notions of causality, which is the idea that every effect must have a cause, and that causes must precede their effects in time. If a time traveler can go back and change the past, it would mean that in effect the time traveler's actions could occur before its cause, the time traveler's birth, violating the principles of causality. One possible resolution to the grandfather paradox is the concept of parallel universes or multiple timelines. According to this theory, when a time traveler alters the past, they create a new timeline or universe that branches off from the original one. In this new timeline, the time traveler's actions have no impact on their own existence, as they originated from a different universe. This interpretation suggests that time travel might be possible without creating logical paradoxes, but it also implies the existence of an infinite number of parallel universes, each representing a different outcome of every possible event. Another approach to resolving the grandfather paradox is the idea of self-consistency, also known as the Novikov self-consistency principle. This principle proposes that the universe has a built-in mechanism that prevents paradoxes from occurring. It suggests that any action taken by a time traveler that would lead to a paradox would be automatically corrected or prevented by the universe itself. For example, if a time traveler attempted to kill their grandfather, they might find that their weapon malfunctions, or they might experience a sudden change of heart, ultimately ensuring that their grandfather survives and the timeline remains intact. The grandfather paradox also raises questions about the nature of free will and determinism. If a time traveler can go back and change the past, does that mean our actions and choices are not truly our own, but rather predetermined by the actions of future time travelers? Alternatively, if the universe does indeed have a self-consistency mechanism, it could imply that our choices are limited by the need to maintain a logically consistent timeline, effectively reducing our free will. Moreover, the paradox has implications for our understanding of the universe's fundamental laws. If time travel is possible and paradoxes can occur, it would suggest that the laws of physics as we currently understand them are incomplete or inconsistent. It might also imply that the universe is more complex and mysterious than we can currently comprehend, with hidden mechanisms and principles that govern the flow of time and the interaction between cause and effect. The grandfather paradox is a thought-provoking concept that challenges our understanding of time, causality, and the nature of the universe. While it raises more questions than answers, it encourages us to explore the possibilities and limitations of time travel, parallel universes, and the fundamental laws that govern our reality. As we continue to investigate these concepts through scientific research and philosophical inquiry, we may one day unravel the mysteries surrounding the grandfather paradox and gain a deeper understanding of the universe we inhabit. The grandfather paradox is not only a captivating thought experiment, but also a gateway to exploring the intricate relationship between time, space, and matter in the universe. As we delve deeper into the implications of this paradox, we uncover a wealth of scientific and philosophical questions that challenge our perceptions of reality. One intriguing aspect of the grandfather paradox is its connection to the concept of entropy, which is a measure of disorder or randomness in a system. According to the second law of thermodynamics, the entropy of an isolated system always increases over time. This means that the universe tends towards a state of increasing disorder, with time flowing in the direction of higher entropy. However, if time travel were possible and paradoxes could occur, it would imply that entropy could decrease, violating this fundamental law of physics. Another fascinating implication of the grandfather paradox is its potential impact on the nature of time itself. Some theories suggest that time is not a linear progression from past to future, but rather a more complex and malleable entity. The concept of closed time-like curves, which are hypothetical paths through space-time that loop back on themselves, allows for the possibility of time travel without paradoxes. In such a universe, the grandfather paradox would not arise because the time traveler's actions would be self-consistent, forming a closed loop in space-time. The paradox also prompts us to consider the role of observers in shaping reality. According to the Copenhagen interpretation of quantum mechanics, the act of observation collapses the wave function of a quantum system, forcing it to take on a definite state. If we extend this idea to the realm of time travel, it suggests that the presence of an observer from the future could influence the outcome of events in the past, potentially resolving paradoxes by collapsing the wave function of the universe into a self-consistent state. Furthermore, the grandfather paradox has inspired numerous works of science fiction, exploring the consequences and possibilities of time travel. These stories often grapple with the ethical and moral dilemmas that arise from altering the past, as well as the potential unintended consequences of changing historical events. They serve as thought experiments, allowing us to imagine and explore the ramifications of time travel in a controlled and imaginative setting. In the realm of physics, the study of the grandfather paradox has led to the development of various theories and models that attempt to reconcile the paradoxical nature of time travel with the laws of the universe. Some of these theories propose the existence of exotic space-time geometries, such as wormholes or cosmic strings, which could potentially allow for time travel without paradoxes. Others explore the idea of time as an emergent property of the universe, arising from the complex interactions of fundamental particles and fields. As we continue to investigate the grandfather paradox and its implications, we are forced to confront the boundaries of our current scientific understanding. It challenges us to think beyond our everyday experience of time and causality, and to imagine the possibility of a universe that is far more complex and mysterious than we can currently comprehend. By grappling with these paradoxes and exploring the frontiers of physics and philosophy, we may one day unlock the secrets of time, space, and the fundamental nature of reality itself. Bootstrap paradox. Bootstrap paradox, a puzzling concept within the realm of time travel, which poses challenging questions about causality and the origin of things. This paradox, also known as a causal loop or ontological paradox, takes its name from the phrase pulling oneself up by one's bootstraps, a metaphor for accomplishing an impossible task. The bootstrap paradox occurs when an object or piece of information is sent back in time, resulting in an infinite loop where the item has no discernible origin. To illustrate this, consider a man who builds a time machine and travels back several decades with a copy of Beethoven's Fifth Symphony. He meets Beethoven, who hasn't written his Fifth Symphony yet, and gives him the copy. Beethoven transcribes the symphony and releases it, and it eventually becomes the very copy the time traveler takes back. In this loop, who is the original composer of the symphony? This paradox presents a challenge to traditional cause and effect reasoning, where every effect has a preceding cause. In the bootstrap paradox, cause and effect become circular, with each one appearing to trigger the other. This circular causality is a concept that traditional logic struggles to accommodate, as it implies an effect can occur before its cause. In relation to time travel, the bootstrap paradox complicates the notion of changing the past. If the past is changeable, then logically, the time traveler could alter events to prevent the future existence of the time machine. However, the existence of bootstrap objects or information, which rely on their future existence to exist in the past, implies an immutable timeline, where all attempts to change the past have already been incorporated into the timeline. This paradox has been explored in various science fiction works, serving as a plot device that allows for intriguing stories about time travel. The TV series Doctor Who has used the bootstrap paradox to explain the existence of certain events and objects. In the movie Interstellar, a complex version of the bootstrap paradox is at play, where the protagonist receives crucial information from his future self. The bootstrap paradox also has implications for our understanding of free will. If time travel exists and bootstrap loops occur, then our actions may be predetermined, as they are part of a self-consistent loop that we cannot alter. This contrasts with the common perception of free will, where we are able to make choices that affect our future. In the realm of theoretical physics, this paradox provokes questions about the fundamental nature of time and causality. Some physicists propose that quantum mechanics, with its inherent uncertainty principle, might provide a solution. One interpretation suggests that in the quantum realm, particles could be in a superposition of states until observed, possibly allowing for multiple, coexisting timelines. The Novikov self-consistency principle, proposed by Russian physicist Igor Dmitrievich Novikov, is another attempt to reconcile the bootstrap paradox with physical laws. This principle asserts that only actions consistent with the existing timeline can be performed by time travelers, effectively preventing any paradoxes. Even with these theories, the bootstrap paradox remains a bewildering concept, illuminating the complexities and peculiarities of time travel. It challenges our traditional understanding of causality, compels us to rethink the nature of time, and pushes us to extend the boundaries of our imagination. Despite the paradox implications, or perhaps because of them, the bootstrap paradox continues to be a rich source of intellectual fodder, stimulating ongoing conversations in philosophy, theoretical physics, and science fiction. The bootstrap paradox, with its circular causality, raises a profound question. Can something exist without an origin? In our everyday experience, everything has a cause or a point of origin. Yet the bootstrap paradox presents us scenarios where things, ideas, objects, people, seem to exist in a loop with no discernible beginning. This challenges our fundamental understanding of existence itself. In quantum physics, there are theories that could potentially accommodate these time loops, where cause and effect can seemingly occur in any order. For instance, quantum entanglement, where pairs or groups of particles interact in ways such that the state of each particle cannot be described independently of the state of the others, might be interpreted as a kind of time loop. Some physicists have even proposed that the entire universe could exist in a sort of quantum superposition, with all possible histories happening simultaneously. The bootstrap paradox also raises intriguing questions about identity. In a scenario where a person travels back in time and interacts with their past self, who is who? Is the individual who traveled back in time the same as the one who stays behind? Or do they become fundamentally different people once their histories diverge? This question has been explored in various works of fiction, such as in the movie Looper, where characters are confronted with their past or future selves. A deeper exploration of the bootstrap paradox can lead us into the realm of metaphysics. For instance, if an object can exist without an origin, does this imply that the universe itself could have come into existence without a cause? This line of thinking opens up interesting debates regarding the nature of the universe and the concept of creation. Furthermore, the bootstrap paradox has implications for our understanding of determinism and free will. If the timeline is fixed and unchangeable, as suggested by the existence of bootstrap loops, then it implies a deterministic universe where all events are predestined. This stands in stark contrast to the concept of free will, where individuals can make choices that influence their future. It's also worth noting that the bootstrap paradox has implications for the ethics of time travel. If one could travel back in time, what would be the moral implications of changing past events? If bootstrap loops are possible, then any changes a time traveler makes have already happened, which raises questions about responsibility and culpability. Lastly, the bootstrap paradox invites us to consider the nature of time itself. Is time linear, flowing from past to future, or can it loop back on itself, as the paradox suggests? The study of time, known as chronosophy, explores these and other fundamental questions about the nature of time. In conclusion, the bootstrap paradox, while seemingly a conundrum, serves as a catalyst for crucial conversations about time, causality, identity, and the very nature of existence. It remains a compelling topic within the realms of theoretical physics, philosophy, and science fiction, providing endless fodder for thought and debate. Now let's talk about the concept of causal loops in relation to time paradoxes, a mind-bending phenomenon that arises when considering the possibilities and implications of time travel. A causal loop, also known as a bootstrap paradox or a self-fulfilling prophecy, occurs when an event or piece of information seems to have no discernible origin, as it appears to be caused by a future event that is itself caused by the original event, creating a circular chain of causality. One classic example of a causal loop is the story of a time traveler who journeys into the past and gives his younger self a notebook containing groundbreaking scientific theories. The younger self then uses this knowledge to make remarkable discoveries and write the very same notebook that he will eventually give to his past self, creating a loop in which the information has no identifiable origin. This scenario raises questions about the nature of causality and whether it is possible for an effect to be its own cause. Causal loops challenge our understanding of the linear progression of time and the idea that every event must have a distinct cause that precedes it. They suggest that the flow of cause and effect may not always be straightforward, and that the universe may allow for the existence of closed time-like curves, which are paths through space-time that loop back on themselves. If such curves exist, they could potentially enable time travel without creating paradoxes, as the events within the loop would be self-consistent and not violate the laws of causality. However, the existence of causal loops also raises philosophical questions about free will and determinism. If an event is caused by its own future consequence, does that mean that the individuals involved in the loop have no real choice in their actions? Are they merely fulfilling a predetermined destiny, or is there room for free will within the constraints of the loop? These questions probe the nature of human agency and whether our choices are truly our own or are instead shaped by the complex web of cause and effect that governs the universe. Another intriguing aspect of causal loops is their potential role in the creation and maintenance of the universe itself. Some theories propose that the Big Bang, the event that marked the birth of the universe, could be the result of a causal loop in which the universe creates the conditions necessary for its own existence. This idea, known as the bootstrap universe hypothesis, suggests that the laws of physics and the initial conditions of the universe may have emerged from a self-consistent loop in spacetime, rather than being externally imposed or requiring a divine creator. The concept of causal loops also has implications for the nature of information and its transmission through time. In a universe that allows for closed time-like curves, information could potentially be passed back in time, creating a self-perpetuating cycle of knowledge. This raises questions about the origin and authenticity of ideas and whether it is possible for information to emerge spontaneously from a causal loop without any external input. Furthermore, causal loops have captured the imagination of science fiction writers and filmmakers who have explored the paradoxical nature of these phenomena in numerous works. Stories involving causal loops often grapple with themes of destiny, free will, and the unintended consequences of meddling with the flow of time. They serve as thought experiments, allowing us to contemplate the mind-bending possibilities of a universe in which cause and effect are not always linear and straightforward. As we continue to investigate the concept of causal loops and their relationship to time paradoxes, we are forced to confront the limits of our current understanding of the universe. These paradoxes challenge our intuitive notions of causality and the nature of time, inviting us to consider the possibility of a reality that is far more complex and enigmatic than we can currently comprehend. By exploring these ideas through scientific inquiry, philosophical discourse, and imaginative speculation, we may one day unravel the mysteries of causal loops and gain a deeper understanding of the fundamental workings of the universe. The concept of causal loops and their relationship to time paradoxes is a fascinating area of exploration that delves into the very nature of causality and the structure of the universe. As we further examine these ideas, we uncover a rich tapestry of scientific, philosophical, and metaphysical questions that challenge our understanding of reality and our place within it. One intriguing aspect of causal loops is their potential connection to the concept of retrocausality, which suggests that future events can influence the past. In a universe that allows for closed time-like curves and causal loops, it is conceivable that the effects of an event could precede its cause, creating a seemingly paradoxical situation. This idea challenges our conventional notion of causality, which assumes that causes must always precede their effects in time. Retrocausality has been explored in various theoretical frameworks, including the transactional interpretation of quantum mechanics, which proposes that quantum interactions involve the exchange of forward and backward propagating waves in time. According to this interpretation, the outcome of a quantum measurement is determined by the interaction of these waves, suggesting that the future can influence the past at the quantum level. If causal loops and retrocausality are indeed possible, they could have profound implications for our understanding of the nature of time and the fundamental laws of physics. Another fascinating aspect of causal loops is their potential role in the emergence of complexity and self-organization in the universe. Some theories propose that causal loops could be a driving force behind the evolution of life and the development of consciousness. For example, the concept of autopoiesis, developed by biologists Humberto Maturana and Francisco Varela, suggests that living systems are characterized by their ability to self-generate and self-maintain through a network of recursive feedback loops. These loops allow the system to continuously produce the components necessary for its own survival and reproduction, creating a self-sustaining cycle of causality. If causal loops are indeed a fundamental feature of the universe, they could help explain the emergence of complex structures and processes, from the formation of galaxies and stars to the development of biological systems and the rise of intelligence. By creating self-reinforcing patterns of cause and effect, causal loops could provide a mechanism for the universe to bootstrap itself into increasingly complex and organized states, without the need for external intervention or design. The concept of causal loops also has implications for the nature of time itself. Some theories propose that time may not be a fundamental property of the universe, but rather an emergent phenomenon that arises from the complex interactions of matter and energy. In this view, the apparent flow of time and the distinction between past, present, and future may be a consequence of the thermodynamic arrow of time, which is determined by the increasing entropy of the universe. If causal loops are possible, they could challenge this conventional understanding of time and suggest that the universe may have a more complex and nonlinear temporal structure than we currently realize. Furthermore, the study of causal loops and time paradoxes has inspired new avenues of research in theoretical physics and cosmology. For example, the concept of closed time-like curves has led to the development of theories that explore the possibility of time travel and the existence of parallel universes. These theories, such as the many-worlds interpretation of quantum mechanics and the idea of a multiverse, propose that reality may be composed of an infinite number of branching timelines, each representing a different possible outcome of every event. In such a universe, causal loops and time paradoxes could be resolved by the splitting of timelines and the creation of alternate histories. As we continue to grapple with the concept of causal loops and their relationship to time paradoxes, we are reminded of the vastness and complexity of the universe we inhabit. These ideas challenge our preconceptions about the nature of reality and invite us to expand our understanding of the possible. By embracing the paradoxical and the counterintuitive, we may unlock new insights into the fundamental workings of the universe and our place within it. Whether through scientific exploration, philosophical inquiry, or artistic expression, the study of causal loops and time paradoxes promises to enrich our understanding of the world and ourselves as we navigate the strange and wondrous landscape of space, time, and causality. Let's talk about the implications of time paradoxes on our understanding of causality. Time paradoxes, such as the grandfather paradox or the bootstrap paradox, challenge our conventional understanding of cause and effect, a principle deeply ingrained in our perception of reality and crucial to the foundations of physics and philosophy. Our understanding of causality operates on the premise that causes precede effects. This is a cornerstone of classical physics, where time is considered linear and unidirectional. However, time paradoxes throw a wrench into these assumptions, suggesting scenarios where effects precede their causes or where cause and effect are cyclic. Consider the grandfather paradox. In this scenario, a person travels back in time and prevents their grandfather from having children, which negates their own existence. The paradox arises because the person's existence is both the cause through the act of preventing their grandfather from having children and the effect being born as a result of their grandfather having children. This creates a contradiction, as the effect the person's existence should not be able to eliminate its cause. The bootstrap paradox further complicates our understanding of causality. In this paradox, an object or information sent back in time becomes its own cause. For instance, a scientist who receives a scientific theory from their future self becomes both the cause as the future sender and the effect as the past receiver of this information. This creates a cycle where cause and effect feed into each other, seemingly lacking an initial cause. These paradoxes suggest a model where time isn't simply linear, but can loop or curve back on itself, leading to situations where cause and effect can be reversed or cyclical. This model challenges not only our intuitive understanding of how time works, but it also raises questions about the fundamental laws of physics, which are traditionally formulated in terms of initial conditions leading to subsequent evolution. These paradoxes also have implications for free will and determinism. If time travel and paradoxes such as these are possible, it appears to imply a deterministic universe where events are predestined and unchangeable. In this view, free will becomes an illusion because our actions are predetermined by the events that follow them. Within the realm of quantum physics, these paradoxes and their implications for causality might find some resolution. In the quantum world, particles do not have defined states until measured, and interactions can seemingly occur backwards in time. This retrocausality is a feature of certain interpretations of quantum mechanics and could potentially accommodate scenarios where effects precede causes. Theoretical physicists also propose concepts such as the multiverse or many worlds interpretation in an attempt to resolve these paradoxes. In these views, each decision or event spawns a new universe, allowing for multiple timelines where different outcomes can unfold without contradicting each other. Nevertheless, time paradoxes continue to confound our understanding of causality, pushing the boundaries of our knowledge and challenging us to rethink the fundamental nature of time, reality, and the universe itself. They serve as powerful thought experiments that stimulate ongoing discourse and research in physics, philosophy, and even in areas as diverse as literature and film. Indeed, the implications of time paradoxes on our understanding of causality open up a plethora of intriguing avenues to explore. Let's delve deeper into some of these interesting facets. The concept of block universe, also known as eternalism, is a philosophical perspective on time that is compatible with the theory of relativity. It suggests that past, present, and future are equally real and that all events in time already exist. In this framework, time paradoxes like the bootstrap paradox might be resolved, as all events are predetermined and self-consistent. Here, causality appears to be more of a global constraint, not necessarily following a strict past-to-future progression. However, this view leads to the problem of temporal passage, often termed as the now problem. If all points in time are equally real, then what gives us the sense of a present moment moving from the past to the future? This question remains a subject of ongoing philosophical debate and has implications for our understanding of consciousness and subjective experience. The time paradoxes also have profound implications for the philosophy of cause and effect. In a world where effects can precede causes or where cause and effect can exist in a loop, how do we define causality? Some philosophers argue that these paradoxes challenge the very notion of causality and call for a radical rethinking of the concept. In the realm of quantum mechanics, the concept of quantum superposition might offer a way to reconcile these paradoxes. In quantum superposition, a particle can exist in multiple states simultaneously until it is observed or measured. This could allow for different timelines or states of reality to coexist, potentially providing a way to understand time paradoxes without violating causality. Furthermore, time paradoxes have far-reaching implications for our understanding of free will and moral responsibility. If time travel is possible, and if time paradoxes exist, then it would seem that our actions are predetermined and that we can't change the future. This deterministic view challenges our sense of agency and our legal and moral frameworks, which are based on the idea that individuals have control over their actions and can therefore be held responsible for them. The delayed choice. Quantum eraser experiment is another fascinating concept related to time paradoxes. In this experiment, the decision made in the present seems to affect the behavior of particles in the past. This retrocausal behavior appears to violate our classical understanding of cause and effect, suggesting that in the quantum realm, the distinction between past, present, and future may not be as clear-cut as we perceive it to be. The implications of time paradoxes on our understanding of causality are vast and multidimensional, affecting a wide array of disciplines, from physics and philosophy to law and literature. As we continue to probe the mysteries of time, we may have to revise and expand our theories, pushing the boundaries of our knowledge and understanding. Time paradoxes, such as the famous grandfather paradox, pose perplexing questions about the nature of time and causality. The grandfather paradox suggests a scenario where a person travels back in time and kills their own grandfather before their parent is born, thus preventing their own existence. This paradox is a prime example of the inconsistencies that arise when we consider time travel within the framework of classical physics. Enter quantum mechanics, a realm that defies our intuitive understanding of the world. Quantum mechanics introduces the concept of superposition, which allows particles to exist in multiple states simultaneously until measured. This principle is fundamental to understanding how quantum mechanics could potentially resolve time paradoxes. Consider the concept of a qubit, the quantum equivalent of a classical bit. Unlike a classical bit, which can be either 0 or 1, a qubit can be in a superposition of states, meaning it can be both 0 and 1 at the same time. This concept can be extended to time travel, where a time traveler could exist in a superposition of states, both having and not having killed their grandfather. The principle of quantum indeterminacy also plays a crucial role. This principle states that the exact state of a quantum particle cannot be predicted with absolute certainty. Only probabilities can be assigned to different possible outcomes. In the context of time paradoxes, this could mean that the time traveler's actions in the past do not have a fixed outcome, but rather a range of possible outcomes with different probabilities. Moreover, the idea of parallel universes, a concept that arises from the interpretation of quantum mechanics, offers another potential resolution to time paradoxes. According to this interpretation, every possible outcome of a quantum event occurs in a separate universe. Therefore, a time traveler who kills their grandfather would not alter their own timeline, but rather create a new, parallel universe where their grandfather never existed. Furthermore, the concept of quantum entanglement could also be relevant. In quantum entanglement, particles become interconnected, and the state of one particle can instantly affect the state of the other, regardless of the distance between them. This spooky action at a distance, as Einstein called it, could potentially allow for a form of time travel that avoids paradoxes, as changes made in the past would not occur in isolation, but would be instantly reflected in the present. In recent years, scientists have proposed various quantum models that attempt to reconcile time travel with the laws of physics. One such model, proposed by physicist Seth Lloyd, suggests that time travel could be possible within a closed time-like curve (CTC), a concept derived from general relativity. Within a CTC, time loops back on itself, allowing for the possibility of time travel. Lloyd's model, however, only allows for time travel that preserves the consistency of the timeline, thus avoiding paradoxes. Another model, proposed by physicists Daniel Greenberger and Carl Svosel, uses the principles of quantum teleportation to propose a method of time travel that does not violate causality. In this model, a quantum state is transferred from the future to the past, thus allowing for a form of time travel that does not create paradoxes. Despite these intriguing possibilities, it's important to note that the application of quantum mechanics to time paradoxes is still a highly speculative area of research. While quantum mechanics offers tantalizing possibilities for resolving time paradoxes, much more research is needed to fully understand the potential implications and limitations of these ideas. Now, let's talk about the examination of the many worlds interpretation MWI and its implications for time paradoxes, a fascinating area of quantum mechanics that challenges our understanding of reality and the nature of the universe. The MWI, first proposed by physicist Hugh Everett III in 1957, suggests that every quantum event creates a branching of the universe into multiple parallel realities, each representing a different possible outcome of the event. This interpretation offers a unique perspective on the nature of time and the resolution of paradoxes that arise from the possibility of time travel. According to the MWI, whenever a quantum system is faced with a choice between multiple possible outcomes, the universe splits into separate branches, each accommodating one of the possible results. This means that every decision, every measurement, and every interaction creates a multitude of parallel universes, each with its own unique history and future. In this view, reality is not a single linear timeline, but rather a vast, ever-expanding multiverse composed of an infinite number of branching timelines. The implications of the MWI for time paradoxes are profound and far-reaching. In a universe governed by the MWI, time travel and its associated paradoxes can be resolved through the creation of alternate timelines. If a time traveler were to journey into the past and make changes that would seemingly create a paradox, such as the famous grandfather paradox, the MWI suggests that their actions would simply spawn a new branch of reality in which the changes occurred, while the original timeline remains intact. For example, if a time traveler were to go back in time and prevent their own birth by killing their grandfather, the MWI proposes that this action would create a new timeline in which the grandfather dies and the time traveler is never born. However, the original timeline, in which the time traveler exists and makes the decision to travel back in time, would continue to exist in parallel. In this way, the MWI eliminates the logical inconsistencies and paradoxes that arise from time travel, as each possible outcome is accommodated within its own separate reality. The MWI also offers a unique perspective on the nature of causality and the flow of time. In a multiverse governed by the MWI, the concept of a single, linear chain of cause and effect breaks down, as every quantum event creates a multitude of parallel causes and effects across different timelines. This suggests that the arrow of time, which we perceive as the unidirectional flow from past to future, may be a local phenomenon specific to our own branch of reality, rather than a fundamental property of the universe as a whole. Furthermore, the MWI has implications for the concept of free will and the role of choice in shaping our reality. If every possible outcome of every decision is realized in some branch of the multiverse, it raises questions about the nature of human agency and whether our choices are truly free or simply the inevitable result of quantum probabilities playing out across an infinite landscape of parallel realities. The MWI also offers a new perspective on the concept of immortality and the nature of personal identity. If the multiverse is truly infinite and every possible version of ourselves exists somewhere within its branches, then in some sense, we are all immortal, living out countless lives across a boundless tapestry of alternate realities. However, this raises philosophical questions about the continuity of consciousness, and whether the versions of ourselves in other timelines can truly be considered the same individual. The examination of the MWI and its implications for time paradoxes also has significant consequences for the study of quantum computing and the development of advanced technologies. In a universe governed by the MWI, quantum computers could potentially leverage the parallel processing power of multiple timelines to solve complex problems and simulate quantum systems with unprecedented accuracy. This could lead to breakthroughs in fields such as cryptography, drug discovery, and material science, as well as the creation of entirely new industries and technologies that harness the power of the multiverse. However, the MWI remains a highly controversial and speculative interpretation of quantum mechanics, and there is currently no direct experimental evidence to support its claims. Critics argue that the idea of an infinite multiverse is untestable and unfalsifiable, and that the MWI simply shifts the problem of wave function collapse and measurement paradoxes to a larger, more complex arena. Despite these criticisms, the MWI continues to captivate the imaginations of scientists, philosophers, and science fiction writers alike, offering a tantalizing glimpse into the strange and wondrous possibilities of a reality beyond our everyday experience. As we continue to explore the frontiers of quantum mechanics and the nature of the universe, the examination of the MWI and its implications for time paradoxes promises to enrich our understanding of the fundamental laws that govern existence and our place within the grand cosmic tapestry of the multiverse. As we delve deeper into the mysteries of quantum mechanics and the nature of reality, the MWI serves as a reminder of the vast and complex universe we inhabit, challenging us to expand our thinking beyond the confines of classical physics and embrace the paradoxical and the counterintuitive. Whether the MWI ultimately proves to be a valid description of reality or simply a useful thought experiment, its examination and implications for time paradoxes will undoubtedly continue to inspire new avenues of scientific inquiry, philosophical discourse, and imaginative speculation for generations to come. As we further examine the many worlds interpretation MWI, and its implications for time paradoxes, we uncover a rich tapestry of scientific, philosophical, and metaphysical questions that challenge our understanding of the nature of reality and our place within the universe. The MWI not only offers a unique perspective on the resolution of time travel paradoxes, but also raises profound questions about the nature of consciousness, identity, and the ultimate fate of the universe. One intriguing aspect of the MWI is its potential connection to the concept of quantum immortality, which suggests that in a universe governed by the MWI, an individual's consciousness may persist indefinitely across multiple timelines. According to this idea, whenever a quantum event occurs that could result in the death of an individual, such as a fatal accident or a life-threatening illness, the universe splits into two branches, one in which the individual dies and another in which they survive. From the perspective of the surviving individual, they will always find themselves in the branch of reality where they continue to exist, even as countless other versions of themselves perish in parallel timelines. The concept of quantum immortality raises profound questions about the nature of personal identity and the continuity of consciousness across multiple realities. If an individual's consciousness is constantly splitting and diverging into different timelines, can we truly say that the surviving version is the same person as the one who died in another branch of reality? This question becomes even more complex when we consider the possibility of time travel and the creation of multiple versions of an individual across different points in time. Another fascinating implication of the MWI for time paradoxes is the concept of quantum time travel, which suggests that an individual could potentially use the principles of quantum mechanics to navigate between different branches of reality and explore alternate timelines. In a universe governed by the MWI, every possible outcome of every event is realized in some branch of the multiverse, including those that involve time travel and the manipulation of history. For example, if a time traveler were to journey into the past and make changes that would seemingly create a paradox, such as preventing their own birth, the MWI suggests that their actions would simply create a new timeline in which those changes occurred, while the original timeline remains intact. The time traveler could then use quantum time travel to navigate back to their original timeline, effectively circumventing the paradox and preserving the consistency of their own history. The concept of quantum time travel also raises questions about the nature of free will and the role of choice in shaping our reality. If an individual can navigate between different branches of the multiverse and explore alternate timelines, are their choices truly free? Or are they simply following a predetermined path through the quantum labyrinth of possibility? This question becomes even more complex when we consider the possibility of multiple versions of an individual making different choices in different timelines, each shaping their own unique history and future. The MWI also has implications for the concept of parallel universes and the ultimate fate of the universe. If the multiverse is truly infinite, and every possible outcome of every event is realized in some branch of reality, then there may be countless versions of our universe with different physical laws, different histories, and different futures. Some of these universes may be similar to our own, while others may be vastly different, with entirely alien laws of physics and forms of life. This raises profound questions about the nature of the universe and our place within it. Are we simply one tiny branch of an infinite cosmic tree? Or are we part of a larger, more complex pattern that encompasses all of reality? What is the ultimate fate of the universe, and how does the existence of parallel universes and alternate timelines shape that fate? As we continue to explore the implications of the MWI for time paradoxes and the nature of reality, we are reminded of the incredible complexity and mystery of the universe we inhabit. The MWI challenges us to think beyond the confines of classical physics and embrace the strange and counterintuitive world of quantum mechanics, where reality is not a single linear timeline, but a vast, ever-expanding multiverse of possibility. Whether the MWI ultimately proves to be a valid description of reality, or simply a useful thought experiment, its examination and implications for time paradoxes will undoubtedly continue to inspire new avenues of scientific inquiry, philosophical discourse, and imaginative speculation. As we continue to explore the frontiers of physics and the nature of the universe, the MWI serves as a reminder of the incredible depth and richness of reality, inviting us to expand our understanding of the possible and embrace the paradoxical and the unknown. In the end, the examination of the MWI and its implications for time paradoxes is not just a scientific or philosophical endeavor, but a deeply human one, touching on the fundamental questions of who we are, where we come from, and where we are going. As we navigate the strange and wondrous landscape of the multiverse, we are reminded of the incredible capacity of the human mind to imagine, to explore, and to seek understanding in the face of the unknown. Whether we are scientists, philosophers, or simply curious individuals, the MWI invites us to embrace the mystery and wonder of the universe and to continue asking the deep and profound questions that have driven human inquiry throughout history. As we continue to examine the implications of the MWI for time paradoxes and the nature of reality, we are embarking on a grand and epic journey of discovery, one that promises to shape our understanding of the universe and our place within it for generations to come. Whether we ultimately uncover the true nature of reality or simply deepen our appreciation for the incredible complexity and beauty of the cosmos, the examination of the MWI and its implications for time paradoxes will undoubtedly remain a source of fascination, inspiration, and wonder for all those who dare to explore the frontiers of human knowledge and understanding. The fundamental building blocks of matter. Atoms are incredibly tiny particles that make up every object in the universe. Each atom consists of a dense central core called the nucleus, surrounded by a cloud of negatively charged electrons. The nucleus contains two types of particles: protons, which carry a positive charge, and neutrons, which are electrically neutral. The number of protons in an atom's nucleus, known as the atomic number, defines the atom's identity as a particular chemical element. Hydrogen, for instance, has 1 proton, while carbon has 6. Electrons, which are much smaller and lighter than protons or neutrons, inhabit regions around the nucleus known as electron shells or energy levels. These electrons play a crucial role in chemical reactions, as they can be shared, lost, or gained to form chemical bonds between atoms. The arrangement of electrons in an atom determines its chemical properties. The periodic table of elements, a tabular arrangement of chemical elements, is largely organized by atomic number and electron configuration. Elements in the same column or group share similar chemical properties because they have the same number of electrons in their outermost shell. Isotopes are variants of a particular chemical element, which differ in the number of neutrons and consequently in atomic mass. While the number of protons remains the same, the varying number of neutrons among isotopes of an element results in differing physical properties. Some isotopes are radioactive, meaning they decay over time by emitting radiation, a process that has both beneficial and harmful applications. Quantum mechanics provides the framework for understanding the behavior of electrons in atoms. Electrons do not orbit the nucleus in the way planets orbit a star, but instead exist in areas of space called orbitals, where there's a high probability of finding them. These orbitals have different shapes and orientations, providing a three-dimensional picture of an atom's electron distribution. The concept of atoms dates back to ancient Greece, with philosophers like Democritus proposing that matter is composed of indivisible particles. However, the modern atomic theory began in the early 19th century with John Dalton. He proposed that each element consists of identical atoms, and that atoms combine in fixed ratios to form compounds. Later, Janssen, Thomson discovered electrons, and Ernest Rutherford proposed the nuclear model of the atom. Niels Bohr further refined this model by suggesting that electrons occupy specific energy levels. However, the Bohr model couldn't explain certain experimental results, leading to the development of quantum mechanics and the modern, cloud-like model of the atom. Discoveries in atomic theory have led to significant technological advancements. For instance, understanding atomic structure and radiation led to the development of nuclear energy and medical technologies like X-rays and radiation therapy. Conversely, it also led to the creation of nuclear weapons, demonstrating that knowledge about atoms can be used in vastly different ways. Atoms, while minuscule, have immense significance. They form the basis of all matter, influence chemical reactions, underpin life processes, and have technological and medical implications. Understanding atoms is fundamental to numerous scientific disciplines, including chemistry, physics, biology, and environmental science. Certainly, let's dive further into the intricate world of atoms. Atoms are not just simple spheres, but rather dynamic entities where a lot of action takes place. The electron cloud surrounding the nucleus is where chemical bonding occurs. Electrons can be shared between atoms in what's known as a covalent bond, or they can be transferred from one atom to another to form an ionic bond. The type of bond and the way in which the electrons are arranged determine the properties of the substance made from these atoms. Atoms can also absorb or emit energy in the form of light. When an atom absorbs energy, its electrons can move to a higher energy level or shell. When an electron moves back down, it releases energy in the form of light, creating the brilliant colors we see in fireworks or neon signs. This phenomenon is explained by quantum mechanics and is a fundamental principle in spectrometry, a technique used to identify elements in a sample. Atoms are also responsible for electricity. When a voltage is applied across a substance, it can push electrons to move, creating an electric current. This principle is at the heart of all our electronic devices, from smartphones to electric cars. Furthermore, in the nucleus, protons and neutrons are held together by the strong nuclear force, one of the four fundamental forces of nature. This force is much stronger than the electromagnetic force that holds electrons in their shells, but it acts over a much shorter range. One of the most intriguing aspects of atoms is their dual particle wave nature. Electrons exhibit properties of both particles and waves, another concept that arises from quantum mechanics. This wave-particle duality is fundamental to the behavior of atoms and other quantum systems. Extending the concept of atoms, we encounter the realm of subatomic particles. Protons and neutrons themselves are composed of even smaller particles known as quarks. Quarks come in 6 flavors: up, down, charm, strange, top, and bottom. Protons are made of 2 up quarks and 1 down quark, while neutrons are made of 2 down quarks and 1 up quark. In addition to quarks and electrons, there's another class of fundamental particles known as leptons. Electrons are a type of lepton, but there are others, such as muons and tau particles, as well as a variety of neutrinos. These particles do not undergo strong nuclear interactions, but are subject to the weak nuclear force, electromagnetism, and gravity. Lastly, antimatter, a counterpart to matter, is composed of antiparticles, which are identical in mass to particles of ordinary matter, but opposite in charge. When a particle and its antiparticle meet, they annihilate each other in a burst of energy, an interaction central to the operation of PET scanners, a common medical imaging technology.